Oh, okay. Yeah. So hello, everyone. So welcome to the second workshop on representing and manipulating deformable objects. So next slide. Yeah, so we're very excited to have you here for this workshop. So to give a brief introduction, here are the organizers. So we have myself, Daniel, we have Michael here, and we have Martina on Zoom, and we have 5 other organizers, Huang, Danica, Alessandro, David, and Giannis. So why are we interested in this workshop? So deformable objects are everywhere in the world. So they include things like, say, food, dough, clothing, ropes, and so on. But from a robotics perspective, their very large and infinite dimensional configuration space means that some traditional modeling, planning, and control approaches can fail. So there's no clear state representation. So how do you represent the state of a deformable object into your policy or your planner, for example? And then there's very complex dynamics, like if you take an action with a robot and manipulate something deformable, what is the deformable going to look like after that? So next slide. So as a consequence, there's no unified solution. So there's many methods that researchers have proposed, but many of them are highly domain specific. And there's also a general lack of a simulation environment, and the existing simulators that we have are often very noisy or inaccurate if you've ever gone through them like some of us have here. So the goal for today is to try to collect many state-of-the-art current methods that researchers are working on right now, identify possible future research direction, and to connect people from a variety of discipline in this workshop to share ideas and potentially overcome future challenges in deformable object manipulation. Next. Yeah, so there's a broad set of topics that we're excited to cover today, including things like representation, data estimation, simulation, sim-to-real transfer, data-driven methods, control, multi-arm manipulation, specialized tools, and various application that we are excited to cover. Yeah, so next. So Martina, do you want to take it from here?
Yeah. Thank you, Diane. And good morning, everyone. Thanks for being here. I just want to connect to what Daniel said, and I just want to point out one of the emerging fields where the manipulation of deformable object is now needed. And in particular, among the several fields, we also have the one of the precision agriculture, where an example can be found in the European project Canopies I'm working on. And here the challenges are that we need to deal with the high variability of these deformable objects and also of the agricultural settings. But another challenge that arises in this context is also that we need to take into account the fragile nature of these objects. So we have to ensure at all times that these objects are not damaged. So this is just to close our overview of why we're interested in deformable objects and why we think it's nice to have these kind of workshops to talk about them. So now we will go a bit more into the details of how it's structured, this workshop. So as you can see, this workshop will be hybrid. So we'll have in-person speakers and in-person co-organizers, and we'll have online speakers and talks. In total, we have 8 invited talks, and each talk will be 25 minutes, plus 5 minutes for question and answers. And then we'll have a final discussion round at 17. We also have contributed extended abstracts. In particular, we have 17 accepted works, and each work will be presented with a 5-minute presentation that is pre-recorded, and then we'll have a 1-minute live question and answer. And then we also have 10 posters that are only in person during the poster sessions. So we'll start at 8:45, that is in 5 minutes, with our first invited talk by Kimitoshi Yamazaki. Then we'll have at 9:15 Youssef Mezouar as a second invited talk. And then we'll have our first spotlight talk session, that's at 9:45, which will be followed by the poster session at 10:25. And here we'll also have the coffee break. So please grab your coffee and then come by to talk with the authors that will be presenting the posters. That we will resume at 11, and we'll have another invited talk by Ken Goldberg. And at 11:30, we'll have the last invited talk of the morning, that is by Andrea Cherubini. And we'll close the morning with the last spotlight talk session at 12. And next, we'll have the lunch. And we'll reconvene at 13:45, when we'll have the first invited talk of the afternoon, that is by Shuran Song. And at 14:15, we'll have the second invited talk by Rika Antonova. And then at 14:45, we'll have the last spotlight talk session, which will be followed by the poster session at 15:15. Here again, we'll have also the coffee break. And we'll have then at 16 the last two invited talks by Kuntz and Isabella Huang, and by Carolyn Matl. And then we'll close the day, as I said, at 17 with an open discussion round. So now just a few words about how to interact. So the idea of the workshop is to be as interactive as possible. So please ask whatever you want and whenever you want. So you can use the Zoom question and answers, especially if you're joining online. You can also use the Slido event, that is this number 6390877. And old but gold, you can just raise your hand and ask whatever. So either virtually or in person, it always works. And if you want to read, if you miss a talk, or if you just want to read an accepted extended abstract, you will find all the talks and all the contributions on our website. So this is the time for any question about organizational aspects. So I don't know if there are any questions. Okay, well, if there are no questions, I think we can move to the first speaker of the day, that is Kimitoshi Yamazaki. So it is my pleasure to introduce our first speaker, that is Kimitoshi. He received the PhD degree from the University of Tsukuba in 2007. And from 2007 to 2012, he was a project assistant professor in the University of Tokyo. Then he joined Shinshu University in 2012, where he is currently a professor. And his research interests are in robotic vision and immersion planning. Then he joined. So thanks a lot for being here, and the floor is yours.
Thank you. Wait a minute. Okay, thank you, Onaidas, and good morning, everyone. My name is Kimitoshi Yamazaki. It is a great honor for me to have this opportunity to talk. The title of my talk today is Cross Manipulation Based on Hierarchical Shape Prediction. Before starting to talk about today's topic, I would like to introduce my first study of cross manipulation. The video above left shows the work that led to this. Here, a dual-armed mobile manipulator performs various chores. One of these actions is to find a piece of fabric in a room and pick up it. However, since cross does not have a specific shape, one challenge was how to find fabric products in the everyday environment. We proposed an image processing method that responds to wrinkles. Using this technique, the robot can locate fabric products as shown in the video below left. The process flow is shown on the right. There is a learning phase in which SVM builds a discriminator that responds to wrinkle-like image regions. After that, an input image is divided into three categories: wrinkle-like areas, areas that may not be wrinkles, and an area that is neither part. Then, graph cut is applied and we obtain a region of the fabric products. In hindsight, this was a very simple method. Okay. After the work I've just introduced, I began to try to achieve more complex manipulations than just detecting and grasping. On the other hand, I also realized that there are many difficulties in manipulating a cloth with a robot. What I talk should go without saying for everyone here, right? A cloth is a deformable object. This deformability is a factor such as infinite shape state, complex shape, and complex contact and friction force with surrounding environment. Therefore, modeling, recognition, and manipulation of cloth become difficult. However, humans have a high capacity for deformable object manipulation. Therefore, it should not be impossible to achieve this with a robot. For such reason, such kind of research team is very rewarding, I think. Okay, from here, I start the main topic of this talk. Introduced at top right is my colleague, Professor Sophie Arnold, who plays a central role in this work. First, we conceptualize cross-folding task as shown in the figure, this figure. Before starting manipulation, the goal state is given. Then, a sensor data for initial state are obtained. To realize the goal state, robots must predict cross shape and plan the manipulation procedure, include any midway states. We refer to this level as plan level. Okay. The robot then manipulates the planned steps one by one. Here, the motion trajectory should be controlled by predicting how the cross shape will change during the manipulation. We refer to this level as the manipulation scale. Now, I said two kinds of shape prediction are needed. The title of today's talk comes from this fact. To realize cross manipulation as conceptualized on the previous slide, we are building a dual level system as shown here. In the plan scale, overall motion planning, including midway state generation, is performed. In the manipulation scale, which is for executing each step, the cross shape is predicted and controlled by appropriate perception and manipulation, which are online process. Let me now explain in a little more detail. The first part is to estimate the shape of the cloth from the sensor data. A mesh structure is used to represent the shape of the cloth. The nodes of a mesh are usually represented by deterministic values. We basically use that representation. However, there will be some areas where the results of shape estimation are not reliable. In the case of deformable object, one challenge is that the shape in occlusion area is unknown. Therefore, a probabilistic representation consisting of a mean and a variance is also introduced in intermediate process of shape estimation. Below right is an example of adding uncertainty to the shape. The goal of shape estimation is to reconstruct the cross shape from a 3D point cloud. Our approach is to generate a cross mesh that is consistent with both the observation and the known cross topology. We chose to solve this problem as an optimization problem as shown in the blue box here. The procedure begins by estimating the initial values of the mesh from a point cloud. This is here. Then we optimize the geometry and the topological constraints of this. I will explain this procedure step by step. First, we obtain 3D point cloud data, SPC, from the sensor. Then, we convert the point cloud into a voxel representation. At this time, we boost Z coordinates to capture more fine height detail, such as closed wrinkles. Then, we estimate the cross shape probabilistically using the voxel-to-mesh network. We call this the V2M for short. The input of the V2M is the voxel representation, and its output is a probabilistic cross mesh. The probabilistic mesh format describes vertex positions as 3D multivariate normal distributions. Finally, we derive a deterministic estimate using a topological refinement procedure. By minimizing the vertex positions negative, we ensure consistency with the observed shape. By minimizing a topological loss, we improve the realism of the estimated shape. Next, I will give a specific explanation of the plan scale here. The method we proposed is EMDNet. This is a modularized neural network, encode, manipulate, decode network. This neural network consists of 3 parts. The encoder here compresses the shape data, and the manipulation network predicts the deformation caused by the manipulation. And the decoder then reconstructs the shape after manipulation. There are 2 inputs, current shape S sub I and the manipulation input M sub I. Output is the predicted shape S sub I plus 1 after virtual manipulation is added. Okay. EMDNet has 2 functions, shape prediction and manipulation planning. Shape prediction is performed by propagating the network in the forward direction. The predicted shape after manipulation is obtained as a mesh representation, like this. Next, we discuss manipulation planning. Manipulation planning is performed by propagating the error here between the predicted shape and the goal shape S star backward through the network using the error back propagation method. The inputs to the manipulation plan are the current shape and the goal shape. The outputs are the manipulations and the shapes between manipulations to deform to the goal shape. This planning makes it possible to deform to various goal shapes. Furthermore, as shown in the figure on the right, 2 or more manipulations can be performed by connecting multiple network. This is an important point of the our proposed EMDNet. Here is an example of the planning. Current shape is unfolded rectangular shape. The goal shape is shown here. From these inputs, EMDNet outputs both manipulation and intermediate cross shapes, as shown here. Okay, the manipulation consists of peak and release points, as shown in green and red dashed lines. In this case, 3 manipulation steps were automatically generated to obtain a shape that is similar to the given goal shape. Next, I will give a specific explanation of the manipulation scale, shown in the bottom. For the manipulation scale, we assume that the initial state, the final state, and the initial trajectory are provided by the plan scale. And we aim to solve the manipulation scale using 3 core functionalities. That is shape estimation, which I have already explained, and shape prediction, and trajectory correction. The accuracy, flexibility, and the execution time of these three functions must all be at practically applicable levels. Core features of our approach are that we use a mesh format for cross-shape representation and run a forward model of the object dynamics for real-time shape prediction. Here, we explain about online manipulation trajectory correction. The goal of trajectory correction is to make the manipulation outcome S sub n here match the goal shape S star, this one. Formally, we minimize the objective function shown here. To achieve this, we predict the outcome based on step-by-step shape prediction and adjust the manipulation trajectory so that the prediction matches the goal. First, we initialize the manipulation trajectory and estimate the current cross shape. Then we start the manipulation. Manipulation follows the following procedure. First, we predict the final manipulation outcomes S hat sub n here and calculate its error relative to the goal shape S star. If the error is above a set threshold, we trigger trajectory correction, revising the trajectory to reduce the error using back propagation through the prediction network. Alternatively, the error is below the threshold, the robot executes the first one-step manipulation and obtain a new estimate of the resulting shape. By repeating this procedure until all waypoints of the trajectory are processed, we get a trajectory so that the target object into the goal shape. This procedure can also be performed during manipulation. In other words, it is possible to correct the trajectory while folding. Okay. Next, I will introduce our experiments. To verify the feasibility of the proposed method, we set up a task to fold a square piece of fabric. Since it is difficult to collect training data only in the real world, we use a physics simulator to collect various folding data. And Kawada Robotics Hero, a dual-armed robot, was used as the actual robot. And the RGBD sensor was placed in a position directly opposite to the robot. The picture on the right shows the experiment in progress. The training data necessary for training the networks used in the experiments were collected using the following setup. First, we decided manipulation method, that is, operate with one or both hands, and grasping position is limited to the corners of the fabric. The hand is assumed to move in a circular arc, and Axim was used as the simulator. As shown in the movie on the right, Axim provides accurate and stable cloth behavior. In one simulation, the cloth was folded 3 times. The shape of the cloth at rest and the shape of the cloth during manipulation were saved. The number of data collected was over 3,700 sets. Okay. This slide shows a trajectory correction example. The evaluation conditions are as follows. We initialize the trajectory as an arc-shaped curve. The grasp points are defined by the initial trajectory. We evaluate three test scenarios. In scenario 1, manipulation proceeds undisturbed, like this. In scenario 2, friction is lowered, causing the cloth to slip during the manipulation, like this. In scenario 3, an external disruption is applied partway into the manipulation, here. Okay, the figure and the animation in the middle right show an example of manipulation with correction in scenario 3. We observed that with correction, the trajectory was modified appropriately, this blue line, in response to the external disruption. Okay. With correction enabled, the error is about 5% of the cross size. This table shows the results. We also performed experiments using actual dual-arm robot. This diagram shows the example. This diagram shows a unified system combining plant scale, as shown in the pink square, and manipulation scale, as shown in the blue squares. So the plant scale provides intermittent cross shapes, while the manipulation scale generates and modifies trajectories in detail. Here are two videos about one folding action. The left side shows the results when a disturbance is applied during folding. The robot realized midway through that the desired shape was different from the current shape and corrected its trajectory on the fly. By the way, the robot's motion is not smooth in this movie. This is because a new trajectory cannot be generated until the shape prediction result is known. So a wait time is required immediately after the estimation. Since this does not look good, we built a control loop that takes the delay into account. As shown in the right movie, the result is the smoother and quicker motion. Okay. Using the system mentioned in the previous slide, the robot solved a folding problem, this initial shape and the target shape. The left bottom movie shows the first manipulation, and then the right bottom shows the second manipulation. In both steps, one hand manipulation is automatically selected and generated. A similar shape to the goal state was obtained. Okay. I think we still have a little time, so I will introduce some of our other research results. We also apply reinforcement learning and imitation learning to cross manipulation tasks. The upper left movie shows how to lift a folded cloth without losing its shape by reinforcement learning. In the movie below, the robot learned how to fold a shirt while placing it on its chest. On the right is our proposed policy model. It processes two things simultaneously, that is, segmentation of a task into multiple simple actions and reinforcement learning of each action. The bottom right videos show that the proposed method falls better than the single policy for.
Amazingly.
People know how to use Zoom now.
Okay. If we want to manipulate the cloth quickly, we need to understand dynamic shape changes. We have been working on this issue. In the movie above left, we focused not only on the deformability of the cross, but also on its stretchability. The wrinkle pattern created by the pool is used to pass a hanger through a narrow neck hole. Okay. The upper right and lower left videos show assistance in dressing. Here, optical flow is used to cross shape estimation. This enables faster detection of snagging than force sensors. In addition, this approach allows the robot to continue moving without stopping during recognition process. And the lower right shows the assistance of dressing according to human movements. The hybrid control of position and force prevents people from being burdened. We are also working on an efficient and stable method of cross manipulation. The video above left shows what we call pinch and slide unfolding. The hand is moved along the edge of the fabric for efficient unfolding. The right video shows an end effector for more stable manipulation. It performs also the pinch and slide unfolding, and it can stably manipulate the cross. As shown in the bottom movies, we are also developing end effectors in collaboration with a manufacturer of industrial sewing machines. It can pick up a single piece of cotton fabric that is thin and easily adhere to each other. As shown in the center movie, the end effector is highly repeatable. The same end effector can also be used to pick up woven rubber, as shown in the bottom right movies. Okay, today I presented cross manipulation based on hierarchical shape prediction. We have organized the problem of transitioning the cross to the desired shape. The two planning scales, plan scale and manipulation scale, are introduced. Then we presented feasible solutions for each scale and how to integrate them. My interest in deformable object manipulation is boundless. Therefore, we will work on quicker cross handling. To achieve this, we work on estimating the dynamic state of the cross and controlling its shape. Efficient learning of cross manipulation is also important. Since a cross can have an infinite number of states, it must be able to appropriately construct a feature space that represents the relationship between manipulation and shape changes of the cross. In addition to these standard directions, I'm also interested in the elucidation of the mechanism by which people understand deformable object manipulation. Okay, before I finish, a few words. My colleague, Professor Sobi Arnold, is now planning a special issue at Frontiers in Neurorobotics. I kindly introduce you. Please consider contributing. That's all. Thank you very much for your attendance. If you are interested in our research activities, let's collaborate internationally. Please do not hesitate to contact us. That's all. Thank you very much.
Thanks a lot, Kimitoshi. So now it's questions time. So I just want to remind the audience, you can just raise your hand or write in the chat on the Zoom and also use the Slido. So we already have one question. It's from Ariel in the Slido. And he's asking, how is the manipulation represented in order to be fed into the network?
In Slido?
Yeah, you can find the link on the website.
Yes.
Maybe I can also send it here.
Mm-hmm. Oh, it's a very difficult question. Manipulation. How is the manipulation representing the to the fed into the network? Because we have two types of prediction network. So this is one of them. Sorry, I cannot understand very well about this question. So can you explain about this question in more detail? Someone?
Well, Ariel, maybe if you're joining the Zoom or you're in the room, you could probably just
Martina?
explain. Yeah.
I think there's a few people in person who have question too.
Yeah. Yeah. Okay. So we
anyone
can
have
go.
any questions here? I saw a few hands. You might have to walk to the microphone if that's okay. All right. So we have one question now.
Yeah. So that's me who asked the question on the.
Oh, okay. Great.
So
Perhaps I can answer this question. So
I'll try to explain. So I guess you
Okay.
can explain how
can I answer it?
the mesh.
So the manipulation input is very simple. Picking up
Just a
point.
moment, Kimitoshi. So they
Okay.
are repeating the question in the room.
Okay.
Okay, I think you actually need to come here. So he hears it. No, he needs to speak in this microphone so the Zoom participant can hear it.
Yeah. So otherwise, you can just repeat it. Hello.
No, it's a computer. It's this computer.
Okay. Well, I'm the first to ask questions, so I guess I'm hitting all the glitches. Sorry about that. So I was asking, I understood that the object is represented by a mesh. I'm wondering how is the manipulation represented? I guess it needs to be represented somehow in order to be fed into the deep network. So what this representation is?
So the manipulation is simply represented by the point and the lines. I have no slide about it, but so there is two candidates of the picking points, and after the points picked, the trajectory is just linear trajectory. So the robot detect pick and points. It is represented by the 2D coordinates, and after that, the distance to move the other part to folding. So maybe we have 6 degrees of freedom as manipulation input. Is it become the answer for you?
Yeah, thank you very much.
Yeah, thank you.
Okay. Thank you. Are there any other questions?
Yes.
Yeah, I think there's one more question in person.
Yeah. Okay. Let's go through the one in person. We have another one on Slido then. How frequent does the trajectory operation have to be run to ensure accurate manipulation? Okay, so. Okay, let me read the question so that everyone can know it. So now we are addressing the question from Thomas on Slido. That's how frequent or infrequent does the trajectory correction have to be run to ensure accurate manipulation?
It is a parameter to investigate for us. And we decided to about 6 millimeters per one manipulation, because we have about 200 or 300 millimeters for one manipulation trajectory, and we divided the trajectory into 50s. So it means about 6 millimeters. This was our findings as good good frequency.
Okay, perfect. Thanks. So, Daniel, you said there is another question, right?
Yeah, we have one more question. I think you also just come to the laptop. We have to figure it out how to do it more efficiently, but I think
we're sorry.
Hi, I may have missed this, but I was wondering, when you're estimating the state of the mesh, how do you handle occlusion, and do you make any assumptions on the shape of the cloth? Do you have any thoughts on how to generalizing these to different types of fabrics? Thank you.
Okay. in the present, we tried just a simple shape, so maybe it is not the general knowledge, but in our case, we estimate the mesh from the point cloud, but here we may have occlusion. In such a case, such occluded part is estimated with the probabilistically. So after that, we optimize the shape by using the topological constraints. So it means the neighboring points existing near of the present points. Using these topological constraints, after we get this deterministic shape, so using this procedure, we cope with the occlusion part as the some hypothesis and so deterministic shape. Sorry, just a difficult point to answer this question.
Okay, great. Thanks a lot. I don't know if there are any other questions.
I think we have one more quick question. Yeah. Although I think this is the last question, and then we have to move on to the next speaker.
Yeah.
Yeah.
It sort of builds off the other one. Oh, so what sorts of cloth configurations do you expect the system to break down? Like, are there certain shapes you've just tried informally where you just think it just wouldn't work very well and more sensing might be necessary?
Oh, sorry, I don't hear you very well. So
speaking
please.
Okay. What sorts of cloth configurations do you expect the perception system to break down? Have you tried any informally where you think that more sensing might be necessary?
Sorry. Sorry, I cannot answer now. So please contact me after.
Okay.
Okay. Sorry.
Okay, then perfect. Thank you, Kimitoshi. Thanks again. So I think now it's time for the next speaker. Thanks. So now it is my pleasure to introduce our next speaker, that is Youssef Mezouar. And he received the PhD degrees in automation and computer science from the University of Rennes 1 in 2001. And he spent 1 year as a postdoc at Columbia University. And next, he was an assistant professor from 2002 to 2011 in the physics department of Blaise Pascal University in France. And now he holds a tenured position as a full professor at Sigma Clermont since 2012. And he leads the modeling, autonomy, and control of complex system team of the Institut Pascal. And his research interests include sensor-based control with applications to robotic manipulation and mobile robots navigation and coordination. And he is also the coordinator of the H2020 European project, Softmanbot, that I think he will present today. So thanks a lot for being here. And now the floor is yours.
Martina, I'm sorry. My name is Mohammad Al Khatib. I will replace Youssef for today's
Okay.
Then he apologized. He had an urgent meeting now.
Okay.
And he asked me to replace him now. So I'm sorry, like he sent his apologies to everybody.
Okay. That's great. We have you. Then you can just present.
Can you see my screen?
Yeah.
Okay. So good morning, everybody. My name is Mohammad Al Khatib. I'm an associate professor here at Sigma Clermont Institut Pascal also. I will replace Youssef Mezouar today. Professor Youssef, he has a urgent meeting, and I replace him. Youssef is the project coordinator, because we are presenting today Softmanbot, and Youssef is the project coordinator. I am the technical manager of this Softmanbot, so I'm more comfortable with his presentation. Today, I'll present to you advanced robotic technology for handling soft materials, deformable materials in manufacturing sectors, which is called the Softmanbot project. Before I start with the introduction and everything, I would like to show you a brief video. I hope the audio will be reached to everybody. Can you hear the audio?
Yes, it's working.
In today's industry, robots see a widespread implementation for more traditional and repeatable tasks, such as assembly and machining, while dexterous manipulation of soft and deformable material is a complex challenge that researchers are still facing today. From surgery to food handling, from packaging to manufacturing, many tasks involving the handling of deformable materials are today performed manually by skillful human operators. The intrinsic complexity of these tasks lies in the high variability of the handled material shape, making it impossible to automate their execution with traditional robotics techniques. The EU co-founded project Softmanbot started in October 2019. It develops an innovative and holistic robotic system for the handling of flexible and deformable materials within labor-intensive production processes. The developed robotic system will be composed by three main pillars: an advanced perception system to track the state of the product and collaborating with human operators, a multi-sensor adaptive control and planning platform used to regulate the product's state and which will enable human-robot collaboration and AI-based task generalization, and innovative dexterous grippers with smart mechanical design that will integrate sensors and embody grasping manipulation skills with the soft product. The Softmanbot findings will contribute to help robots play a bigger role in European factories, thereby increasing productivity and job quality. The project's consortium is composed by 11 partners from 4 European countries, coordinated by Sigma Claremont, an engineering school connected to the industrial world with a global and international perspective and strong ties to high-end research and entrepreneurship. In order to facilitate the assessment of the performance, transferability, scalability, and large-scale deployment of these solutions, the demonstrations of the project are conducted under real industrially relevant environments in 4 pilot demonstrators involving 4 key manufacturing sectors: toys, Duema, textile, Decathlon, footwear, Plastina, tires, Michelin. The Softmanbot project strives to design a modular and interoperable architecture, develop a robotic perception platform, develop a multi-sensor planning and control system, design and develop intelligent, dexterous, and low-cost grippers for deformable object handling, deliver an environmental, economical, and social evaluation. If you want to stay in touch with the latest updates of Softmanbot project, you can follow us on LinkedIn and Twitter, subscribe to our newsletter, and check the project website.
So, Softmanbot project, as you saw in the video, is by 11 partners in Europe that gather around to manipulate or propose a solution for deformable object manipulation. These partners, we submit the project in 2019, and we were granted around 8 million euros to do this project with four different industrial partners in Spain, Italy, and France. The project was now begin the last year of this project, and for this project, we are aiming to handle some industrial situations. And the situations nowadays can be seen that the partners in Europe now they want to bring back the manufacturing of industry to Europe. How are we gonna go bring back this industry? By proposing some complex materials handling, plus we can human-centered the production with ergonomics, attractiveness, safety analysis, etc. And by this, we focus in 4 different deformable object sectors. The first one is by Huang in Spain, where we assembly and demolding the doors components. Secondly is Decathlon in Italy, where we handle textile industry for manufacturing of texture or fabric with Decathlon. Third is with Plastina in Spain for footwear industry, or demolding the shoe soles. And lastly, with tire industry in France, with the Michelin, with assembly the tires by the superposition of components. I will go one by one just to introduce the problem of deformable objects here that we concern of. For Huang in Spain, this is an enterprise or a company located in Alicante. They work with dolls since more than 30 years, and they are one of the best in Europe in a good quality dolls. The process of manufacturing the doll, as you can see in the image and from the left to right, they pour the raw materials in the molds. They use some pillars or clamps with high force to demold these materials, as you can see in the second image. After that, they assemble these parts to form the doll, as you can see from the right images. As you can see here, the whole process is done manually. And we aim in this project is to facilitate the work of manufacturing the dolls by proposing some solutions. This solution is to help the operators to not do repetitive tasks like this, it's just by supervising. Second, we call it like deformable objects, which is the textile, is from Decathlon, from in Italy, Milan. And here, as you can see, is the process of padding the fabrics. Padding the fabric, starting by putting the pads on top of each other, sewing around with the fabric around the pad, and stretching from the sides to not find wrinkles in it. And after that, checking again this process. Again, it's fully manually processed, and which means that the repetitive work can have a health issue for the operator. And for that, Softmanbot project proposed some solutions. For the third, we call industrial partner, we have the filter plastiner. As you can see from the left image, we have the molding machine where the operator inject some raw materials in the mold. After that, using a plier or a clamp to demold the shoe sole with really high force. As you can see, he used both of his hands on the right image just to demold one shoe. And as you know, repetitive work here can finally have a health problem, some muscular injuries. And Softmanbot proposed some solution for this, for not automatize, no, it's just collaborating the robot with the human for deformable object manipulation. Lastly is Michelin, which is one of the biggest tire manufacturer in the world, one of the biggest three companies in the world for tire manufacturing, more than 120 years of experience. How they manufacture the tire, as you can see here, we have a drum shape process. They put the tire around this drum shape instrument, and they hold it by both hands to do sticking both parts together. And by this, after that, applying high force, as you can see here from the second image, the middle one and the right one, to apply some force on the intersection part to stick both threads together. And as you can see here, it's totally manual and needs to be helped by the robot or the cobot with the operator to do this task and to avoid repetitive task injuries. For this, why we need this Softmanbot? We need to deliver a robotic system capable of obtaining acceptable processing speed during the process. We need also to have a solution for different objects, different sizes, different forms, no fixed position. Also, we need to have a robot and a hand that is dexterous, has a progressive dexterity that needs to perform the task. We also need a high variability in the parts quality, color, hardness, and we also aiming most of the time to worker health problems due to repetitive tasks. For this, we are 11 partners in Europe. We propose a solution to have a common software platform based on ROS, robotic operating system, that having common grippers technologies with sensor integration in it, like tactile and other sensors such as cameras. And we have a common integrator that guarantee the coherence of this project. And we started this one. If you have more to go more detail about the partners, you can go to our website, softmanbot.eu. So what we propose is to have 4 different robotic cells, one for each industrial partners, one for the tire sector, one for the toy sectors, one for the fabric, and the last one for the shoe. As you can see from the top left, we have for the toy sector, we have a robotic cell that can take the toy, demold it, and after that do the assembly. We have from the top right, we have the robotic cell for the fabrics. When we took the pad, we have a specific gripper for that, and then another robot is not mentioned, is not shown here for doing the stitching. From bottom left, we have the robotic cell for the shoe sole, where the operator and the robot was together to demold and evaluate the quality of the shoe. And lastly, we have from bottom left, right, which is the for tire use case. We have the 2 robots that can receive the tire thread, and perform the task to put both of them into each other and do fixation of these 2 threads together. What we have challenges, as you mentioned, for this workshop is the deformable objects of manipulation. For that, we have different challenges based on deformable objects. First, we need to know how to handle these objects. For that, we have different kinds of objects, from toys to texture to tires. For that, we need to have a smart, dexterous grippers. These grippers should be adaptable for the use cases, plus should have some specific properties, which we will discuss after. The second challenge is to learn how to do the task. Like this, we need to do a human-robot collaboration. And once we mention the human, we need to also assure the safety and the ergonomy of the human. Third is to identify the objects, look at them, and to find the best resting positions, which we are working with deformable objects. We need to look at them with robotic perception based in multimodal, such as tactile, such as also vision systems. And lastly, we need to control the pieces deformation while manipulating them, which we need also multi-sensor control and planning. As you can see here from the image, we have the main 3 pillars. We can call it as a pillar of this project, which is the robotic perception, smart dexterous grippers, and multi-sensor control and planning, which we will take each one now. For the first one, which we have a smart dexterous gripper. As you can see here from this figure, we have proposed 4 different grippers. Each gripper has different properties based on the deformable objects. From the left, we have the gripper for the tire use case, where we need a multi-finger gripper that can, from one side hold the first thread, from the second side hold the second one, and put them on top of each other. So we need to have a long stroke plus multi-finger gripper. For the second one, we have a gripper that has properties of high forces. This one, we use it for 2 use cases, for the toys and the shoes, for demolding. This gripper can reach more than 150 newtons for removing or demolding the objects. And also, it has the properties of tactile, which means that we need to get a feedback from the object once we receive it, because once you put the gripper inside the mold, the vision system cannot be adaptable there. For that, tactile properties is important. For the third one, we have the long stroke gripper, which we propose for assembly of the toys, different parts of toys, from the head to legs, arms, which means, and the body, which means we need to have a gripper that vary in the stroke of the gripper, which means that can open very wide or can short and very narrow. And lastly, we need a gripper that have special task. This gripper needs to remove the wrinkle of the fabrics, and after that do the stitching of the pads on the fabrics. We have some first results, as you know, that the Softmanbot project is still going, and we have first preliminary result from the top 2, which is the gripper for the demolding. As you can see, it's about the long stroke of the gripper, can be more than 40 centimeter, which can adapt for different kind of dolls, of different kind of toys. From the middle left, I have a video to show you where we have a gripper for the tire. You can see it's long stroke, and after that, multi-finger gripper. From the middle right, we have the assembly gripper for the toys, where we also, it's very precise. That means can open in very short centimeter or millimeters, the precision, and it's good for simply adding some force to simply the toys. And lastly, we have the gripper for demolding. For demolding, it should have a really high force that can replace the human process. And we put a force sensor, and you can see here in the meter that can reach more than, it will reach more than 150 or 160 Newton, which really, really high force to repeat the task. This is for the grippers. For the second thing, the challenge is the human-robot collaboration, and we know why we need learning the human process. For that, it's not always need to manipulate the object to reach a final position. It's also we need to know how to manipulate it. Doesn't mean that the final position is the important one. Also, how to do it is really important. And by this, we work on learning from demonstration, such as screw-based DMPs, dynamic motion primitives, bilateral calibration, and also because we mentioned that there is a human in the process loop, we also add some human safety and ergonomics. For the human safety, we established some areas that there is nothing happen to the robot, work normally. Some area in orange that the robot needs to reduce velocities. That means we need to have a function that reduce the kinematics of the robot. And some red areas, which means that the human within the workspace of the robot, which means that the robot should stop moving, because when you work with high forces, especially for demolding, more than 150 newtons, we need to empty the space, the workspace of the robot. We need just to have more safety for the human. Second thing, because we are working with a human that can evaluate the process, that can help the robot to do the task, and after that the robot repeat it. For that, we need to know the ergonomics, such as fatigue, some health issues, the posture. Also, we need to have to evaluate the worker ergonomics to have it checked up in every hour. I can show you some work on learning from demonstration. We can see here some using DMPs. From the left, we can see that the operator do the task. As you can, we have some QR codes. We have we save the trajectory by the operator, and after that, in the right video, we have the robot repeat the task the same as the human did. And as you can see that the robot follow the same exact trajectory as the operator. As we said before, that not just the last phase of the process, which is the last position of the object, is important. Also, the way to do the manipulation is also important. We also have some videos about using some learning techniques to learning from demonstration to demold the shoe. As you can see, the operator do the task using some plier with some QR code to calibrate it and also save the trajectory. And after that, the operator, as you can see, they choose the best grasping position, and then the robot perform the same task exactly with the same maneuver. Lastly, we can not just teach the robot by saving trajectory. We also can do some teleoperation, bilateral teleoperation, that we show the robot how to do the task. And after that, the robot can do the task one more time by learning from demonstration. And by this, we can save time, we can use work from distance, etc. And as you can see here, we have a deformable object, which is the bottle, and the operator teach the robot how to handle these objects. For the third part, or the second pillar, is the perception. As I mentioned, we work with 5 different types of deformable objects, such as dolls, shoes, tire treads, and also fabrics. For this, we face some problems or challenges such as object segmentation, shape detection and tracking, wrinkle detection, and also contact point detection. And also we know that the human in the control loop, that's why we need to know where is the human exactly in each second, which means we need human 3D pose estimation. For that, we propose in this consortium, we propose we call it some solutions for each part. For the visual perception, we talk about particle SFTs and also position-based dynamics as rigid as possible models. Also lattice, which is the next advance from as rigid as possible, which is lattice as rigid as possible model. And also now they are working about graphical neural network. These models can give you the shape of the objects. And also some of them can give you also segmentation of the objects that can be used for the next step, which is modeling and controlling the manipulation of deformable objects. Also, we also work on contact determination by work on contact determination based on Kosaret model. Also, contact determination based on probabilistic ensembles. Also, we use some tactile perceptions for grasp stability, which means that we add some tactile sensors on the gripper hand and evaluate the grasp stability. These sensors is like papillary array tactile sensor, digit tactile sensor, thick scan tactile sensor, and sync tactile force sensor. Finally, once we know also the human is around, we need to know where is the human using open pose, 3D position estimation, and also we know the recognition of some actions by the human. That means like he's standing up, he's doing the manipulation, he's away from the machine, he's retreating back, or doing some activity. And we use some deep learning methods to recognize these actions. Some of them result that can we show that for the tire thread, as you can see here, is using as rigid as possible to deformable objects showing shape deformation. And as you can see, it can detect it really nice, track the deformation in each frame. Also, we have this is for the shoe sole. This is using the lattice one. As you can see, it's like around the box, around the objects, and detect the nodes using the lattice as rigid as possible. For this one, we finally work on how to manipulate and how to control and plan the deformable objects manipulation. For this, we propose some shape serving techniques from finite element methods to meshless shape matching. Also we use as rigid as possible geometrical deformation model. Also, we need to know how to grasp the model and how to know if it's grasping it's stable or not. For this, we propose some methods on dynamic grasp synthesis, grasp affordance, deep Q-learning, and grasp stability. For motion planning, also we use the same model is PlayRab, as rigid as possible, geometric information model. We use also G-Explore, which is a model based on G-Explore algorithm. And also we work on optimal control for motion planning. In the end, we propose in this project is to generalize all methods in one. That means that I can use one model for these 4 use cases or for these 4 objects. We use that multitask reinforcement learning and meta reinforcement learning. For some results, on the left, I will show you some result about how we manipulating using some ARAP for, as you can see, once we change the sheet in the image, the robot needs to follow the deformation of the object. On the right, we have the optimal control, but we have different scenarios, different starting position, and we need to know how to reach the final position by sticking 2 threads on top of each other. Finally, I want to show you this video about as rigid as possible shape servoing. where we define the final pose of the object, of the deformable object, and the two robots manipulate the object to that shape. We use different kind of materials, from papers to the shoes from Plastinet company, and also tires from Michelin company. So once we use the a tire thread with different kind of shapes, finer shapes, and both of them the robot succeed to reach that shape. In conclusion, I present to you Softmanbot project, which is advanced robotic system for handling soft materials, deformable materials for industrial sectors. We are around 11 partners that from 4 different countries in Europe that work on these projects. I propose to you the 3 main pillars of this project, which is the robotic perceptions, the smart dexterous grippers, and the multi-sensor control and planning. We propose to you the 4 different industrial sectors that we will work on, 4 different deformable objects, from toys to footwear, textile, and tires. Finally, if you have any more questions, you want more details on one of the methods or one of the how to do the planning or suggestions, feel free to contact us directly using the softmanbot.eu site, or you can go directly and contact us directly. Thank you.
Thanks a lot for the presentation. So now it's time for the questions. So are there any questions from the audience? So you can use, again, the Slido or the Zoom, or just raise your hand. Are there any questions in the room, Daniel?
I don't think so, although it might. Oh, we do have one question. You might have to come up here in the microphone. Yeah. We're going to get the microphone checked during the break, but it won't be for another hour or so.
Okay. Should I talk here or here?
Into the laptop.
Okay. Hi. Thank you for your great presentation. For the last video that you showed us, how did you identify your deformable object using your mesh data? The point cloud. Yeah.
For this one, we have 2 options. We worked before in the beginning of the project on textures, and based on the texture, I would know the deformable object's status now, and then I can move it, or using the ICRA model to move it to the last position or the final position. Nowadays, we are working on different techniques, not using the texture. It's called textureless technique, using deep learning methods. In the video, it's based on texture.
Okay, thank you.
Because of time, I think we should move on to the next session.
No, but we have a last question. Let's go through the question. So there is a question on Slido that is, do you use any simulators in your work? If so, which ones?
For this moment, we don't use any simulator. We work directly with the robot.
Okay.
We have some partners planning to use some reinforcement learning techniques.
Mm-hmm.
But for this moment, as I told you, the project is ongoing, and I think they are going to use some real to sim to real, which is under process now.
Okay, last question that is here in the chat. So it's Jiangzu and says, thanks a lot for the presentation. It seems in the project you have specialized the solution for each scenario. What do you think are the most critical challenges that you cannot have a generalized solution?
Thank you for the question. I think we have some use cases have little bit different issues than the others. For example, we have for Decathlon use case, which is about the fabrics. We need to stretch the fabric using a specified paper and then do the stitching. And by this is different than other methods. For this, the generalization, the ideas or the solution will be a little bit difficult.
Okay, yeah. That makes sense. I guess it's really critical to have a really general solution for everything. Okay, so I think we can move to the next part for of the workshop. And thanks again for being here.
Thank you guys.
Thanks for the interesting talk. So now it's time for the spotlight talks. I'll share the screen with the videos. So Daniel, if you can explain how it works, and then in the meantime, I will share.
Yes. So we're going to be having some spotlight talks right now. So Martina will share her screen with the pre-recorded video from the people with contributed work. So we'll play the video, and then we'll have around 1 minute after each video for a question. So for those, please either type it in the Zoom or Slido, or if you're willing, you can walk up here until we fix the microphone issue. But anyway, I think we should move on to the next speaker. And I see the next speaker is on the Zoom call. Okay, good. So let's play the video.
Hello, everyone. My name is Yu Mingrui. It's a great honor for me to present our work, Shape Control of Deformable Linear Objects with Offline and Online Learning of Local Linear Deformation Models. In this work, we consider the shape control of deformable linear objects, just like these previous works shown in the video. The task objective is to manipulate the DLO to the desired shape. For control, the key challenge is to obtain the exact deformation models. In other words, how the robot motion affects the DLO shape. The previous methods to obtain the deformation model can be summarized as follows. First, using analytical models. However, they are just approximate model and require accurate DLO parameters. As a result, data-driven methods are more practical. They can be further divided into offline and online methods. In offline methods, the most common one is to offline learn a nonlinear global forward kinematics model. However, the model training is usually data inefficient, and they may get into trouble when manipulating a new DLO. The online methods usually online update a local Jacobian metric. These methods can be applied on any new objects, but they are only effective in local configuration and less accurate. To address this issue, we propose a new method which learns the deformation model in a coupled offline and online manner. The model is first trained based on randomly collected data in the offline phase, then seamlessly migrated to the online phase as an initial estimation, and further updated while achieving the shape control tasks. The advantage is that it can allow for both more accurate modeling via offline learning and adaptation to new DLOs via online learning. As for the formulation of the deformation model, we use the local Jacobian in a global way. Here, our Jacobian model is not just a metric, but a mapping from the state to the Jacobian metric. The advantages are that it is both globally effective and more data efficient because it implies a strong linear prior. We proved the reasonability of this formulation under the quasi-static assumption. We use an RBFN to approximate the Jacobian model. We also propose a proper relative state representation as a network input. During the actual manipulation, the weight of the RBFN is further updated to compensate for offline modeling errors. We also analyze the stability of the closed-loop system using the Lyapunov method. We build both 2D and 3D simulation environment. The offline model is trained using only simulation data. First, we compare our Jacobian model with FKM. We test their offline model accuracy on a certain DLO. The results show that our model can achieve more accurate predictions with less training data. We also validate the proposed relative state input. The results show that it can enable the offline model to have better generalization ability on new DRO. Here we show some shape control results in the real world. It has shown that our method can achieve better shape control results than the previous works. Here are more cases accomplished using our method. In summary, our method is more stable and more precise. In conclusion, we propose a new scheme for shape control of DROs, combining both offline and online model learning. We conduct both simulation and real-world experiments to show the superiority of our method. Recently, we have just submitted a journal version of this work, in which we propose new model modifications and training strategies, a new optimization-based controller, a new robust online model updating law, and more detailed simulations and experiments such as dual-arm 2D shape control, dual-arm 3D shape control, some potential application cases, and a demo for obstacle avoidance. That's all. Thanks for listening.
Hi.
Oh, do you have any question for the speaker? Well, I mean, I have a question if that's okay. So I'm actually curious. You talked about offline and online learning. So I'm curious, how far can we go with just offline learning? Like, do you need the online learning, or how important is that stage?
Nowadays, I think, thank you for your question. I think nowadays both offline phase and online phase are important because I think all simulators for the deformable objects are not perfect now, so there are a huge reality gap. That is why we think online model adaptation is very important. But if we have only online phase, the limited online data cannot ensure accurate model learning. Okay, thank you.
Okay, so maybe we should move on to the next video. And is Rui here?
Yes. Thank you, Min Rui.
Here? Yeah, I mean, if they're in the audience, they can come up here, sit here watching the video, and then answer questions.
Okay,
Hi everyone, I'm Goldberg.
Yeah.
And in this workshop, I'm going to present our work entitled An SC3-based formulation of the shape servoing problem. A general approach to solve manipulation tasks is shape servoing, also called shape control. The goal of shape servoing is to provide commands to a robotic manipulator so that it deforms a deformable object autonomously to give it a desired shape. In the literature, there are model-based and model-free approaches. Model-free ones operate in closed loop. The desired shape is given as input and is compared to the current shape of the object. With this, we obtain a shape error that the control law transforms into robot commands. Once these commands are executed, we obtain a new shape of the object from which we extract features of interest to close the loop. Different solutions have been developed for this, but a very interesting one is to use position of points in space, since this provides a direct way to define the target from the task objective. So in this approach, that I will call position-based servoing, the features in the control loop are defined by the three components of points on the object. We note them y and their desired position yd. Moreover, independent grippers grasp the object rigidly and their pose is noted z. Then, if the system is quasi-static, we can linearize around the current configuration to obtain a relation where a Jacobian relates gripper motions to feature motions. This matrix is called the shape Jacobian, and estimating it correctly is a key ingredient of the approach. To estimate J, what we have at disposal is an history of pairs delta Z and delta Y. Several techniques can be used, and in this work, we choose to illustrate with the Broyden update rule, but our method, we emphasize that it is not tied to this rule. What is important to note here is that delta y and delta z used in the update are defined with respect to an inertial frame, so that the shape Jacobian depends on its choice and is not independent on rigid body rotations. Once J has been estimated, we can use its pseudo-inverse and the shape error to obtain gripper commands. Usually, this error incorporates only the position error of the feature points. In our SE3-based approach, instead of using points as features, we propose to use mobile frames defined from the surface of the deformable object. The goal is now to control the grippers such that the feature frames reach a desired pose. This pose incorporates the position of the frame, but also a rotation matrix defining its orientation. HP is the current feature frame, and
I think the video is stopped. Can we try playing it again?
Oh. Martina, are you still there?
I think there's some issues with her connection. So because Italy is far away, but we can just swap to the local version then.
There's a problem with the drive.
It's Windows, gonna work.
Oh.
So now we just need to share our screens. So it should be this one.
Yeah.
Hi everyone, I'm going to add an instruction.
Share the screen here.
So,
yeah,
let's just share the screen. Okay.
This pose incorporates the position of the frame, but also the rotation matrix defining its orientation. HP is the current feature frame, and HT is the desired one. Now, since the shape Jacobian relates motion of frames, we need to redefine the Broyden rule. The key difference is that now we use relative transformations between successive feature frames and use a logarithmic map to obtain the vector that we can use in the Broyden rule. We do the same for the gripper motions, and in the end, all the variables used in the Broyden rule are now coordinate independent and insensitive to rigid body motions, so that it will also be the case of J. Very importantly, we need also to redefine the shape error, so we use the relative transformation between frames HP and HD and the log map. Compared to the traditional approach, the error incorporates also rotation information. Again, we simply invert the model to obtain gripper motions, and we update them with either position or velocity control. To illustrate the results, we have made several experiments in the simulator bivalent. The controller has no access to the object model, and we initialize the Jacobian with null perturbations and finite differences. In the traditional approach, called here position-based servoing, we use 3 points shown in green here, and we use the same points to build the frame HP in our new approach. For small deformations, we observe that both methods work. However, the advantage of SE3-based servoing is more visible for high deformation tasks. Here, coupling position and rotation in the error avoids twists because it deteriorates the rotational part of the error. The trajectory we obtain is smoother and more straightforward. In contrast, for these two tasks, the traditional approach failed. Finally, when we subject the beam to rigid body rotation, we observe that in position servoing, the components of the Jacobian vary non-linearly, while in our approach, it remains constant, which should be the case, since the shape Jacobian should only capture shape variations. Finally, I would like to thank the ERDF that supports this research through the ICRA project. This is an interim project in the region Beudrin that gathers partners from several countries to promote the development of composites in the region. To conclude, I would like to highlight that our approach is not tied at all to the Broyden rule, nor to the controller used here, so our method could be easily extended to other frameworks. Thanks a lot for your attention, and please do not hesitate if you have any questions.
Thank you very much. Any question?
We have questions on Slido, actually. The first question is, yeah, thanks for the presentation. Can you have more than one frame as the target in order to define more complex target shapes?
I speak then.
Towards the laptop, mostly loud.
Yeah. So yeah, you can use several frames. Here. Yeah. You can use several frames. And in the case where the additional frames you add are near the gripper, it will in fact help in succeeding in the task, because the relation between the motion of your gripper and the motion of this frame will be, there will be a high correlation between both, and so it will help in succeeding in a task. But if you define additional frames that are located far away from this gripper, then you have the under-actuation problem that will make it sometimes harder. So I would say to choose the frames, it will depend also on the task and on which points on your object you want to arrive at the good location. So it will depend on your task.
Thank you. I think.
Yeah, we can move on. But there's one more question about how do you determine the initial frame?
Yeah, but so it is related, but so it will depend on your task objective. If you are wanting to just bring some subset of your deformable object to some location, you will choose your inertial frame accordingly. I know it speaks about inertial frame. Yeah. Here it is independent of the inertial frame, the method, because it uses a relative transformation, so you do not need an inertial frame. I don't know if it answers the question.
All right. So next speaker is Peter. I think, yeah, you should probably come up here and we'll play your video. Then if you have any questions, just ask as usual. You can take a seat here if you want. Or up to you.
It's like super silent.
Oh. I think we need the volume.
It's as high as it goes. Sorry.
Is it better if I share? Now I'm back again.
Okay, try it.
This stupid laptop. Okay, let me try. It's quite silent anyhow.
And I'll be discussing our paper titled Data Augmentation. My name is Peter Matrano, and I'll be discussing our paper titled Data Augmentation for Manipulation.
Okay, we're just going to have the presentation live. Do you want to talk over that or just without slides?
I'd rather than mute it so it's not confusing. Yeah, it's probably better or just play it on this side.
Okay.
Oh, so okay. We can play it on this level, or we can just mute the sound and he talks over the slides.
Okay, cool.
Okay.
Now I'm starting.
All right. Hi, everyone. My name is Peter Matrano, and I'll be presenting our paper titled Data Augmentation for Online Learning of Rope Manipulation. In this work, we propose a data augmentation method for increasing data efficiency for deformable object manipulation. Data augmentation has been used to great effect in computer vision, wherein, for example, an image classification task, we can sometimes apply random rotations or crops. And this has been shown in prior work to increase the data efficiency and generalization. But these methods are typically specific to both data type and task. And so while existing methods exist for text and images, the same cannot be said for robotics. In this work, we focus on augmenting trajectories of geometric state and action data. This includes object poses, joint configurations, voxel grids, or point clouds. We focus on short trajectories, and our method is applicable to both classification and regression problems. I'll now describe our method and then our experiments. So at a high level, we apply, we also go over the assumptions carefully in the paper, since data augmentations are typically very specific. At a high level, we apply a rigid body transformation to some of the objects in the scene. So we decompose the scene into three categories. There's the robot, the moved objects, and the environment. We frame augmentation as the following optimization problem with three terms: validity, relevance, and diversity. Validity means that the example obeys the laws of physics. Relevance means that it's similar to data you'd see when performing the target task. And diversity is maximized when the transformations are uniformly distributed. We take this abstract problem and propose a specific version for robotic manipulation, which has 6 terms. The first term expresses diversity as the distance to a uniformly randomly sampled target transformation. And the next 4 terms describe the validity and relevance of the object state. They enforce that the state remains within the workspace bounding box. They penalize invalid transformation parameters and preserve near contacts and contacts with the environment. The final term defines the validity for the robot state in action. We solve this optimization problem by splitting it into 2 parts. In the first part, we optimize the validity, relevance, and diversity of the moved object state. And in the second part, we optimize the validity of the robot state in action. I'll now go over experiments. So we start by evaluating on bimanual rope manipulation and simulation. The robot is holding the ends of the rope and is tasked with placing the middle under the hooks in the goal regions in purple. The planner here uses an imperfect model of the rope dynamics. And so in order to produce accurate plans, it learns a classifier that predicts whether the dynamics model is accurate. And we apply data augmentation to the training data for learning this classifier. If we analyze the success rates over the final 10 iterations of learning, we find that the method which uses augmentation has a success rate of about 70%, and the method without augmentation has a success rate of 48%. We also evaluated on bimanual rope manipulation in the real world. So the scene here is a mock-up of a car engine bay, and the robot has to move the rope, middle of the rope under the engine without snagging to set up for lifting the engine. Here we used CD-CPD2 to track the rope state with 2 Kinect 3D cameras. We ran 30 iterations of learning and then froze the models for evaluation. The evaluation found that without augmentation, it succeeded in 7 out of 26 trials, and with augmentation, it succeeded in 13 out of 26 trials. In summary, we propose a novel method for data augmentation for robotic manipulation. We formulate augmentation as an optimization problem, and we show that it improves performance on downstream tasks in the low data regime. Thank you.
Yeah, so any question? Yeah.
Very nice work. Well, Trish, can you say something about the failure modes with augmentation?
Can you repeat the question?
Yeah, so the question was, what are the failure modes specifically with augmentation? So one way in which things could go wrong is you could produce augmentations that are invalid or irrelevant or just not diverse enough. So this is going to be probably most likely to happen when some of our assumptions don't hold. So let's say that the rigid body transformations don't preserve internal forces for some reason. So maybe gravity has a really strong effect or something like that. And in that case, you might produce data that is not either accurate to the real task or not relevant, in which case it wouldn't help.
What I'm getting is you have 13 out of 26. Correct?
Oh, I see. I think honestly, in this case, it's just that the amount of data is still, even with augmentation, small, and the task is really difficult. So I think while the augmentation helps, in order to succeed at this task 100% of the time, you'd probably need more than just 30 trials and more than just data augmentation. You need better control, better sensing, etc.
How is the robot represented in the state action space? Is it in Cartesian space or a joint space in the optimization?
So the question is, how is the state and action of the robot represented? So the state is the joint configuration, so absolute joint positions, and the action is relative gripper position changes. So move forward 3 centimeters in some robot frame.
We also have a question on Slido.
Okay, thank you.
That's how long is the time cost of the optimization to get a transformation?
Okay, it's fairly fast because we can do it in parallel on the GPU. We use PyTorch for the optimization problem. So we can generate anywhere between 5 and 15 augmentations per second. So it's pretty trivial compared to training time or robot execution time.
Okay, thank you.
Do we have time for one more question here?
Yeah, one is fine.
So the question is, how sensitive is it to the hyperparameters and the optimization? It's not particularly sensitive. You could probably add 50% to any of the variables, and we didn't notice significant changes. The terms were chosen by basically just balancing the magnitude of the losses because they're in wildly different units.
All right, I think we should move on to the next speaker, but thank you very much.
Thank you.
So next speaker is Thomas. Thomas, are you, yeah, do you want to come by here? Well, Martina, do you want to play the video?
Yes, I'm playing it. No,
My name
wait.
is Thomas, and I'm going to
I'm
present a
restarting
paper.
it wasn't muted.
Hi, my name is Thomas, and I'm going to present our paper on learning key points from synthetic data for robotic cloth folding. Robotic cloth folding is a challenging problem due to its deformability, which results in infinite degrees of freedom. Nonetheless, complete pipelines for cloth folding have been created by leveraging the observation that it suffices to know the position of a few semantic key points or landmarks. These pipelines, although very impressive and robust, have limited potential to generalize to diverse environments, as they rely, for example, on segmentation techniques that assume a known background color distribution. In this work, we attempt to overcome these limitations by leveraging the generalization capabilities of neural networks. We train a neural network to detect towel corners and transfer this network to a real setup, which allows us to fold towels with a simple open-loop trajectory. By using procedural data generation, we can train this network without having to collect large data sets. We can also easily generate all desired variations in the dataset. Our pipeline contains 3 components: the procedural data generation, the key point detector, and the scripted fold trajectory. I will briefly introduce them in the next slides. To generate the training data for the key point detector, we create a 3D scene in Blender. We randomize the geometry and pose of the towel, as well as its material. For the towel material, we create a simple noise texture, as creating high-fidelity textures of cloth is time-consuming. The camera position is also randomized to make the network generalize to different camera poses. The major issue when training neural networks on synthetic data is the sim-to-real gap, or the decreased performance when transferring the network to the real world. To overcome this, we use domain randomization. We sample objects from the Thingy10K dataset to provide negative distractors. To introduce diverse lighting, we add high dynamic range images as environment maps. Finally, we add a random material to the surface to introduce spatial patterns. For the key point detector, we use a UNet-inspired architecture with residual connections in the bottleneck to combine spatial resolution conserving paths with a downsampling path for a larger receptive field. The network outputs a single heat map that contains all detected corners of the towel. After training on the synthetic dataset, the network achieves an average precision of 82%. We then manually define the grasp pose and the circular fold trajectory in a local frame on the towel. Once the corner locations are known, we can transform this local frame to the frame of the robot and fold the towel. To evaluate the system, we gathered 20 towels and divided them in 2 groups. Within distribution towels that have uniform textures as modeled in the synthetic data, and out of distribution towels that have unmodeled textures. The robot attempts to fold each towel under various circumstances. We change the towel's initial state, the environment lighting, and the presence of random objects in the scene. We use the grasp success rate to measure the performance of the key point detector and evaluate the complete system with a fold success rate. The system has a grasp success rate of 80% on the in-distribution towels. Grasp failures are due to wrong or incomplete key point detections, indicating that there is still a sim-to-real gap. In future work, we aim to further explore this to provide more insights and a more principled approach to procedural data generation. The difference between grasp and fold success rates are caused by limitations of an open-loop unimanual fold trajectory. In most failure cases, the corners of the towel get bent, resulting in a failed fold. For some towels, the difference in material properties causes the fold to fail. To conclude, in this paper we showed how to use procedural data generation to train a neural network to detect towel corners and use them to fold towels with an open-loop trajectory. This shows that synthetic data generation can be used to solve perception tasks for robotic cloth manipulation. You can obtain more information in the paper or by visiting our poster stands.
Any question? Yeah, I think you can ask your question here and then you'll just repeat it for the people on Zoom. Yeah.
Yeah, I have a question. So it seems that you have no texture on the cloth of the situation data, but you have some real data using this seem to get this scenario.
Yes, so the question was about the textures that were used for modeling the cloth, where the textures in simulation were very simple and not really they didn't represent real cloth. And the question is, does this cause a sim-to-real gap? Well, I think that's indeed one of the things. I'll move away from this mic. So I think that's indeed one of the main issues with the reduced performance we saw. But the point is that if you want a diverse set of real textures of cloth, well, that's very hard to create, right? So this was the reason to use a low fidelity texture, but indeed it's causing the sim-to-real gap.
We also have two questions on Slido. So the first one is, can you use traditional methods like Aries corner detection for detecting these corners?
Yeah, sure. That's a great question. I think indeed for the settings that we evaluated in this paper, you could use more traditional methods like the Harris corner method. I also quickly tried it and it did seem to work. Although we also, for example, experimented with adding some random objects in the scene. And once you start doing that, it becomes a little bit more tricky to tune things to make sure that these objects do not result in false positive corners. But yeah, with enough engineering, you could probably solve all these tasks. But the point is mainly that you can use this synthetic data also for more difficult cloth types because the methodology is not limited to rectangular shapes, for example.
Okay, thank you. Then we have, I think, the last question. That is, can the perception system be used to foreclose the loop folding?
Well, depends on the frequency of your controller. I would say the inference time for the network is rather small. So if your controller accepts control rates of 20 to 30 hertz, you could use that, I think. But then you would also have to train it on data where the manipulator is also in the scene because it would cause occlusions and stuff like that. So if you add this to the data, then you could surely use it for closed loop simulation as well. Maybe if there's still time, there was one question from the audience, but I don't know about the schedule.
Yeah, one more question.
You know, what fraction of real data do you think you would need to achieve the same performance? So say you had 100 samples of synthetic data, and then you collected, 10 very carefully, very careful samples of real data. Would that be sufficient to get the same performance?
That's an interesting question. I think sorry, yeah. So the question was, do you have an intuition on how much real-world data you would need? Like, what's the ratio between the simulated data and the real data that you would need to achieve the same performance? I think it depends on how well you choose the real-world data. Because, for example, I used well, you have like the table of our robot is like an aluminum construction. If I would take the photographs all on that table, it would probably suffice to have like maybe 50 instead of 100 samples, but then it would only work on that specific table, right? And if you want to generalize to all kinds of tables, then it becomes more tricky, and yeah, you would need more data. But I think you would need less data if you use real world data, obviously, because you don't have a sim to real gap to overcome. But on the other side, that's more expensive to obtain and to label. But you would definitely need less data here. Thanks.
All right, thank you very much. I think we should move on to the next. So we can move on to Irene video, and Irene is on Zoom. Yeah.
Hi everyone, I'm Irene Garcia Camacho, and I will present you the cloth manipulation and perception competition. Establishing well-defined benchmarks that serve to evaluate different robotic manipulations is still a pending challenge in robotics. Several initiatives have been proposed in recent years, but a benchmark is successful only when it is widely accepted and used by the community. For this reason, during the last years, several competitions in robotic manipulation have been organized as a way to drive scientific progress in the field, as they enable comparison of different approaches with equal test conditions. One of them is the robotic grasping and manipulation competition that includes 3 tracks. Nevertheless, previous competitions have mainly consisted on rigid object manipulation, leaving behind the challenges that suppose grasping and manipulation deformable objects. For this reason, we created a new competition which will be held as part of the service track of this competition at ICRA 2022, which consists on perception and manipulation tasks involving highly deformable objects such as textiles. This competition is the first proposal to bring together researchers in solving the same tasks in cloth manipulation, comparing the different solutions in equal conditions. This comparison is now quite difficult to do with published works, as they use completely different metrics and use different types of objects. Another motivation of this competition is to increase the acceptance and use of the household cloth object set, which was designed as a first step towards benchmarking cloth manipulation through the standardization of textile objects, similar to what was done with the YCB object set. This set will be distributed to the participants in order to perform the tasks of the competition and will be able to keep it later to continue working with it. This competition consists on a small set of tasks based on the current challenges in 2 important areas of research in deformable object, perception and manipulation. We selected 3 tasks that include problems that have already been tackled in literature, but that still require efforts to be considered as solved problems. The first task focuses on the main perception skills necessary for the following grasping of the textile object. It will be evaluated the ability of detecting relevant features and the selection of suitable grasping points according to the cloth configuration. Notice that this configuration is very important in manipulation, as it determines the possible grasps in order to manipulate it as desired. The other 2 tasks consist on the implementation of 2 of the most studied cloth manipulation tasks in literature. On one hand, the unfolding task consists on grasping a cloth and manipulating it until it is placed flat on the table. This task is considered successful when the cloth has been placed laying flat and is completely inside of the table. We also will evaluate the quality of the placed cloth by measuring the resulting area and computing the error. On the other hand, the folding task consists on folding the cloth 2 times once it's flat in the table. This task is considered successfully completed when the folds are performed according to the protocol and the opposing corners are together in each fold. In similar way to the previous task, here we will also evaluate the quality of the result. We selected tasks for both areas in order to allow people from both sides to have the opportunity to participate. In this way, with this competition, we are able to test separately the vision solutions, but also assess 2 common cloth manipulation tasks, which require of several manipulation skills that are also present in many other cloth manipulation tasks. We also allow to focus only on the manipulation part by easing the perception with the use of colors on the grasping points, for example. Besides, these 3 tasks together form a complete pipeline that can be executed continuously. Therefore, we offer a competition with a compromise between doing something that has been studied in literature and fosters research groups to participate, but also providing challenges with increasing complexity. We believe that the organization of this kind of competition is a great way to improve and compare state-of-the-art approaches, and that it will provide useful knowledge for the deformable object manipulation community. Thanks for listening.
Do we have any question?
Well, I think Thomas has a question, right?
Do you want to repeat that? Oh, gee.
I think Irene is not there, so I'm gonna answer. Oh, Irene is there.
Yeah, I'm here.
Oh, okay, go ahead then.
Could you please repeat the question? Because here we couldn't hear it.
No.
Me? Do you want to repeat the question?
We need to repeat it inside.
Any of you.
So basically, the question, if I understood well, it was that we are relying basically on planar and kind of planar shapes, and there are more complex shapes like t-shirts that should be taken into account. Something like this? Yeah?
Why do you include rectangular shapes, cloth items, and other measurements?
Yeah, that's the question. Irene, only why you are including only rectangular or planar shapes and not t-shirts?
Yeah. Okay, so as I said, this competition was made for distributing the household clothes set. This set is a first clothes set that only included household items that include different sizes and different shapes. But we are planning to extend this clothes set to other shapes and other items as clothing items with t-shirts, trousers. So in this set, it's not included, but it will be. Is that, does it answer?
So Martina, should we move on to the next? I think we're running a little behind.
Yep. We also have a poster session afterwards in the break. So if there is additional questions, go to the poster.
But we have one more video speaker. So Martina, do you want to?
Yeah, I'm sharing. Sorry. Okay.
We study a dynamic deformable manipulation task. We assume that the robot has already grasped the deformable object, and that the robot can accurately measure the 3D position of a single point on the object. Our benchmark task is to track a fast-moving trajectory with the measured point. The true state of a deformable object is continuous, infinite dimensional, and governed by complex dynamics. Furthermore, the system is only partially observable. We cannot measure the full continuous state from the real world, only the controls U and observations Y. We learn an input-output dynamics model from real-world data using a recurrent neural network, which has an uninterpretable hidden state, X. The recurrent network forms a discrete time dynamical system, so we can use standard nonlinear state estimation techniques to estimate a value of the uninterpretable state that is consistent with past inputs and outputs. In our protocol, we first interact with the object to build a dataset, which we then use to train the recurrent network. We estimate the recurrent network state from past inputs and outputs using an extended Kalman filter. We then use the mean of the Kalman filter belief distribution as the initial state for the dynamics rollouts in a nonlinear model predictive controller. The controller sets end effector, pitch, and yaw angles for the robot. The Kalman filter consumes inputs from the controller and measurements of a single point from a motion capture system. We test our method on a robot arm grasping a foam cylinder. This video shows the tracking performance for a circular trajectory. We also perform an ablation study where we remove the Kalman filter component. This results in an open-loop system with no opportunity to use observations to correct for modeling error in the recurrent network dynamics. The open-loop system shows degraded tracking performance. More details and the results for other trajectories are available in our paper.
Any question?
So there are no questions in the room. Martina, do we have some online? We lost just the Wi-Fi, so we don't have access.
We do have one question in the room in the back.
What's the motivation?
Everyone, can you repeat the?
Yeah. The question is, what's the motivation of this work? I think it's a great question. One of the initial motivations is trying to govern objects that are dominated by passive dynamics in sort of highly dynamical tasks. One of the initial motivations, which comes from a funding source, is manipulation in space. So if you have a very low power space actuator, so oftentimes you ship something up to the International Space Station, it has a very low actuator potential. You're manipulating maybe a cargo bag, and you have a very low actuation compared to the actual passive dynamics of the object. The test bed on Earth here is basically some task where you have these passive deformable dynamics that really dominate. So that's why we tried to make the task tracking as fast as possible. Thanks, it's a great question.
One more question? Yes.
And a follow-up. What is the motivation of using model predictive control for this task?
Yeah, what is the motivation of using model predictive control for this task? I guess my question there would be sort of as opposed to what? I mean, do you have something else in particular in mind?
Yeah, I mean that we can do something that does not require to have a receiving horizon. We can minimize some instantaneous cost instead.
Yeah, it's a good question. I think because the dynamics dominate here and because there's some significant nonlinearities in the dynamics, that's why we chose a nonlinear model predictive control architecture. There are other ways to solve this problem too. And future work, we'd like to benchmark against multiple approaches. Thanks. Yep.
How big was
Yeah, the question is, how big is the data set when we train the LSTM? Thanks for your question. We actually only needed, I think it was about 10 minutes of data. We just rolled out some sinusoidal trajectories. One of the things that we found was surprising is we actually had pretty good task generalization. So we were able to track like a rectangular trajectory pretty well. Please stop by the poster. We have some results there too. Yeah, thanks for your question.
All right, so thank you very much. I think it's time for our first break. So we'll have a break right now, and please be back by 11 o'clock for our next speaker. So right now we have a coffee and posters, I think.
Yeah, so the posters are just outside the door. The people that post the posters, please hang them up on the poster session. The posters are just outside. See you all at 11. And we need to see if we can fix the mic thing.
And Martina, do you want to share the slides?
Oh, my slides here. Yeah. So do it on Zoom. Do you have an HDMI? I have an adapter. I have an adapter. Yeah. So ideally, we could plug you in here. You join Zoom. You share your screen, and then you talk that this and the room can hear. That would be ideal.
Okay. Okay. So I have to join the Zoom.
Yeah. Otherwise, the remote participant cannot enjoy.
How many do we have remote?
It's 13 Zoom. 34.
Let me see. How do I join the Zoom? Should have been an email, right?
Email, or you can on the website if you Google the Deformable Object Workshop.
And then this. Is this one not working? I'm not sure. Hey, check. I'll turn this one off too.
That's the second one. Zoom link. Exactly.
Testing the Q&A mic in the middle of room 13C. Testing 1, 2, 1, 2.
Camera. So it's there. Okay. You can place it really.
We came here. Microphone 113C.
Testing, testing one. One, got some serious reverb.
Yeah, audio. The audio.
One. Oh. I'm hearing it from the last.
I think you have to mute one laptop.
Yeah.
I think the microphone.
Okay, that worked.
It should be. Looks like it.
Oh, yeah. I am talking into the podium. You're going to hear some reverb because the laptop is broadcasting as well.
Oh, should I turn this one off?
No, you're fine. You're fine. Yeah. Yeah, you're good? Okay.
Should I turn off?
You just hear what happened?
Yeah.
It's picking up my voice, and then it's picking up the speaker.
So I should turn
your laptop volume off.
Volume off. Okay, so like that. Wait, that. So now I'm not.
And you're still.
So it's not the volume, it's the input.
Is it this guy?
It could be either one.
Oh, I see. Wait.
Maybe just this guy.
No, it's probably. I should.
Yeah, this is broadcasting your video audio.
Okay, so wait. So I can turn off my audio here. Hold on 1 second. Stop sharing. Then I'm going to turn off.
You're perfect. You're not hearing the reverb anymore.
No, it's good.
Do they hear us? Do
Yeah.
they hear us?
Yeah.
You hear
No.
us?
Yep.
No, it's
You're
good.
plugged in right here. So
Okay, and then people in the room?
Yeah.
You can hear us all right?
It's just not a great setup, like these mics. So let me see if we can get a bit closer to you.
Oh, I see. Okay, so if I'm like this.
Yeah, it's not working. I can't turn it up like much.
That's the size.
I got it.
Yes. It's a tape.
All right, how's that? Like, sounds good? You hear me all the way out there? All right. So then, if we turn this a little.
Now, here's another option. If you want, you can.
Yeah.
Then you don't have to use that. Then
That's
you
better.
push that back. So.
Great. Okay, let's go with that. Everything okay?
Yeah, we are fixing it.
We're good.
So then
But-
just put that.
Oh, all the speakers should hear that.
I think if it works. We test it out now.
Testing. Oh, that's much better.
So.
Yes.
Yeah, I'm good.
One more question for you guys.
But do they hear me?
Yeah, so this guy still picks up with his regular microphone, right? Is the point? I brought this microphone, it's mine, to plug this into this.
Oh, yeah, do that. That's probably
Yeah, as
better.
long as you're into this laptop. This is the broadcast laptop.
All right, Maria, can you hear me all right? Martina?
Yeah, it's
Okay.
good.
Okay. And then you have my screen.
Oh, I lost the screw.
It's right there on the table, along with the two washers.
Just,
We're adding our own microphones with this laptop.
yeah, that would be wise. That's probably the best setup you can do in this type of thing.
Maybe you could help me with the laptop setup if you would be so kind. Let me plug in this guy.
It's USB.
Hey, how you doing?
Yeah.
Good.
It's a little chaotic.
Was it? No worries. Okay.
Trying to figure out the subway and everything.
Oh, yeah, how was that?
It was all right.
Oh my God.
Pretty straightforward. Just get it.
I'm gonna be back in five minutes.
Yeah.
It should be like just a couple of stops, right?
Yeah.
Okay. Good.
So let's just plug it in. I think we don't need this.
That's the pretty clicker,
Yeah,
right?
yeah.
We don't. But this is, I think this is the Yeti, right? Can you hear us, Martina?
Yeah, now it's much better.
No, we don't hear
Yeah, we
here
don't hear
anymore.
her. So I think it's like one or the other with these. I haven't hooked one of these up,
Okay,
so.
okay.
Michael, can you hear me?
Is she hearing us now? She's muted. She has to unmute herself.
I can hear you.
But now it's not coming through.
Now we don't hear her, but
So
she
go
hears
in there.
us.
So speakers.
But speaker is not the Yeti, yeah.
So we want this one?
Yeah. Martina, can you say something?
Hello.
Okay.
Okay, do you hear us?
Yeah.
Okay, yeah, okay, so you had just selected.
Okay.
So you're good and you hear us?
Yeah, I can hear you.
There's like a little delay, but.
No, but this is perfectly fine. I
Just
think
be aware there's going to be a delay, a slight delay.
with this we can work. Thank you so much for
Yeah,
for
no
that.
problem, yeah. I haven't really actually used Zoom since the pandemic's been over, you know what I mean? Like we used it and we stopped, so now it's like a quick little course. All right, so that microphone's, what I suggest though, to repeat the question. If someone comes up, repeat the question, that will benefit everyone, okay?
One more question. Is there any way to turn up the volume if we play a video and it's too silent?
Everything okay there? You have a little volume here, and then you also have volume on your PC.
Okay. So
So you
we
have,
will try this.
like,
Yeah.
see that I just turned that all the way up, so you might have to turn it down now, okay? Let me just.
Okay.
So for any video now, we just adjust with that.
Yeah.
That comes out of this laptop.
Yeah.
But for okay. All right, so for the speaker speaking there, they use their laptop and speak through this. This will be.
Or a lob. The gentleman has a lob too he's using.
Yeah, so
a lavalier.
So it's one of them.
Yeah, they need to speak into this, or the other gentleman has the lavalier on somewhere. He walked out of the room, so.
He's over there.
Yeah, so he'll come back.
And does this microphone work?
That's on, yes. Now, what I just said to repeat the question. It will help in the room all together, okay?
We did that first.
If you get people that speak this far away, it's not going to work, okay? So if you hear the question, repeat the question nice and loud in one of the microphones and then move on from there. That's what I suggest would work the best. You know, you just get people that just speak too far away from it, okay? So I think you're good then?
Yeah, thank you so much.
And listen, you have an issue or something, we're out there, we can, lunchtime, we can go over and try to work anything out that you need. Okay?
Thank you so much.
Wait, are you giving part of this talk?
No, you asked me citation.
Hey,
I have my pictures. I just put it in.
Because like one of the speakers had a student giving half the talk. I didn't know if you were doing that.
No.
Are we using the same?
Yeah.
We are.
Michael.
Yeah.
Can you make me host?
You are.
Oh, really?
One second.
Okay. Yes, now I am. Thank you.
You have control of her on this knob here.
Yeah. Okay.
You know, you have the control of whatever's coming out of here on that knob. You know what I mean? So like if you're too loud, they'll complain like they complain. You know what I mean? But whatever.
Yes.
Just so
Okay.
you know you have that knob that's control.
Yeah. Thank you so much. If it's too loud or too silent, we have this knob.
Hey, check 1, 2, 3, 4. So if they're talking back here, so you know, have them speak in.
Very close. Okay. Yeah. Thank you so much.
Like when I adjust it, just tell me if it's the right audio level.
Yeah. Right.
Is that laptop working? Okay.
Michael, maybe you just need to move a bit the webcam because now I cannot see that well the guy. Yeah, guy.
Hi, I'm Shuran. Just checking in.
Hey, nice to meet you.
Nice to meet you as well. So are we going to use my laptop?
I think it's easier if you use your own laptop. This is Ken's laptop.
Okay, great.
And then we just connected with the HDMI.
Okay, and then I will share my screen.
Yes, you joined the Zoom. The link is either on the website or in the email.
Okay.
And then you just share the screen, so the remote participant also see it. And it's, yeah, we will see it now with Ken. You test it.
Okay, okay.
Thank you.
Hey Daniel, how you doing? The workshop is going well. Just that did you just come in? Yeah, I go. No, right. That's true because this was the only room that didn't have a projector set up. This room did, and all the other did. This was the only one that, like, we got them here in time, but. So, Martina?
Yeah.
So I think maybe we should switch the screen sharing to Professor.
Yeah. Stop sharing. Yep.
Oh, this one? Okay. Okay.
Yeah. Yeah, and then if
do you want to?
If Ken could share, then
Oh, yeah, I'll share.
yeah, then we'll
Start now or in a few minutes?
Well, I can.
You can start sharing, and we wait a few more minutes.
Because I'm just going to check my schedule.
Yes, yes.
Okay. But do you mind if I give the introduction to you? Or
We can still wait a few minutes. Like people are still outside. Like
Yeah, wait 2 minutes.
all right, okay. I want to listen to the talk and not be distracted by people coming in.
What would you say?
Yeah. I want to listen to the talk and not distracted by the people coming in.
Yeah.
Let's just give them a few more minutes.
All right. I see people coming in. Yeah.
We were late for the first part. We can wait a bit.
Yeah. We were late for the first part, so we can wait a bit.
And it's also, there's a lot of people in the poster session, like talking. So, is there a way you can just like close the door or get them to, I don't know.
Let's wait 3 more minutes.
Yeah.
It's going to be fine. The workshop is never completely on time.
Yeah.
I've never seen this happen. So.
Hi.
Microphone.
Yeah,
I can't hear you, and I have my hearing aid.
Well, they fixed it.
Good, good.
They say they did.
Huh?
They say they fixed it. Can you hear me now?
I hear
Okay.
you.
Okay.
Yes, yes.
Good.
But when they talk there, I can't hear anything.
Yeah, they messed.
And I'm still learning.
Oh.
She's right.
I mean, if the other rooms are closing the door, maybe we should do something similar, but I don't know.
Let me just inform them that we are starting up in 1 minute.
Yeah,
They come back in.
good. But I also don't know if it makes noise
If not,
when people.
close
open.
it.
Yeah.
Okay, so now I'll share screen. Make sure this works. So that's I hear an echo.
Yeah, which
I have mine.
you are muted. No, yeah, you want to be muted because the sound goes over this one.
Okay, that's got. Why don't we? Let's see. Try it again.
Yeah.
Share screen. Okay. So flash is good. All right. Is there mute? Sounds good. And Martina, can you hear us?
There is an echo.
Yeah, there's an echo.
Maybe if you can't beat that. Off the volume on those guys. Yeah, mute that. There you go. All right, now that should help.
It's
still got an echo?
I'm hearing it from here. Is it the speakers of the laptop?
That should be off. Okay.
Oh.
Is that better?
Yeah, now it seems fine.
Oh, okay. We solved the problem.
Okay, nice.
All right, we got it. It's working?
Yep.
Yes.
Amazing.
Martina, confirm?
Yeah, it's working. Thank you.
Perfect. Should we just get rid of this guy?
Yeah.
Just
All right.
All right. So, may I introduce?
Please.
Oh. Hello, everyone. Hello, everyone. So it's my great pleasure to introduce our next speaker for this workshop, Ken Goldberg. So Ken is the William S. Boyd Distinguished Chair in Engineering at UC Berkeley and an award-winning roboticist, filmmaker, artist, popular public speaker on AI and robotics. Ken trained the next generation of researchers and entrepreneurs in his research lab at UC Berkeley. He's published over 300 papers, 3 books, and holds 9 US patents. His artwork has been featured in 70 art exhibits, including the 2000 Whitney Biennial. He's a pioneer in technology and artistic visual expression, bridging the two cultures of art and science. With unique skills in communication and creative problem-solving, invention, and thinking on the edge, Ken has presented over 600 invited lectures at events around the world, including this one here. And I'm very happy and honored that I got to be one of his many PhD students during my PhD studies. So please take it away for you.
All right. Thank you so much. Appreciate that, Daniel. It's an honor to be here, and I want to. This topic is something that my group and I have been thinking about for the last 5 years. We're really interested in it, and I'm so glad that this workshop is having a new iteration. So we've been thinking about this in 3 components. One is one-dimensional deformable objects like strings and cables, 2-dimensional deformable objects like fabrics and garments, and 3-dimensional deformable objects like solids and bags. Now, I just want to briefly acknowledge that this is my group. It's all this work is really credited to them. They deserve the credit. And here's a little cartoon of our lab with some of our actual robots in it. More information is on automation.berkeley.edu. So what I want to talk about today is something that we've been exploring in just this past year, and will be presented at the conference. And what we're particularly looking at is an approach to to deformable manipulation that we're calling real to sim to real. So I'm going to go back a little bit in time and start with some earlier work and then come up to that. I'm also going to talk a little bit about this idea of labels from ultraviolet light, which we're very excited about, and I think is relevant to almost all the work that's going on in that I've been hearing about in the workshop so far. I'm very excited about. And this is a general technique, and I want to make sure I have time for that at the end. Okay, so going from the beginning, our first foray into deformable objects was learning how to manipulate cables dynamically to do things like this. Sorry? Oh, I thought I heard something. So this was inspired a bit by the Raiders of the Lost Ark TV or movie series, and how you can manipulate something like a bullwhip. And so we wanted to see if we could get a robot to be able to do something analogous. And here's the idea. So we have a fixed, actually it was inspired a bit by vacuuming in the lab. And we were trying to get the cable loose because it was snagged over a chair. So you know how you do this? You kind of fling it and it goes over the chair. So that's the idea here. And we looked around for related work. There is some very interesting work in manipulating flexible objects like cables, and also, of course, throwing objects, tossing by. And we considered here 3 tasks. We looked at vaulting, which is just to go over an obstacle, knocking, which is to knock something off of an obstacle, and the third one is weaving, to weave the cable in and out of different obstacles. And the assumption is, again, that the one end of the cable is fixed, so it's plugged into a wall, for example. And we also wanted we wanted a method that would be general, that we could generalize to different cable types. So we looked at these ones. The idea, and this was reported in the paper last year, is there's an algorithm. First, something that we call INDI, which is a acronym for Iterative Training for Dynamic Cable Manipulation, and I'll mention that in a minute. And then GOMP, which is a method for optimizing the motion trajectory of the arm to minimize jerk. So the parameter learning here was based, in this case, for learning a single key point for the ballistic trajectory of the arm. So we wanted to learn the apex point where the arm the midpoint of it should pass through, that would cause the cable to do what we want. So again, the assumption is that the endpoint is fixed, and that we also are holding on to the cable with the gripper. One key part of this was being able to do resets. And I think this is an interesting question in general for this in terms of deformable objects, is how can we reliably reset things? It's very difficult in general, but with cables, we found that we actually could do that. And the idea was to essentially pull the cable fully taut and then drape it down onto the ground. And if you see here on the right, this is actually an overlay of 20 different cable iterations after the reset. You can see you can almost not tell the difference. So the reset was very effective in this case. Again, for one-dimensional cable, it's not too hard. But thinking about that is very helpful, because you want to be able to get back to an initial state so that you can continue, you can do exploration. The pipeline for learning this was that we did a deep network, a ResNet, to essentially learn these 3, the configuration of the apex point. And then once we had that, we ran it through the trajectory solver, the GOMP solver, to be able to compute a time optimal trajectory for the arm that would minimize the jerk. And then we execute that. So here's the vaulting trajectory in real time. Here's the knocking trajectory, a success. And then here's a weaving trajectory. Good. Now, it doesn't always work, and I'm sorry I don't have bloopers. I try to always show those, but it doesn't always work. There's some variability, but it worked actually surprisingly a large fraction of the time. But it's fairly repeatable. Again, if you can do the reset to get you to the same initial starting point, then the motion is fairly deterministic and repeatable. Now, in contrast, here's a problem where the motion is extremely non-repeatable. And this is a problem that we started studying this year that we call planar robot casting. And this is work by Raven and Vincent and Lawrence, who are here, and they'll be presenting this. Here's the idea: is that there's many scenarios where you want to be able to control the motion of an object, but you can essentially only launch the object, and then you don't have control after that. So in cases like this where there's friction, the shuffleboard or bowling or anything like that, then you have to. The problem is very difficult to model, and there is essentially this fundamental sim to real gap. So and this is what we've been talking about today in several of the presentations, the sim to real gap, because we can simulate these things in a somewhat realistic manner. They look good, but they're not, they don't then translate into physical reality. So how can you get around that? So there's one technique is domain randomization. As everyone knows, you insert some noise into the simulator and training and then try it. That can be helpful in many cases. Domain adaptation is another way of doing this, where there's some interleaving between the sim and the real rollouts. But the idea that we're particularly have been thinking about is this, where we essentially train the simulator, try to learn the parameters for the simulator to match the physical system that we're working with. So we collect some real rollouts, then train the simulator, and then use the simulator to generate lots of training examples, and then learn a policy. So this is the real to sim part. Now, some of you may be thinking, oh, this is just system identification. It's well known, it's a solved problem. You can just go to a textbook. Well, yes, if you're talking about a lumped parameter system like a robot arm, where all you're trying to do is identify the masses, then it is possible to excite the system in a very specific way to learn what the masses might be, or the lengths. But in a general system like this, where you don't have a good model, then it's actually extremely difficult to identify what are the system parameters for the simulator. Because you have things like torsional variables and friction and static and dynamic friction, very hard to estimate what those should be. So in this case, you're seeing that we actually, in this particular instance, are able to match fairly reasonably. And the technique that we're using is differential evolution. So this is a technique that was developed in other domains for tuning simulators. And so what we do is we start by collecting a fairly small amount of data of examples of just pulling on the cable, basically casting, and then we try to look at those trajectories and run them through the simulator, and then tweak the simulator essentially until it hopefully converges. Now this was interesting and surprising to us. We tried a number of different methods, but this one, differential evolution, worked surprisingly well in this case. And then we were able to generate, once we have the simulator tuned up, we could generate lots and lots of examples, like 40 times more examples. Then we use that to do policy training. And the, okay, yeah. All right, so the policy training. So here we're comparing some different methods. The first is cast and pull. And I should mention that one way you might say that we can achieve this, or solve this problem, is just to essentially cast as far out as possible in the direction of the desired target and then pull it back to the target. But this doesn't work very well. The median error, and this is as a function of the length of the cable, is fairly large at 61%. Gaussian process model does better, but the policy is trained with this real to sim to real here does better. So this is if we use only the real data, we get to about 15% error. And then if we use the simulated data only, we get a little bit better. But if we combine the two, the real data and the simulated data together, we get the best performance that we're able to achieve. And we believe that there's a certain amount of aleatory uncertainty that remains. In other words, there's a certain amount of error that is going to be inevitable just due to the nature of this problem and the frictional interactions, which are very difficult to control or model. We also tried this with different cables. So here's the first one. And it's a fairly thin cable. This is the second one where the cable is a little bit thicker and we get a little bit worse performance. And then this is the third one where the thickest cable And again, the performance degrades a little bit there as well. All right, now here's an example of this is a successful target. Simeon is acknowledging the success here. And so the idea being that we have a camera overhead, we toss a coin into the workspace, and then we have the robot try to hit that trajectory. By the way, the one thing that's also very nice about this domain is that you can do unsupervised data collection. The robot can just be left alone, and you have a camera overhead just tracking the motions. Just for this is the blooper I promised you. That's showing it doesn't always work. All right, so this is I do not want to claim in any way that we can do this perfectly anytime soon. We can characterize a lot of the error, again, because the nice thing about the unsupervised data collection, we can model and characterize the error for many different targets. And by the way, the one thing to note is that the bold area in the inner circle is the reachable workspace of the arm, and then the outer annulus is the points that are outside the reachable workspace. So that's where casting is particularly nice. So this is with the different cables, and we can characterize where the errors form. And we see that there are certain target areas, like certain on the fringe, on the periphery, that are more difficult to control than on the center. Okay, now I want to switch over to fabric and smoothing. And this work goes back a number of years. And I want to also acknowledge Daniel did our initial work in this area. This is also with Soshi and Navid and Katsu who were at Honda. And the idea here is we started with the goal of bed making. We wanted to be able to make beds. And so, but we started exploring this in the context of using our Da Vinci robot, surgical robot, to do fabric manipulation. And the goal here, the very first goal, is to just maximize the coverage. So again, remember we were trying to make a bed, but in actually many other applications like folding, you want to, first of all, lay things out as smoothly as possible, which is to essentially maximize the coverage of a crumpled piece of fabric. So Daniel very heroically developed a fabric simulator on his own using a spring and mass model here, and I'll show you a little picture of the performance. This is a finite element model. Let me see here. Here we go. That Daniel developed and put out open source with a 25 by 25 grid. And you can see that actually you get a fairly realistic appearance of the fabric. But what that also taught us, there's so many interesting parameters and nuances, even in terms of how many grid points you should use, how you deal with self-collisions, how many iterations do you do with the integration? I mean, there's a lot of parameters. It's very difficult to do this. This was actually fairly reasonable. I would have to say, I think it was very useful for us as an initial start. And Daniel used that to develop an algorithmic supervisor that would know where the state of the fabric was and then provide points. Basically, the key idea here is to find the key point to pick the fabric and then a direction to pull the fabric to achieve higher coverage, to increase the coverage. And so we ran these experiments with a dagger using demonstrations, using a small number of demonstrations from an algorithmic supervisor, essentially, where we knew we had basically inserted the demonstration of where the pick point and pull direction should be. And then we compared it to some other baselines, like just pulling in the orthogonal direction to wrinkles that we could detect, or pulling to reduce the highest point of the fabric. And the dagger model did better than those two baselines. The next thing we tried was something called visual foresight. That was this was done by Ryan Hawk in the lab. This was the idea here was to actually model the effect of different actions, and then try to predict the effect of, let's say, multiple actions out. What would be the state of the fabric, and try and basically choose a sequence of actions that would get us closer to desired final state. In other words, maximizing coverage in this case. And the nice thing here is that you can just take random motions, random pull operations on a piece of fabric to essentially learn it what it's basically trying to predict is what will happen when you apply an action to a crumpled fabric, piece of fabric. And the predictions actually we learned to be able to do that fairly well. Again, this is all in sim. And then once you have that predictor, you can essentially use it in a optimization loop to find the sequence of actions that will get you closer to the final state. So this is the, as was mentioned in the earlier talk, model predictive control. We applied it here, where we have we are constantly updating and relearning reapplying the learned predictor to determine what should be the next action. And there are 3 tiers of difficulty here. Again, this is something I think we could also discuss as a group, that that there are many cases for deformable objects, and so we found it was helpful to divide into sort of a tier 1, fairly easy, tier 2, which is more complicated, and tier 3, which is very difficult. Okay, so I'm rushing through all these because I want to get through this, but I'm looking forward to discussion on all these points later today. Another aspect that I want to mention that Ryan used that has been effective for us is using depth sensing for fabric. Because as everyone knows, works with fabric, it's very difficult to determine state from the 2D images, from RGB images. But we had a depth sensor, and that gives us another signal, another channel that can be very helpful. The next thing we tried with fabric was learning key points, and this is Adi Ganapathi's work. Along with a number of others. The idea here is to learn key points in fabric from, again, many examples, and we'll come back to this. But then once we have that, once we identify key points, then the idea is we can show one folding demonstration on a canonical example with a garment, and then apply that to new garments, subsequent garments in different configurations, because it just wants to find the associated key point and then do the associated folding moves. So again, here's a demonstration action. If you look at the upper left, is to grab at the sleeve and move that fabric, fold that across the center line. And then the nice thing is, once you learn that, then you can apply that for different fabric, different garments in different orientations, as you can see there. And the same would work for pieces of square fabric. And okay, so now I'm going to move on to fabric flinging. How much time do I have?
As much as you need.
Very nice. No, I'll end on time here. Flingbot. So hopefully everyone knows this terrific work by Ha and San. This is a real beautiful piece of research where they realized that by grasping 2 corners of a piece of fabric and then lofting the motion up with the fabric up with 2 robot arms, essentially a new primitive that they call flinging. This is very effective for doing smoothing, and it's actually also very, very much of a inspired, I think, by human motions. When we're folding laundry or things, we do this as well, using essentially the air as sort of an extra manipulator. So they published a beautiful paper on this. It was in Coral last year, and I remember one of the discussions that came up, and the questions afterward was, well, do you really need 2 arms? And so there's a debate about that sort of came up, and someone who was in the audience said, well, I was I had a baby, and I had learned how to fold laundry with 1 arm. I had to, because I had the baby in the other arm. So then we started thinking, well, could we learn how to do this with a robot? And so that's the origin of the learning to fling with the single arm paper that Lawrence Chen and Raven Huang worked on. And so I'm not going to have time to go into full detail on this. There's a fair amount of prior work on trying to do RL for this problem, but we wanted to look at it from this perspective of training just a single trajectory motion, the fling, if you will. And so we were able to break this down into a 7-parameter trajectory. This is on the side view, looking at the robot arm. This motion here is parameterized by some key points and velocities. And so then the trick was to try and apply to learn combinations of these parameters. So each one of those is a fling motion. And then you apply the multi-arm bandit approach. So each one of those fling motions is a bandit, if you will, and then you're applying it. And each time you do that, you get a payoff, which is the amount of coverage that the garment achieves. So we looked at a range of garments like these, as you can see here, and the idea is that these are the results of after learning the best bandit motion. Now again, this is a case like the planar robot casting where there's quite a bit of non-determinism or aleatory uncertainty. So you're never going to be able to do this perfectly. But the idea is, can we find motions, fling motions that will do better on average than others in terms of coverage, final coverage. You can see that these actually do fairly deep reasonably. We actually had a little competition in the lab, and humans were anywhere from, the humans, at least the grad students in the lab, were anywhere from like 78 to 88 or so in being able to achieve coverage. So it's a hard problem. The details on the paper here are actually under submission for ICRA, but we can use a cross-entropy method and a combination of that plus Bayesian optimization to further tune. And here's just a visual of this motion. So the idea is to first pick it up and then shake it here to basically shake out wrinkles, and then a little more shaking to shake out wrinkles, and then here's the fling motion. To drop it down onto the surface. I'll just show you one more of those real quick. This is a reset, if you will, right? So again, this is self-supervised. There's a camera overhead and in front, and it's trying to maximize coverage. All right. The last result I'll mention is another paper under review right now, which is learning to fold garments with one arm. This was an interesting experiment because we used a robot setup that we did not have access to. This robot was entirely in a Google warehouse, and Google gave us access to controlling the arm, but we never got to even see it. So this is a good example of research that can be done during COVID-19, right? You don't have to go get access to a remote environment, but you can perform experiments repeatedly. And so I won't say more about this because it's still under review, but this is, you can find Brian if you want to learn more about it. It's a very exciting idea that you can do these experiments without being there and present. All right, so the last thing I want to mention is this idea of learning labels or key points in a very efficient way. And this is joint work with Brijan and Justin, who are in the lab. And they came up with the title, All You Need Is Love. So love is, in this case, labels from ultraviolet. And the clever idea here is to essentially, well, let me say what we're trying to do is to be able to segment or identify key points on, in this case, could be rigid objects, but primarily on deformable objects where it's very difficult to obtain labeled examples. So you can either do this in simulation, as we've heard this morning. One way is to simulate the materials where you have ground truth, you know where things are, and then you can generate images, realistic images of these, and then you try and essentially train it with a lot of these examples. In other words, the labels are here indicated in red on the left. On the other option is to take real images from the real world and then label them with humans labeling every object in the scene. And that's obviously extremely time consuming. So here's the new idea. Labeling them with ultraviolet is just simply to paint the material and with an ultraviolet dye in such a way that you can turn with standard lighting, you don't see the dye at all, it's invisible. And then when you turn on the ultraviolet, the dye jumps out and you have very clear, essentially, you see where these key points are, and then those provide your labels. So as you see here, the yellow cloth execution, sorry, I should say, once you've done the training with all these examples, then you don't need the dye at all, and you don't need the ultraviolet light at all. You just then, from that point on, you hopefully have learned how to find these key points in raw images. So the idea here is to, again, combine the ultraviolet paint with the ultraviolet lighting to come up with these pairs of images in real, if you will, and then images that are labeled. And they went out and found out that there's a lot of different kinds of paints, ultraviolet paints out there. Some of them are visible in real light, so that's actually not so good because then they mess up your ability. You don't want to use paint in the subsequent operations. So you want something that's transparent to normal light, invisible in normal light, but very highly visible in ultraviolet light. So again, so what you see here is the standard image on the left of a piece of fabric, and on the right, when you turn the UV on, you see that the corners jump out. Similarly, another thing that's hard is a piece of cable or rope. Very hard to track, as we all know. We're trying to do that, but when you turn the ultraviolet on, it pops out. And it's very easy to identify in the image on the right. And the last one is we're trying to find needles in surgical applications, which is very difficult. So again, by actually activating the ultraviolet, we're able to do so. What you're seeing on the right hand here is that the UV labels, which are very easy to extract just by color threshold, they are very, very high quality. So they compare very well with what humans would do. And as you're going to see, sometimes even better than humans, because humans are prone to error. So again, here on the left, you see something, and then that's how it looks. This is actually after the training. Now it's labeled the images because it's learned how to do that. So in the lower, so it's remarkably good at finding corners in this case. Here's a case where, again, after training, in this case, we're not using any UV. I know the coloring looks a little bit like it's UV, but there's no UV paint or light at all anymore. We just now take an image like you see on the left, and that's what pops out on the right. So the network is very, very good at learning this after it's seen sufficient number of examples. And then here's the case of for the needles. As you can see, the needle is very hard to see on the left images, but that's what pops out on the right out of the network, not out of the UV. All right, so I want to say this is very exciting. It's more accurate than humans because in some of these cases, as you can see here at the far right, it's not at all clear where to label the corners in that little blob of fabric, right? But the UV shows it very clearly. And it's much faster than human labeling. So when we try to basically just do a sample of these, it's like 2,500 times faster. So you can just, and then again, unsupervised manner, you can just have the robot just moving things around, and you can turn the light on and off, turn on and off, get these pairs, generate thousands of pairs, and then use that to train your system. So we're very excited about this work. You can ask us about it, or it's linked on our lab webpage. But the nice thing is we happen to provide all the code if you need it, and the information about what dyes and what lights we use. The whole thing costs like $200, so it's very easy to recreate. So we're really happy to share that with others, and pretty excited about it for exactly this domain of manipulating deformable objects. Okay, so that's all I have. Thank you.
So did anyone have any question? And the microphone should be working. So if you can just walk up to the microphone and ask the question, it'll be easy for everyone to hear.
Okay.
Yeah, so if you have questions, just line up on the microphone.
You need to get very close to it.
Oh, yeah.
Hello, can you hear me? Okay. Hi, thank you for the great talk. I have a question on the fabric flinging project. So obviously actually, like the type and the mass of the cloth will affect the type of motion that you need. I wonder if the current system can handle it, or like if there's a way of generalizing to different types of fabrics. Thank you.
Okay, great. So it's an excellent question. So the type and the material and the weight of the fabric is going to affect on the flinging motion. The flinging motion that would be more successful than others. And you're absolutely right. So one thing I will say is that this method is meant to essentially quickly learn a new garment. So you'll give it a garment, it'll start experimenting, and then it's going to learn a trajectory for that garment. Now, in terms of trying to generalize to reduce the number of samples that are needed for the new garment, right? You want to be able to learn, because you've learned a bunch of garments in the past. Here's a new garment. Maybe you can categorize it, right? It's in the same, it's a t-shirt, right? And it has similarities. So can you use that to bootstrap the learning? And it's a great question. We have done limited work on being able to generalize in that way. The one thing that and this is something we do plan to do. One of the things that I think is really important that we're starting to understand is that more recently that the fabrics that are very heavy and don't basically that defeat the air current, right, require a very different kind of treatment. And it's actually very hard to get high coverage from them. There's let's see, actually, Lawrence, are you here? Lawrence is in the back. Lawrence, do you want to answer that question?
Yeah, so the way that we do is basically by categorizing similar garments during the training. So when we get the new garment, it's a t-shirt. We'll use our class data set from the t-shirt. And then from our class data set on t-shirts, we know at this point what kind of actions are good. And then we'll find them first and then find some good actions.
Okay, that's a better answer than what I was trying to get. But so you take that, you classify it, then you have those set of actions and use those for the bandit method. And so you have a starting set of priors that are actually hopefully will be better than average than if you started at scratch. Great, thank you. Thanks, Lawrence. Lawrence, you might want everybody who's involved in this might want to be ready for the answer to these questions. Yes.
I guess the holy grail for the deformables in the LUV context would be to label them densely. Do you think there is a chance that it could be done?
Sorry, Professor Goldberg, could you repeat the question?
Okay, the holy grail in the UV ultraviolet labeling would be to get a dense labeling of the whole state of the
yeah, for deformables.
Yes, that's tricky. Well, I mean, I guess that's somewhat true with the cable, right? That's a dense model, right? We can track the whole piece of the cable. I'm a little worried that if you painted the whole fabric piece, for example, then I'm not sure that the holy grail is to be able to just find all of the fabric, because that's not that hard. But what you want to do is find key points. Like, let's say we wanted to find wrinkles, right? But that's hard because the wrinkle then would have to, that would be hard to paint that appropriately, right? Because the wrinkle would be created on the fly. But key points like corners, or if you're doing folding of garments, you might label things like buttons and corners of sort of features on the fabric. That could be, you could do that very easily with the UV. So it's a good question though if you want to get a fully dense model, dense sample. And I don't know. I mean, obviously the P. Florence technique of learning dense object descriptors might be useful there. I just don't know how that would work with ultraviolet, but maybe there's a way to do that. Okay, thank you.
Actually, I want to make sure that we get at least one of the Zoom questions, just because this is really a hybrid workshop. So may I just ask one question from Zoom?
Okay.
It's from Jihong Zhu and says, great work. I was wondering, in the real to sim to real work, in real to sim, how much data do you need to train a simulator? And if the data is able to generate a model reasonably well, can you design a controller based on that model? And so, if so, what additional benefit does the sim to real bring to the task?
Good. Okay, Lawrence, come back. Come on up here for a second, all right? Raven, Lawrence, all right, because they're asking about how much data is needed. So in particular, we found that if we just used the amount of real data that we collected, we're able to, do you guys have the numbers offhand? Go ahead, Lawrence.
25 real trajectories in the simulator.
25 real trajectories for tuning the simulator, but if we just used those 25 trajectories to learn policy, that was not sufficient. The quality was much poorer than if we were able to tune the simulator, then generate simulated examples, and then use the combination of the real and the simulated demonstrations to tune the policy. Good. All right. Thank you. Yes.
Okay. Thanks for presenting your great job.
And also, I have a question about labeling from UV light.
Yes.
So why you use UV light, for example, for object detection of cable? Why not use it only color of the cable, and then use it as labeling?
Oh, okay, good. So a lot of times, so it's asking, why not just paint the cable, right? And in fact, or the needle, right? Which is what. So in fact, I'm sorry I didn't make that more clear. In practice, after learning, we want to be able to do this under situations where the cable or the rope or the needle are not painted, right? So, because that's very common in real scenarios, right? You often don't get the luxury of a very high contrast material that can pop out. So that's why you're doing this. So in needles, for example, you can't paint surgical needles. You have to just take them because that would make them inoperable you couldn't use them on humans, right? You have to leave them in their natural state, which has a lot of specularities, right, because of the metallic materials. So the same is true for cables too, because you may get cables that, like surgical thread, we want to be able to track that, but it's going to be in a color that's very hard to distinguish from the background. Okay, so what we do is we essentially get what you're asking, say we get that high color contrast when we're training. That's what we get from from turning on and off the UV. But then we hope the idea is to move away from that. So then you don't rely on that color contrast anymore once you've trained the network. That's the key insight.
Yeah. So what I understand that you are saying, if we depend on using color that we want to use it, then maybe we are not able to paint it, for example. But what I'm saying, during the training, why not using the painting and then use the...
Let's take this offline because I think you're misunderstanding the key idea.
Yeah.
It's that we use the coloring only to train, and then you take the coloring away.
Yes.
So you don't need the coloring to do the perception.
Exactly, yeah.
Right. Well, let's talk right afterward.
Okay, thank you. And also,
there's a number of people waiting behind you.
Second question: How large was your training set? That's it.
How long was it?
For labeling using UV light. Yeah.
Oh, the training set. Let's see, guys, are you here? Where are they? All right, we will answer that question offline. I don't have the numbers.
Maybe just one more question, just because we're going a little over time, but maybe the last question. Yeah.
Oh, okay. Okay. Yeah.
Okay. Well, thanks for the great talk. Just a quick question on fabric smoothing. What does the distribution of picking points look like? Is it just mostly the corners, or what happens if you limit it to just the corners in like the general case?
Daniel, you can answer that one. Okay. So the question is, in the fabric smoothing, what if you just you limit yourself to picking only at corners? How does that help you?
Yeah, so in general, because when we're doing something like, say, learning from demonstration or learning from some expert policy, because in cloth smoothing and folding, manipulating the key points like corners is fundamental to the task. Like if you just do that, like that seems to be the most reliable way. So it makes sense to, for example, make sure that the demonstrator does like manipulation on corners, or if you're trying to learn from a large offline data set, maybe bias the data collection towards those key points. Like that's one of the problem-specific assumptions that you can make to get further gains instead of like taking an off-the-shelf method and without any modification. That's my take on this.
Great. Okay.
This meeting is being recorded.
Oh, I guess we're done. All right. So thanks, everyone. And I'll turn it over to the next speaker.
So before you leave, maybe you can just point out the students again, so we can hunt them down for more questions.
Hunt them down. Yeah, stand up, you guys. Stand up. Ryan's here. Lawrence, you got to stand up. These guys are being shy. All right, good. There's Vincent, Justin. There's actually 14 students from the lab here at various, but they're not all here for some reason. But if you find me, I'll be happy to direct you to them. So thank you guys. Appreciate it.
Is the speaker in person?
Nope.
Virtual?
Yep.
Oh, okay.
We're gonna continue with another remote speaker.
we just connect the setup again.
Everything good?
Okay.
Can you hear me?
Can you repeat it?
Can you hear me?
I'm trying to turn off the volume a bit. It's a bit silent.
How about now? Can you hear me?
Yeah, I think now it's okay.
Okay, can you see my slides? Just one slide?
Yes.
Yeah, we see the slides.
Okay, fantastic. Should I leave the active speaker view on, or do you want me to remove this? This window, should I move it?
Oh,
Should I leave it on?
it's not visible, so you can keep it.
We don't see it here.
Yeah.
So I think it's fine. But, but let me first introduce you, please. So it's our next remote speaker is Andrea Cherubini, and he received a master in mechanical engineering from Sapienza University of Rome in 2001, the master in control from the University of Sheffield, UK in 2003, and a PhD in control from Sapienza 2008. From 2008 to 2011, he was postdoc at INRIA Rennes, France, and since 2011, an associate professor, and 2021, now a full professor at the University of Montpellier, France, where he leads the IDH, Interactive Digital Human Group, and is in charge of the robotic master. And I personally had the pleasure to have him in my defense committee, which I was very happy about. And yeah, take it away.
Thank you very much, Michael. Thanks also Martina and Daniel for inviting me. I'm very sorry not to attend in person. It was quite hard for me this year for attending ICRA. So I'm going to speak about vision-based manipulation of soft objects. So what I call see and shape, and I'm going to show you some results we had on 3 different use cases, so to say. The first one is deforming via contacts with the environment, as in this photo you see, where a person is routing a cable on some contacts on a wall. The second is shaping an object while holding it with either one or both hands. And the third use case is molding plastic materials. So I'm going to present the 3 of these, starting from the first one, which will be quite short. Deforming via contacts with the environment. So this work was realized by Jiong Zhu during his PhD. He's also attending, so I say hi to him. And basically, the purpose was to reproduce cable routing with our dual arm robot. So for this, we had to set up the robot in such a way that it was possible to have 2 specialized end effectors, and one for holding the cable and the other one for moving it. And here the contributions of the work, which was published in IEEE RAL, was to design what Jiong called a contact mobility index, which is a metric determining whether the cable is mobile and to what extent. And this mobility index is used to trigger the 2 phases of the manipulation, which are pulling and turning the cable around contacts, as you can see in the video. So I would call it a hybrid planning and vision-based strategy, where the planning is used to move among contacts. So the robot has a model of the contacts, but it's actually being controlled in real time according to what it sees. And in particular, when it sees the contact, it is capable of estimating this index and determining the next action to do. I hope you hear me well and all is good. So the robot you see is our dual-arm robot platform Bazaar, which has been designed and assembled in our lab using off-the-shelf, I would say, robots. And you will see it a lot in today's videos because it's the platform we use in most of our work. And of course, we validated this framework in various scenarios, which are shown here. So let me now move to the next topic, which is shaping while holding. So this was also started by Huang during his PhD, and then followed up by a current PhD student, Celia Sagur, who is obtaining nice results also in this context. I will give a short reminder of what is vision-based control, for those of you who are not familiar with it. So assume we want to control this robot via some velocity in order to move its camera so that it can see the photo that you see here, the current image, in the same way as a desired reference image. So this is a classic control problem, only instantiated for the specific sensor and state space, which is camera and image space. So to do this, so to generate the proper camera velocities of a visible point, for example, you have to determine which is the reference, the target point you want to see, which is the starred coordinates of a pixel in these equations, and then you can just drive the error between the current and the desired pixel using what is called an interaction matrix, which is in a nutshell the model which relates the velocity of the robot with the motion of the pixel. So to minimize the error, the two norm of the error, one should invert the interaction matrix and multiply it by the error. So this is I would say, academic video of the kind of behavior you would get if you consider 4 pixels, as in this video, and the robot is moving in order to see them in such a way. And this framework has been very popular lately. It's also called visual servoing. So if we go back to the equation, we have 2 big issues here when we attempt to apply to soft objects. So the first one is that the task is very highly dimensional, because the soft object has many features, possibly even infinite features. So you cannot just rely on 2 as in this example, and very quickly this leads to an underactuated problem, since our robots often have 6 or 12 degrees of freedom. And the second big problem is that if we don't have a mechanical model of the object, as in is often the case when we do manipulation of soft objects, if we don't have a mechanical model, then we cannot know the values of the matrix L and use it in our control law. So to address these 2 problems, we have reduced the task dimension using the most simple, I would say, machine learning technique, which is principal component analysis, applied on the contour of the object. And to estimate the interaction model, we have designed an observer which runs online and is updated on a short window by relying on a linear model. And basically, using this linear model, we update continuously the relationship between the robot movements and the shape of the object. The results are shown in this video, which was the result of a very fruitful collaboration with David Navarro Larcon, who is also online. So first, well, these are basics about the image processing. We need to extract a contour of the object. And in the following video, you will see in red the target contour and in blue the current contour. So here, the robot has a preliminary phase where it moves the cable around to get a first estimate of the matrix, the interaction matrix, and then it keeps on applying the visual servoing law, so inverting the interaction matrix to control the shape of the object. And the principal component analysis is run on the contour points. You can also, of course, apply it for rigid objects, where it will converge more quickly. And in other situations where the object should both change pose and also change shape. So it's a more complex problem. Of course, we also had fails, which we show here, which are often related, they can be related to various issues, which we're trying to deal now with the thesis of Celia, but I think one of the main ones is that our object is not totally observable. So the natural follow-up to this, where we were working with planar objects and just using one arm in most cases, was to move over to solid objects and dual arm. So we want to control the shape in space, and we have some first results with the work of Celia. So to control a dual arm robot, we use a cooperative task representation, which is a particular type of controller where we control the absolute and the relative task. Then the rest is similar for now, in the sense that we are sampling the contour from a depth image and using principal component analysis to compress it in a dimension which is usable in the visual servo and control law. And on the right here, on the top right, you can see the two frames, the absolute and relative frames. So we are quite optimistic that this cooperative task framework is very useful for manipulating and shaping soft objects, because in a nutshell, the absolute task consists in controlling the pose of the object in 3D, and the relative task will mainly drive the features to give the right shape. In fact, here with rigid objects, we have mostly changes in the absolute task. This is a fancy object, a plastic glove. One thing we still have, an issue which maybe can raise questions afterwards, is that we're still only observing one side of the object, because we're working with a perspective camera, even if it's a depth image. And the future will consist in having an estimator, online estimator for the occluded side of the object. Now for the last part of my talk, which is about molding plastic materials. So the first work I did on this was during my sabbatical at TUT in Brisbane, Australia. And here what I was interested in was trying to see if a robot could shape some granular material, here's some sand, to a desired shape. So the way the problem is stated is that we want to obtain a certain image, for example, here the right image from the left one. For this, we need a scalar function to measure the image error. And the robot should apply a finite sequence of actions to go from the first to the last image, similar to what Ken Goldberg presented before with the RL framework. So we assume that the method works if after ki iterations, we get an upper bound on the error. So we had to add other hypotheses for this, because it's a very complicated problem and there was not much literature on it. And the first one is that the shape should be feasible. The second one is that we have a finite set of actions. Here we define two, pushing and tapping. And also the third one is that each action will only regulate some features in the image. So we can decouple the effects of actions on the state. For example, here you can see in red is the contour of our sand here, which is can be represented as a sequence of, as a list of pixels, just like in the previous video I showed you. And it can be controlled by the pushing action. On the other hand, the green is the texture of the image at a given position. So we can represent this as an imagette, a small image. And this feature can be modified by tapping on the material. So then we should design a controller based on the feature that the action affects. So recalling the actions, which are the pushing and tapping, we can rely on image-based visual servoing. So I showed you the equation at the beginning. In vision-based control, the velocity of the robot is controlled by inverting the matrix which relates the changes in the image and the velocity itself. So we can start modeling this, but clearly, very quickly, we are confronted once again with an issue, which is that this model is not available, and we need to find the relationship between state changes and actions. For example, if we consider the contour changes and the pushing action, we can we would like to figure out which action is needed to go from the red contour here to the green contour. And for this, there are various options. One is to go from the centroid of the red pixels to the centroid of the green pixels, and we call this method average. Another one is simply to push the sand where the distance is maximal between the two contours, and we call this method maximum. And the third one, which is quite trendy nowadays, is to use a neural network which can, given as inputs these current and desired contours, infer the blue arrow, the action needed to go from one to the other. So now the big issue is how to train such neural network, which should map the blue contours here in this image to the action, to the tool motion. So first of all, we recorded a data set of participants pushing with the tool, the sand, and the images were could be easily labeled because we were using a color code, as you can see. Then we break the sequence into smaller sequences. So on the left, you see the first image, on the right, the last image, and in the middle, all the images of the sequence. And this we can do by checking when the tool stops or changes velocity. Then we can, of course, detect the contour changes between these. Red is the first, blue is the last, and green is the intermediate. And then what we can do is we can take all permutations of these of pairs of images where there has been sufficient change along the sequence, and we have all the data for this, including the labels, because as I mentioned, the environment is color coded, and this is used to train the neural network. So the ground truth will be the position of the tool before and after, and the input to our neural network as the contours of the sun before and after the action. And as you can see, we have a quite good results. The yellow is the ground truth and the green is the output of our neural network, which unsurprisingly is more mistaken at the beginning than at the end of the action. Now to the funny part, the robot. So these are the experiments we did. So we want to achieve the image which you see on the top left, and the robot is operating on the bottom right and applying some pushes. Either the green or the cyan arrow are applied, and the human operator is selecting one of the two, because at this stage this was one of the last experiments we did, and we simply wanted to have fun and challenge a bit the system. So the best the behaviors that you see here are the neural network and the maximum method. So these two methods are respectively the green and the cyan arrows shown here. So more quantitatively, we benchmarked the three desired shapes, which you can see here. And these are the results which our robot obtained, which are quite nice. Of course, there is a sort of a discretization issue because this is due to the fact that the desired shapes were modeled by a human, whereas the reproduced shapes are made by the robot, which has a finite tool size, and this makes the images sampled a bit. So the big problem here was to define an error metric, and for this we used the mutual information, which is a very powerful tool in signal processing and image processing because it is robust to luminance variations and generally to different environments, etc. And we compared the three methods: average, neural network, and maximum. And as you can see, in all cases, the errors converge. So the robot is making the image much nearer in terms of mutual information to the desired one. The characteristics of each method are that the average was very coarse and in fact is the worst if you look at it in terms of error values. The neural network had a very fast convergence at the start but was not very efficient on the small errors, and the maximum method was opposite. If you look at the curves, it takes longer to converge but then is very efficient on small errors, because it will keep the robot pushing where there is an error between the two contours. So after that, I extended this work back in Montpellier on point cloud shaping. So this time we tried to move in 3D and use a robot hand to do the task. So we designed 3 actions again. I mean, no, in the previous work, there were not 3 actions, but 2, but knock, grasp, and poke. And the purpose here, once again, is to predict what will happen when I apply an action. So for this, we used 3 convolutional autoencoders for the robot and 3 for the human, which could infer, given an initial shape, what would be the following shape after the action is applied. Then we want to realize the desired shape, which you see on the top left here. And for this, we do a very simple path planning through a tree of possibilities. So we simply deploy the tree from each image to all possible following images, given all the possible actions. And then at each layer of the tree, we select the depth image, which gives us the least error with regards to the desired shape. And we stop when the least error starts to increase. So one very important thing, I think, in this paper was the metric which we used to match 2-point clouds. I will talk about it right after. So this is an experiment where the robot should reproduce an image, actually not an image, a shape. So a 3D shape, given the initial point cloud, it will apply a sequence of actions to reproduce the same shape. And here you can see that the result is very similar. And then we did another experiment, which was quite fancy, where the shape was made by the human and the robot had to reproduce the shape. So again, the robot is now executing the solution which has been found in the tree exploration. And as you can see, the results were also quite close. So I would say the most relevant thing here is that we need a metric to train our neural networks. And this metric should be a measure of how close 2-point clouds are. So one option is to go through ICP, iterative closest point, but this is probably untractable for deep learning because it will require a lot of time to calculate the metric each time. So instead, we designed a new metric which is very fast and consists in subtracting 2 modified images and gives you immediately the distance between 2-point clouds. So I can send you the paper if you're curious about particularly this part. I will just give a few conclusions, well, a bit not directly on soft manipulation, but more on the robot learning, which we practiced a bit in, as you have seen in these works. So it's more, I would say, almost philosophical or just my own reasoning about this. And it comes from a bit of considerations on the buzz there is about robot learning and particularly deep learning nowadays. So we should keep in mind that as humans, we have developed 3 types of intelligence. The first, the most ancient one is the spatial and bodily intelligence, which enabled us to hunt and fetch our own food in prehistoric times. Then more recently, we developed the relational intelligence, which makes us relate to other human beings and interact. And very, very recently, probably in the last 2 or 3 centuries, we have developed logical, linguistic, and mathematical intelligence, which makes us solve very difficult and complex logic problems. And what I find very fancy nowadays is that with the artificial intelligence developments, we have actually we are addressing this in the opposite order. It seems like we are capable of doing fabulous things in terms of the third point, like winning at Go with beating at Go a human with a machine, and so on. we are starting to have robots which can interact and relate to persons, but we are really struggling on the first point, as you can see in many demonstrations of robots, not so as nice as expected. And this is paradoxical because the spatial and bodily intelligence are the first ones as humans we developed. So I think there's a lot of work to be done for making robots which are actually capable of operating in real environments. And this is also why molding and deforming soft materials is a very interesting problem to be generalized for other issues as well. And lastly, also another thing which is a bit of a concern with robot learning is that most of the times it operates on correlations. So you have fancy correlations as the one I show here, where you can find websites showing this. This is the relationship between divorce rate and consumption of margarine. And a computer is not capable of discerning the fact that these events are uncorrelated. And you can say the same about syllogism, such as the one you can read here, which are also logic relationship which can easily break an artificial intelligence. So my personal take-home message, I would say, especially to the young students, is that machine learning and deep learning are really powerful tools, but they have to be used with caution. And in general, and I hope that's also what we are managing to do in Montpellier, you should combine the models with the data as much as you can. When models are available, as you saw in our work, you should keep them also in the pipeline, because data alone can be very tricky to be used. That concludes my talk. This is Bazar, our robot, and all the people who contributed to the papers and research I showed. Thanks again to the organizer.
Thank you so much. If there's any question, please go to the microphone.
Hi.
May you a bit closer?
Oh, hi. Thank you for your talk. For the shape throwing project, I have like a question. So I think that you have like a local reactive policy changing the shape of the deformed object. So have you observed like trap in local minimum to the target or some like oscillation around the target configuration of the object?
Okay, so I'm sorry, but I hear you.
Yeah, come here.
I just heard local minima on the target, but that's all.
Speak into this one.
Oh, hi. Thank you for your talk. I have a question on the shape throwing project. Have you observed like the trap of the object, like some local minimum towards the target, or like oscillation around the target configuration of the object?
Yes, for sure. That's, I think, also the reason. Well, I think you referred to the first one where we were pushing on the sides.
Yes.
Yeah, so yes, as you see, there's a plateau. So somehow that we cannot go below the plateau, which is that's also why we did not expect to reach a zero error. Okay. And the reason for this, in terms of machine learning, is that I think we have the data is not, we don't have enough data for very small errors. So that could be addressed by having broader data, including very small errors, which was not present in our data set. So it was kind of overfitting and performing very well when the error is big, but then as the error is smaller, it becomes a problem. Local minima in general, yes, but we had a sort of planning strategy, as you see in the video, where we select some areas where to operate. And I think that was the trick to get rid of the local minima, because we were actually choosing some regions of interest where to apply our framework. Because if you consider the problem as a whole, I'm quite sure that, as you say, there will be local minima. So I think when you do, this is a very general answer for all of you who want to work on soft object manipulation. I think when you do soft object manipulation, you always need, so that's also why it's interesting, is that you need planning and control all the time, because for sure your state space changes so much and your models are also changing so much that you cannot apply the controller as is. You have to control from one configuration to the other. Do you see what I mean? So there has to be a plan for going from one configuration to the other, and then a control loop below, which goes which converges to the given one. And that's been a bit the rationale of what we did.
I see. So like the planning module is kind of very important.
Yes, I think you need it very often in planning, even a rough planning. It doesn't have to be something sensational like the tree I showed at the end, the path planning in a tree, but you need that, yeah. If you want to make big changes in the object, yes.
Okay. Thank you. Yeah, thank you.
You're welcome.
Thank you very much. Let's take another question from Slido. The question is, in case of Doolam manipulation, how do you estimate your interaction matrix L? And how do you know which arm contributes to the observed deformation?
Okay, so it's a similar method as before. So technically we have this 12 degrees of freedom because we have 6 on one side and 6 on the other. But with the cooperative framework, instead of representing each arm separately, we have the absolute frame. Can you see me? You see me on the screen, right?
Yeah.
So you can have an absolute frame, which is driving the position, I would say, of the body center of the two end effectors. And then there is the relative frame, which can do the relative things between the two. So these, in any case, these are 12 velocity inputs. And then we use a principal component analysis to extract the 12 features of the object. And then what we do is that we run a few tests, just like Jiong was doing with the cable in one dimension. We run some tests to infer with linear regression the mapping between action and space. And then this way we get an interaction matrix on a sliding window, which is updated regularly, and this interaction matrix is inverted in the control law. I hope I answered.
Thank you very much. I think we have one more question in the Zoom, and then we need to close this talk for the interest of time. In the Zoom chat, it's very interesting talk and insights. I have one question on the SANS pushing work. From what I can see from the video, there are shapes and motions in 2D. Have you considered shapes and motions in 3D?
Yeah, so in the problem statement slides, as you saw, I was mentioning a tapping motion because we're doing this pushing on the side, and then we also wanted to tap, but it was not. So the plan was to use the texture. Sorry, the plan was to use luminance texture of the images, but it wasn't working well because I think the state was not easily relatable to the action. So that's why afterwards I moved to this 3D experiment. I think in all these sand, so in the 3D experiment we work on point clouds and we try to do actions in 3D. But in the first one it wasn't working well, so that's why I only showed the results on the pushing actions. This said, I think most of the problems we have nowadays, if we want to have a robot sculptor, is that the hardware of robots itself is not mature yet, because even as you saw in my last experiments, roughly what we do is we just do some fingerprints or try to grab some sand, but it's very difficult with the shadow hand or other robots to actually mold material. And I think this is the limitation of the hardware, which made us struggle a bit with actually extending to 3D. So, but surely it would be very exciting to do so. And maybe with softer robots, it could be possible, or with these robots which are waterproof, like the one which is used by Mohammad Al Khatib in the undersea, the soft hand. So yeah, that's my answer.
Thank you very much. Thanks again for the great talk.
Thank you again. Bye bye.
Thank you, Andrea.
Enjoy Philadelphia.
Okay, so now I think it's time for the second session for the Spotlight Talks. So the first one is Rita Laezza from Chalmers University of Technology, who should be there. So please, Rita, if you can go to the desk.
You need
And
to
I'll,
swap to your screen, Martina.
yes, I'll share it. Wait.
And get the speakers here if they're here.
Yeah.
Okay.
Okay.
My name is Rika, and I'll be presenting our work on blind manipulation of deformable linear objects based on force information from environmental contacts. Deformable linear objects such as cables are found across many challenging industrial applications, most notably cable harness production. The alloys don't really oppose deformation in most directions except when being tensioned. And humans tend to use this observation to simplify the sensing and manipulation problems when handling such objects. So when we have a cable in between our hands, then we can feel the tension when we're pulling it, and we can assume that the shape in between the two grasp points is a line. And also, if we then push that cable and have some sort of obstacle, we can feel a change in tension and estimate the new shape. So it is based on this simple observation that we propose a graph representation of the object, which then is used to define 9 force-based manipulation primitives. The goal of this project is to see how far we can get with force-torque sensing alone, but I would like to point out that in any real application, vision will still play a big role, especially for handling errors. So when something unexpected happens, it's very hard to recover with force alone. So the proposed representation is summarized as a graph G and constant of the weight per unit length, which is either measured before or known, or even just measured using the motion primitives as a first step. Once we have that, then we have the path graph that is constantly updated as we manipulate the object, and it contains a set of vertices and edges. Vertices are defined in a set order, so anytime that a new vertex is added to the model, then the indices need to be updated. And also, here we can see that vertex 3 was added in order to formulate this clipping motion. So when the grippers were above the fixture, then we added a new vertex to define that we want to have it clip through this object. And we can also see that each vertex contains information about the position, orientation, and also a point mass estimate of that vertex based on the rho constant. Each edge naturally contains information about the distance between 2 points, as well as a measure of the sag to evaluate how accurate this distance is. So if there's a lot of tension, there begins to have to be a bit of sag, which then means that we cannot trust our distance and we should tension more. We also have a scalar force, that is the force felt along that edge, and an estimate of the elasticity, which is needed mostly for these tensioning primitives, which can easily lead to an emergency stop triggered with the robot, and we want to try to avoid that. So the 9 motion primitives we have proposed are essentially tensioning primitives or sliding and clipping primitives. They are subdivided into coordinated control when the grippers are moving in a relative motion, or individual control when we have a single gripper manipulating the object. The most important primitives naturally are the tensioning ones, and here we demonstrated with more detail how we can see that the sag is being constantly estimated, and it shows in red when we have too high sag, and in green when sag is none, and we can assume a linear edge. We also have here a demonstration of all of the primitives on the real robot. We also tested our contact point estimation, which is necessary to update the vertices, and we see here the error decreasing as the Kalman filter observes more data, and also a sudden change that is then quickly recalculated. So we can see here how as the robot moves, the variance of the estimate becomes smaller. And then finally, we test all of this on a cable harness experiment with hard-coded primitives, which are shown here in the bottom. Thank you. My name is Rika, and I'll be presenting our work on blind manipulation.
Any questions?
Thank you, Rita.
Yeah, actually, before questions, I just want to mention, I hope that the last frame would stop there because I had to shorten the video, but a lot of the credit goes to Finn. That was the last second frame that was there. Finn did this work in his master thesis, so it was really good work.
Okay, nice.
Yeah, we have one in-person question, right? Or, yeah, maybe come also just up here. I think the mic still doesn't pick it up right, so just gonna use the one here.
Yeah, so my question is, how did you estimate the slack in the rope?
We used the catenary model. Yeah, it was just a catenary model of the rope. That's why we assumed this uniform density. We need to have that estimate, and then we can actually have, there's just some formulas to estimate the sag based on the tension.
Okay, great. Are there any other questions? So if not, I think we can.
Yes. One now.
Okay.
To execute the primitives in the last video that you showed, did you have you had all the red position holders placed at fixed spots, right?
Yeah.
So did that limit the sort of which primitives you could execute at which point of time, and how did? I guess this is the more real execution question.
Yeah, exactly. So I mean, this is a blind operation, but we need to have some assumptions of what is around. So even though we're estimating the contact points, when you define the motion, you have to know where they are in a sense. So you can define the right motions.
Yeah. So there was no vision in any sense.
No vision at all. It was just knowledge a priori. Yeah.
We need to move on, but Rita will also have a poster later. Yeah. So then we'll direct the question towards her there.
Yeah.
Thank you again.
Thank you.
Yeah. Thanks a lot. So the next one is Ali Dinkel that should be there. So please, if you're there, just get closer to the laptop and I'll start playing the video.
Wires are ubiquitous deformable objects. Perceiving these objects enables robots to interact with them in challenging manipulation scenarios, like industrial wire assembly, knot untying, and autonomous human habitat caretaking. Our work on wire point cloud instant segmentation from RGBD imagery is inspired by several recent works. First, recent work automatically generates a synthetic dataset comprising single wire images where the wire masks are cheaply obtained using color-based thresholding. These images are used to train DeepWeb v3+, a method of semantic segmentation to segment wires in cluttered scenes. Second, the RANE+ algorithm proposes the first method of RGB wire instant segmentation. The RANE+ algorithm enables individual wires to be distinguished from each other, building off of work produced in the auto-generated wires dataset. Third, MaskRCNN is a state-of-the-art general method for object instance segmentation RGB images, learning to directly predict instance masks. Finally, the point-run mask prediction head is trained to iteratively predict the label for ambiguous points to refine the mask edges to finer resolutions. Point-wise semantic labeling of point cloud data remains an open challenge in computer vision. We first perform instance segmentation on RGB imagery, then apply the instance mask to the depth image. Object instance segmentation models require labeled data for training. Annotating point cloud data with object instance information is expensive. Pixel data in RGB images can be cheaply obtained using automatic labeling techniques. In general, point data in depth imagery are more difficult to label to obtain ground truth information than pixel data in RGB imagery. This work leverages automatic RGB image labeling in the UIUC wires dataset to train MaskRCNN to perform object instance segmentation in RGB imagery. The UIUC wires training data are synthetically generated from single object images using color thresholding to automatically obtain object instance masks. It uses the copy-paste background substitution, scale jittering, and hue jittering augmentation techniques to increase the variety of wire configurations and environmental noise classes present. UIUC wires is an RGB image dataset comprising 2,000 training images of up to 4 wires and up to 2 devices per image. Images include 2 schemes of object segmentation mask representation. With object segment semantics, or OSS mask representations, each object contour receives a unique bit mask, and occlusions by other wires and devices are not explicitly represented. With object semantics, or OS mask representations, all contours comprising an object receive one corresponding bit mask. These data are used to train MaskR CNN as implemented in Detectron-2 with the point-and mask head. The trained model is used to predict object instance bit masks on the RGB image. Then the instance segmentation masks are applied to the image-aligned point cloud to obtain the 3D points belonging to each object in the scene. The UIUC wires work under submission found that MaskR CNN, instance segmentation, and RGB imagery performs better when wire masks are specified with OSS semantics. The proposed method of point cloud segmentation using the PR plus OSS model produces significantly more complete segmented point clouds than the PR plus OS model. Preliminary results indicate a 153% improvement in the number of points recovered using the PR plus OSS model. The segmented point cloud was used to construct an object mesh of the scene using a density-based clustering outlier removal step to smooth the scene mesh. The mesh reconstruction is a candidate 3D representation of the scene from raw RGBD data. One challenge with using UIUC wires to train instance segmentation is it does not simulate real lighting effects like object shadowing, object glare, or low light conditions. We also observe resolving self-occlusion and environmental occlusion is an open problem in wire instance segmentation. Finally, we observe point clouds are noisiest around object edges, which is a residual source of uncertainty in the scene surface reconstruction step. This work is the first to predict wire object instances in point cloud data using MaskR CNN. This work leaves the following questions for future work. Can a graph search method, such as the method used in RENE+, be combined with the instance segmentation performed by MaskR CNN to improve instance segmentation performance for the class of wire instance segmentation problems? Can multiple fused sensor perspectives improve scene point cloud and mesh retrieval for the 3D wire instance segmentation problem? And how do wire detection and segmentation frameworks perform when trained on the auto-generated wires dataset compared with the UIUC wires dataset? In addressing remaining open questions, future work aims to improve the reconstruction quality for model-free deformable object perception. Thank you for your time and attention today.
Thank you, Ali. Are there any questions?
Not from the room, but maybe there's some online.
No. I actually have a curiosity. So do you think that if I understood it correctly, you now just do the segmentation using the RGB image, right?
Correct.
Yeah, okay. So have you tried also to use the depth map that you have to do the segmentation? And do you think that this may help?
So one of the motivations for this was the difficulty of labeling depth imagery, the difficulty of labeling point clouds directly, but we came up with this auto-labeling technique for labeling depth imagery to train a model. Well, I don't know how obvious it is, but PointNet, there are a few depth image segmentation models that exist, but we just, because there was no sort of existing wire data set, we started from the RGB standpoint to obtain free data. Thank you.
Okay, thanks a lot. So now we have the next speaker, that is Shengyin Huang from the University of Leeds, and I think that he is online. You can just show up and I will start playing the video. Hello.
Hi. Can you see me?
Yes.
Okay. Hello, everyone. My name is Shengyin Wang. Today, I'm going to present our work on goal condition model simplification for deformable object manipulation. This is a joint work with Matl, Leonetti, and Memo Dog at the University of Leeds and King's College London. Deformable objects are everywhere in our daily life and have a wide range of applications from housekeeping, medical operation to industrial production. Compared to rigid objects, deformable objects pose two main challenges: high-dimensional configuration space and complex dynamics, which make both planning and learning time-consuming. To simplify the deformable manipulation problem, we have conducted some research trying to fill several existing gaps. Instead of defining key features manually, such as corners and contours, we want to establish an automatic feature extraction method that is adaptive to different goals. Instead of using the expensive fine models, we want to find a simpler model with acceptable accuracy. Instead of learning high-dimensional space, we want to find a compact state representation that captures the most important and relevant information to achieve the task. This leads to the work we are doing now, namely as goal conditional model simplification for deformable object manipulation. Potential usage of the method includes simplifying the action space or state space for both motion planning and policy learning. In this work, we focused on action space simplification for manipulating ropes and clothes using cross-entropy method as a planning algorithm. Given the goal configuration, our model simplification method will find the minimum elements to approximate the original model with acceptable accuracy. Depending on the types of the deformable object, line fitting or mesh simplification will be called. After model simplification, a set of key points will be extracted as graspable points, which can reduce the searching space for CEM-based motion planning. For line fitting, we start from using two key points to approximate the original model. The position of the key points can be anywhere in the space. We use quadratic programming to find the optimal position based on our defined distance error metric. If the approximation error is below the threshold, the simplified points and line segments will be outputted. Otherwise, we will gradually increase the number of key points until the precision is satisfying. As in the example shown above, 4 or 5 points give a much simplified model with minor errors. The same idea applies to close approximation, with the only difference of using off-the-shelf mesh simplification toolkits from MeshLab. For a piece of clothes folded sideways, a simplified mesh with 6 triangles has a small enough error to approximate the original model. After model simplification, we use the simplified model to reduce our defined action space by extracting a small number of key points on the original model as graspable points instead of searching in the action space of all points. The bottom left figure shows the extracted key points in blue pentagons, while the bottom right shows the motion plan based on the simplified action space. Finally, to demonstrate the effectiveness of our proposed method, we conducted a set of comparative experiments on 4 tasks. Due to limited space, only the results of close diagonal folding are shown. As we can see from the same initial state, CEM simple, which is based on the simplified action space, can successfully achieve the task, while CEM original cannot find a feasible plan with the same number of simulation steps. Additional results can be found in the paper. Thanks for watching.
Thanks a lot. Are there any questions?
Not on site.
Okay, we don't have any remotely. I actually had just a curiosity. Do you think, actually 2 things. One is, do you think that it could be easy to extend the approach with some complex shapes? And also if you tried to apply it also in real world?
Thanks for your question. Yes, yeah, I think it can be extended to more complex shapes. But for real robot experiments, that is still an ongoing work, and we are having still having some many problems, especially in the perception system. But the method is scalable to most complex shapes. Yeah.
Okay, great. Okay, thanks a lot.
Thank you.
So if there are no other questions, I will move to the next one. There is, I'm so sorry for pronouncing it probably really bad. That is Azak Kipur from Carnegie Mellon University. That should be, no, sorry. It's Xiaoqing Yao from University of Illinois at Urbana-Champaign. That should be there. Okay, so I'm starting the video.
Hello everyone. Today I'm going to present our work on estimation of point-based volumetric stiffness model using joint torque sensors. Estimating the stiffness of the deformed object can enable robot arm intelligently navigate around in a cluttered environment. Such cluttered environments exist in agricultural applications or our daily life. Estimating stiffness can also enable efficient autonomous packaging of the deformed object and also haptic feedback rendering in teleoperation. Existing works that model the stiffness of the deformed object either require a mesh model, which can be difficult to obtain online, or mostly work with two-dimensional planar object. Recent work model the volumetric obstacle distribution from contact feedback, but only recover the geometry of rigid objects. In this work, we present volumetric stiffness field, a point-based deformed object representation that can be efficiently estimated in real time and used to predict force response during interaction between the robot and the object. We apply this method to model the stiffness of a highly heterogeneous deformed object, which is the artificial plant. Our method is as follows. First, the hardware sensors will sense the joint angles of the robot arm. Together with the geometry of the robot, the contact simulator will simulate quasi-static stick-on-stick motion during interaction. The simulated displacements of points in the field will be sent into the volumetric stiffness field, giving an expected joint torque measurements. Compared to the actual joint torque measurement, the recursive estimator will update the belief on the distribution of the stiffness in the environment. We implement an extended Kalman filter-based method that can run this update loop in 17 Hz on a normal CPU. Here, we visualize one example where the robot arm interacts with the artificial plant and the volumetric stiffness field is estimated in real time. The left figure shows the motion of the robot arm, and the right figure visualizes points with stiffness estimate greater than 1 Newton per meter. We repeatedly touch the same location on the plant from different joint angles. Here we can see two features. First, before contact happens, the free space volume is mostly estimated with low stiffness and are not visualized. There is sparse spurious estimation, but can be potentially removed in post-processing. Second, when contact happens, the estimated high stiffness region is mostly localized around the true contact position between the robot arm and the artificial plant. We make quantitative evaluation of this dataset with 11 touch sequences and 400 steps for each sequence. We take a k-fold validation approach, where we take every sequence as a testing sequence and estimate the volumetric stiffness field using the rest 10 sequences. We implement several baseline methods that directly learn this mapping from joint angles to the joint torques. The red figure shows the maximum torque prediction error per sequence, and we can see our method outperforms the baseline methods by a large margin. Here, another experiment where the robot arm touches slightly different location on the artificial plant with similar configuration. Taking a zoom-in view of the touch region, we can see variation on estimate stiffness in this field. There is sparse, spurious stiffness estimation on the upper part of the robot arm because of limited number of touches and similar configurations. Estimating the stiffness by touching every location of the plant can be very tedious and time-consuming. Therefore, we implement a vision-based method to extrapolate the stiffness estimation from touch region to untouched region. We only use the RGB value and KN interpolation and demonstrate that the quantitative result is interesting. We can see the branch region is estimated with higher stiffness value compared to more deformable leaves, which corresponds to our intuition. In conclusion, we present volumetric stiffness field, which is a novel deformable representation that can be estimated efficiently in real time. The estimate model can be used to predict force response and achieve better performance compared to baselines. In the future, we are interested in include correlation between motional points in the field and learn the relation to map visual information to stiffness.
Thanks a lot. Are there any questions?
There are no questions here, but I actually have a question. Like, if I understand it correctly, you use the vision not for the estimation directly, but later for the interpolation.
Yes, that's true. We only use the vision for the estimation.
Could you also use it for the estimation part, or?
That can be potentially used in the estimation, but we currently don't have that integrated in the estimation procedure.
Okay.
Yeah.
Okay, great. So I think if we don't have other questions, we could move to the next one. So thanks again.
Thank you.
And the next one now is Azar Kipur from Carnegie Mellon University. That should be there. Okay, hello. Let me start the video. Okay. Let me share also.
Hey everyone, I am Mohammad Musai, and I am presenting our work on detection of deformable linear objects and the physical interaction of aerial robots with these objects. Deformable objects such as cables and wires are part of many of our everyday and industrial tasks. We collectively name them deformable linear objects or DLOs. In order to automate tasks involving DLOs, such as manipulation of cables in industrial settings, utility pole maintenance using UAVs, or stitching with surgical robots, a crucial part is to detect the DLOs in a way that the detection result can be used for further manipulation or planning. On the other hand, to extend the DLO applications to aerial robots, we need to study the requirements for physical interaction of aerial manipulators with DLOs. Some of the challenges in this application that a detection method needs to address includes partial views and occlusions, crossings, existence of multiple DLOs in the frame, and supporting different image types. Finally, the detection method needs to output a model that is suitable for other automation tasks, such as manipulation and planning. While there are many methods for segmentation of DLOs, their output as a collection of pixels is not suitable for most robotic tasks. On the other hand, various tracking methods for DLOs exists that can track the motion of a DLO across the camera frame once it is initialized in the first frame. However, as far as we know, our detection method is one of the few solutions that can fill the gap between the segmentation and tracking methods for robotics purposes. To go through our approach, First, the method segments the input frame. This output has many gaps which needs to be filled and many crossings that needs to be resolved before it can be used. In addition, the segmentation is purely a collection of image points, and we need to model the DLO in a more suitable way. The next step is thinning or skeletization, which allows an efficient extraction of contours in the next step. Each of these extracted contours are used for fitting a small DLO segment, and then all overlapping segments are removed. Finally, we iteratively find 2 DLO segments that are best fits and connect them together using a computed curve. The final output is a single DLO represented by a sequence of short fixed lengths cylinders connected to each other using a spherical joint. This output can be used as the initial state for tracking methods and had been used in our work for cable routing and manipulation. The whole process is near real optimal, and the whole process is near real time. In these experiments, you can see how the detection and method can handle occlusions and crossings. To extend the physical interaction of DLOs to aerial robots, we analyze the visibility of the tasks from the end effector position perspective in simulation. We also analyzed the required forces for normal everyday manipulation tasks, such as pulling a USB cable, and concluded that even for simpler tasks such as this, the remaining wrenches to perform the tasks are barely enough. With that, I'm going to conclude this talk, and thank you for listening.
You have a question? Yeah, just come here to the microphone.
Okay, thanks a lot. Are there any questions for?
Yes, yeah.
Okay, cool.
Thanks for the great talk. I was wondering if you, how did you reason about which cable is on top of the other? Because in a cable manipulation, if you do not reason about that, that might bring about a bunch of problems, right?
Yes. So in this specific work, we did not reason about it. We did develop some method, and I've seen actually better methods being developed than what I just ad hoc developed. And maybe in the future work, it will be infused into this method. But right now, it does not detect which one is on top.
Would having a side view help?
Probably having a side view helps, but the methods that I've seen, I reviewed, but so I cannot disclose what methods are. They had 99.5% success rate in detecting the top one. So I'm pretty sure it will be published.
Cool, thank you.
Thank you. I think we also have a question here in Zoom. So there is Todor. We cannot hear you. Maybe you could just write in the chat. So he said, okay. So the question is, I was wondering how you deal with 3D DLOs.
So we started the work with 3D. Our camera was RGBD, and in the middle, this work, in the perception work was done for my internship. So I did have a very limited time, and we switched from 3D to 2D, but gave a very clear guideline how 3D can be made. Perception, I have not worked on 3D yet. The method is very general and can be easily extended to 3D, but it's not implemented for 3D right now.
Thanks. I don't know if you hear me now.
Yes, now yes. Okay, thanks a lot.
I think now, I think for time we might have to move to the next speaker, but I think there's a few other questions too.
Yeah, let's move to the next speaker, but just catch him.
Thank you. So we now have the last speaker for this talk, for this session. That is Cristiana de Farias. She's online. Okay. Hi. Now I'm sharing the screen.
Today, I'm going to present our work on grasp transfer for deformable objects by functional map correspondence. The main motivation behind this work is that we want to grasp objects in an unstructured environment, such as the workshop in the image, where there are arbitrarily deformable cables, articulated tools, and rigid objects. In grasping planning literature, there are a number of methods to plan grasps for rigid objects. But what about objects that have suffered some non-rigid deformation? Intuitively, we might just think that we can ignore the object after the deformation and plan grasps directly on it after the deformation has happened. However, this can be counterproductive, as we're ignoring some previous or expert knowledge, such as task awareness, and it can be inefficient because maybe we have planned grasps before the deformation has happened and we're just throwing them away and planning them again after the deformation happened. As humans, we're capable of recognizing similar objects and similarities between objects, and we can find correspondences between different parts of a shape, even in the presence of deformation. Thinking of that, we can think of a second option, which is to transfer grasps between instances of objects that have suffered non-rigid deformation. To do that, to exploit these correspondences between parts of the objects, there's a very nice framework that was proposed in the 2012 paper Functional Maps, a flexible representation of maps between shapes, which is the functional map framework that can find correspondences between near isometric shapes, even in the presence of large deformations. And by joining that together with some user input to have some task awareness, we have our method presented in this image. We start here by selecting an object and segmenting that object in different parts. A user then chooses one of the parts of the object, and we plan a number of grasps with the Locomo grasp planner in that particular object part. Then a robot observes a deformed version of that object and gets a point cloud of the scene. It does some pre-processing to get a mesh of the object, and we then use the functional map framework to transfer the selected segmentation from the source object to the target, and we compute the transformation between those two regions. With this rigid transformation, we can transfer the grasp to that specific segmented part. And we do some local replanning to ensure that the grasp will be stable. We do a number of experiments with these 4 objects in the image here. In these different configurations, the dataset that we use is available on our GitLab page. And we have actually very nice results shown in these videos here. In the videos, the top image shows the initial grasp before the transfer, and in the bottom, we have the grasp after the transfer. And our experiments were particularly successful. We compared them with a similar method, but using CPD and ICP instead of the functional-based method. And we have seen that the functional map-based method improved grasp transfer significantly, especially for objects with high deformation, such as the case of the bear, which is a more complex object, less aligned, and with a higher deformation. In this case, only our method worked and the other 2 failed. So in this work, we have shown that functional maps are a good option for transferring grasps between objects, and it allows information to be propagated as objects deform. Today, I'm going to present our work.
Thanks a lot, Cristiano. And are there any questions from the audience?
Yeah, there's one. Please come. Oh, there's two then. Just line up.
Yeah, I had a question. So is a functional map like a matrix, or like what sort of transformation is it?
So the functional maps basically works by changing the domain that we want to work from a matrix of all the vertices in the mesh to a functional basis. Like we applied Laplacian to transfer the domain, and then we do the correspondence in this Laplacian domain. So that's how it works.
Hey, do you use any environment collision information when transferring the graphs to make sure it's still valid after the deformation of the object?
Yes, the way our method works is we plan a number of grasps in the beginning, and in the beginning part that we segmented, and then after we transferred, we check if the grasp is feasible. So we filter out the ones that are not.
I see. Thank you.
Thank you very much.
Thanks a lot. So I think if there are no other questions, we can close this session. And thanks again.
Thank you.
Thanks to all the speakers for being here. And now it's lunchtime. So we're sorry that we are running late, but we have to reconvene at 1:45. So see you in 40 minutes.
Might start a little bit here. Yeah, but let's say yeah.
The recording has stopped.
I think you guys ready to get food.
Yeah, we have them in the second coffee break. That was the idea, at least, because it's 5 posters, and it's a 3, I think, for the next.
So I should put it up like right before.
You can put it up now. I mean,
Yeah, that's what I'm asking.
it's not going to get taken down.
I see. And are there allocation? Maybe I missed something.
It's
Yeah.
on this
Just
page. Any place you find. Yeah.
I would.
Michael. Michael, are you there?
think it's that microphone Yeti. Okay, let's see if Martina, can you hear us?
Yes. Hello, Shuran. Thanks for being here.
Can you hear me?
Yeah, it's a bit silent. So I can hear you, Michael, but not Shuran.
Okay, so it's this mic again. Okay, let me actually swap to the.
I think I will try it out later. It probably.
You can try it. Yeah, just to see.
Oh, okay. Now it's good.
For the round, but how is it for the remote? How is it, Martina?
Can you try to speak again?
Hello, can you hear me?
What's that?
Oh, hello, can you hear me?
It's a bit low.
I haven't tried it yet. It's connected. So HDMI and端-to-端for this to show up.
Yeah, you need to join the Zoom.
Yeah, that should be.
And then. Oh, okay, there.
But how to make sure that that's nice.
Okay, I think for the we can just retry this. You noticed something.
Oh. Good. Okay, let me just make sure that's the size gonna play.
One is usually reliable. There's a room at CMU where all the adapters fail except for this one. Like I literally replaced adapters with the different HDMI cables, and this is the one that works, and the other one.
Okay.
Okay, I think this is good. And if I just share my screen, I should share my screen.
Yes, in the Zoom as well. How is the sound, Martina?
I think now it's better.
Okay, I placed the mic.
Oh no, echo.
I just joined. Oh, I should mute this. Okay, now it should be good.
You still hear us, Martina, right?
Yes.
Okay, perfect.
It says I cannot share screen. Can I be the co-host?
Yeah. Martina, you need to give her the permission.
Because now who can share all participants?
Try it again.
Because I'm sharing. I think that's blocking.
Yeah.
But I can stop sharing, I mean.
Yes, okay, now I should work.
Great. So
Yeah,
I
I think it should be this.
Just this.
I think it's the safest.
Okay, cool.
And then if I
You can make that.
and then so many buttons. This is good.
Yeah. It's running. Yeah. And I think if you move the mouse from that, the Zoom should also this should also vanish after a while.
It's okay. It's not a lot of information there. Should be fine.
It's actually it doesn't show up in the remote, but it does show up in the.
Yeah, here it's perfect.
Okay. I think this is good.
Okay. Yeah, it's a bit weird. Okay, we still have some minutes.
Okay. Yeah, let's just wait.
This one? Oh yeah. Yeah. So we still have let's give some more. We should start. Yeah.
Yeah. That is late at the
Yeah, exactly.
I saw the announcement about the Korea report.
Yeah.
Very helpful.
Yes.
I think I need to sign some kind of release.
Yes. We have a printed version of the release over here. Printed version of the release.
I can do it online. Yeah, they just said there would be enough. Yes. Let's can. Let's get everyone that we can get. I'm not Ken, so I'll get started. Yes, we're just going to send it to email. Okay. It's just the release for the streaming and the YouTube. Perfect. Okay. It's just a digital signature works. Yeah, let me just. They did send me something. Yeah, then if you can somehow get that back, the signature on it, you can, like, if you can draw into it in the PDF or whatever, that is perfect. On our way. Okay, cool. Thank you so much. Yeah, thank you.
Your student here at
Yes. A few. Yeah. Yeah, I have a few that's sitting there. I can introduce you later. And Chen is not here. Who? Chen. I did the RSS. I did the RSS.
Oh.
You will see them.
So maybe 3 more minutes. That's, I also love this title of the talk, combined with the title of the talk. It's some nice evolution. So yeah, people are coming in now. So let's give them some minutes.
Yeah.
It's 20. Oh, she has it. Everything.
This meeting is being recorded.
Can you trick the okay?
Oh,
thank you.
Got it.
Got it. Yes, I'm going to close this. Let's say 3 or 4 more minutes. Yeah.
The doping has done arrived yesterday. 8.5 hours flight. Let me close the door and then
I can. Yeah. Okay. So hello everyone. So thank you for showing up to the second half of the workshop, and it's my great pleasure to introduce our next speaker. Shuran is an assistant professor in the Department of Computer Science at Columbia University. Before that, she received her PhD in computer science at Princeton University. Her research interests lie at the intersection of computer vision and robotics. And her work has received awards, including the Best Paper Award at TRO 2020, Best System Paper Award at Coral 2021 and RSS 2019, and the Best Manipulation System Paper Award from Amazon in 2018, and her other work has been finalist for Best Paper Award at ICRA 2020, CVPR 2019, RSS 2019, IRA 2018. She's a recipient of many awards, including the NSF Career Award, the Sloan Research Fellowship, and research awards from Toyota Research Institute, Microsoft, Amazon, JP Morgan, and Google. And it's our great pleasure again to have her give a talk, so go ahead.
Thank you so much, Daniel. It is a great pleasure to be here, and so nice to see everybody in person. Yeah, so today I'm going to talk about dynamic manipulation for deformable objects, and hopefully by the end of the talk, you think it is a good idea. Okay, so I think at this point of this workshop, I probably don't need to repeat the importance of manipulating deformable objects and why it is a hard problem. But I do want to highlight one of the most fundamental properties of deformable objects that actually directly motivates our approach of using dynamic actions. That is, there are extremely high degree of freedoms. Right? So for objects like clothes or garments, they can easily be considered as have a near infinite degree of freedom. And what makes things worse is that among all these degree of freedoms, actually only a very small amount of those degree of freedom can actually be directly manipulated or controlled by the robots through contact. In other words, the system is often highly under-actuated. Right, so for example, if a robot just kind of holding a cloth, all it can control is a very small region of the cloth around the gripper. And the rest of the cloth is kind of just hanging there, and the system does not have any direct control over those auto contact positions. So as a result, because of that property, a lot of actions or action primitives that we designed for manipulating rigid objects is actually highly inefficient when we're dealing with deformable objects, because each time or during each of the interaction, the system can only manipulate or kind of affect a very small region of the class or the object compared to the total degree of freedom of the object. And apart from efficiency, this kind of quasi-static pick-and-place action also kind of limited the type of tasks the system can perform. Right? So for example, a system or a robot can never really manipulate an object that's outside its kinematic reach range. However, in contrast, we human actually manipulate deformable objects in a very different manner. Right? So we often use very fluid and fast motion that fully leverage the dynamics of the object in order to quickly achieve our goal. So formally, we can categorize these two types of manipulation as quasi-static or dynamic manipulation. So fundamentally, what dynamic manipulation allows us to do is to leverage those accelerations in action, in other words, the dynamics in the system, in order to control those auto contact positions on the surfaces or the deformable object. Therefore, allows the system to obtain more control over the total degree of freedoms of the object. And I think this property is actually particularly beneficial for deformable objects or in general, a system that's highly under-actuated. So here are just a few quick examples of applying dynamic manipulation on deformable objects. So for example, we can fling a cloth to open it, or swing a rope, or opening a bag with active air. Right? So in all these examples, we can actually highlight the position on the object that's it's actually manipulated by kind of controlled by the system, but actually never really directly in contact with the robot throughout the manipulation process. And before we get into more details about those examples, let's take a step back and then think about this question. If dynamic manipulation is so well suited for deformable objects, then why we have not yet using it everywhere? So what are the main barriers preventing us from using dynamic manipulation for deformable objects? So I think there's three key challenges. So first is action complexity, or the action sequence complexity. As you can imagine, for programming or kind of code up a simple pick and place action, you only need to specify 2 positions for pick and place, or like 2 unfactor poses. However, if you want to specify a dynamic action, we also need to kind of, in addition to specify these velocities or accelerations in action. Therefore, the policy or the algorithm that designed for dynamic manipulation really need to be able to handle this expanded action space. And another challenge is complex object dynamics. So as we know that objects' motion under dynamic action is actually highly influenced by their physical properties. And many of those physical properties is actually extremely hard to measure, especially if you consider deformable objects. Right? So that really requires the system or the policy able to actively adapt to those hard to measure physical properties on the fly. And I think the last challenge is about simulators, or the sim-to-real gap, right? So I think by now, the simulators for class or for deformable objects is still very far from perfect, especially when dynamic actions are involved. So how to design a system that either can directly or efficiently learn from real world, or robustly adapt this kind of sim-to-real gap is another big challenge. And in today's talk, I'm going to kind of show some of the possible solutions for all those challenges through 3 of our recent work. And we will start with a relatively simple task that's just kind of doing class unfolding. That's not really require very precise control, and moving towards more challenging tasks that actually has much higher requirements of precision and also is goal conditioned. So let's start with Flingbot, which is actually our first attempt of using dynamic manipulation for the task of class unfolding. So the task for class unfolding actually has a very simple objective. It's just trying to maximize the class coverage through interactions. However, just like many tasks in robotics, although the objective is very simple, designing or kind of developing a robotic system that's able to do this task efficiently and robustly is actually quite hard. So here is an example of a 2-arm system that is trained to do this class unfolding task using pick and place actions. So what you can see is that it actually takes the system a very long time in order to make a very small progress. Actually, for a very long time, the class is still kind of in this compose state. And what's worse is that if the class being unfolded is larger than the robot's kinematic reach range, then the class will actually never be fully unfolded. So which means that if you think about unfolding your blanket in the morning, if the blanket is larger than your arm length, then you'll never be able to fully unfold it, which is not very ideal. Right, so, but obviously that's also not how we're gonna do this task, or like how human will do this task of class unfolding. So very likely what we're gonna do is something similar to this. We're gonna hold this class with 2 arms and then fling it with a high velocity in order to quickly unfold it. Right, so based on this observation, the key idea for Flingbot is actually really simple. It's just use high velocity 2-arm fling for class unfolding. So to implement this idea, we developed a system that learns how to unfold a piece of fabric using a sequence of pick, stretch, and fling action. So this, the performance of the whole system, or all the action primitives, are directly measured by the class coverage that can be directly computed from the top-down camera. Therefore, the whole system actually can be trained end-to-end with self-supervision. So you can let the system collect training data by itself, and then it will just overnight improve its performance. So to make long story short, by the end of training, both in simulation and real world, Flynbot is able to reach 80% of coverage within 3 interaction steps. And at least for the class that we tested on. And it's also able to work on the class that is larger than its a physical reach range, and also generalized to class where garments has different geometrical shapes when it's only trained on rectangular class. So here is a more detailed comparison, and in particular, we compare to a baseline that's used only pick and place action. You can see that Flynbot is able to fully unfold this class within just 3 interaction steps, where the pick and place baseline actually take a much longer time to make progress. Even with significant more interaction steps, it's still not able to fully unfold the class. And here is just another example of testing its generalization. Again, the system is only trained on rectangular class, but here we are testing it with a t-shirt with a quite different geometry and shape, but the system is still able to perform reasonably well. So I think throughout the process of developing Flynbot, I think the most surprising thing we learned is that even without explicitly modeling the class state or using any complex learning strategies, Flynbot is actually able to work really well for the task of class unfolding. And I think the simplicity of this approach really highlights the key takeaway for Flynbot, which is the dynamic action is just really good for the task of class unfolding. But of course, I don't want to give you the wrong impression that Flynbot is able to solve all the class unfolding tasks, which is obviously not true. So actually, one of the typical limitation, like failure case for Flynbot is that when the class getting larger, significantly larger or heavier, the system cannot actually produce sufficient speed in order to fully unfold the class. So for example, here the system is trying to handle a long dress, and actually no matter how many times you try, because of the speed limit of the robot, it's never able to fully unfold this piece of this long dress. And also in those cases, in order to further increase the robot speed, it's either limited by the hardware or sometimes can even be dangerous if the system needs to operate around people. So in a follow-up work, actually, we try to address this problem by introduce additional aerodynamics. Right? So this system we developed is called dexterity with air in it. So what we do is we ask another robot try to control an additional air blower and learn a closed loop policy of controlling the direction of the air blower. And with the help of the aerodynamics, the additional aerodynamics, the system can actually easily unfold a large variety of class, including this long dress in this example. And another thing to note is that with this new formulation, we actually can easily replace all these 3 robots with some slow and cheap robot hardware, because now we no longer require the system to move in a high speed. And also the air blower, you can just buy it from Amazon with $20. And of course, air-based manipulation actually has a lot of other applications in addition to just unfolding class. Right? So here I'm showing you 2 other applications. One is trying to use active airflow to opening a deformable bag. The other is trying to blow the particles into a target area. And I think compared to those traditional contact-based manipulation, actually air-based manipulation has a lot of unique or complementary advantages that I think is still underexplored, and I think it's pretty exciting and interesting to think about. And go back to Flynbot, I think another limitation that Flynbot has is that it has actually very limited capability of handling goal condition tasks, or like, for example, achieving specific goals or configurations of the class. So for the whole system, actually what it's trained on or what it only care about is the total coverage of the class, which means that all the configurations that you are seeing here is actually considered as equally good by the system, which is obviously not sufficient for many real applications that requires more precise configurations. So for example, if you want to fold the class, maybe only certain configuration is good for those tasks. So in the next project, we're gonna...
It's some error from the Zoom.
Okay.
Sorry.
No problem. Yeah, so in the next project, we're going to focus on actually another category of tasks that is much harder or much challenging, but also goal conditions. So what do we mean by goal condition task for dynamic manipulation of deformable objects? So here are two examples. One is trying to swing a rope and try to hit a target position in the 3D space. The other is trying to swing a cloth and then try to swing it in a way so that it reaches to a target configuration. Right, so in both cases, the goal is defined by the target keeping locations. So either it's on the tip of the rope or the corners of the cloth. And in both cases, the goal are still outside the robot's kinematic reach range. Therefore, it still requires the system to leverage or make use of dynamic actions. So actually, in our earlier work, we have been on purposely trying to avoid this kind of goal condition task because we just think it is way too hard, right? So basically, the combination of dynamic manipulation and the deformable objects make it just extremely challenging for the robot to precisely control its action in order to reach to an accurate goal. So, and in fact, it is a task that's even challenging for us or for people. So I think given a new rope or an unknown rope, it's actually very unlikely that you're gonna be able to hit a goal position within the first trial, right? So, but the good thing is that after a few trials, just like in this example, you typically will be able to kind of get closer and closer to the goal and eventually reach to the goal condition. So the question to think about here is, what do we really learn through this kind of trial and error process, right? Do we actually learn the mapping directly from our action to the full trajectory of the rope? I think probably not, right? So at least I don't think I can do this task. Or maybe we are trying to decoding the rope parameters through this trial and error process. I guess probably not either. Especially for deformable objects, those parameters are actually really hard to measure or think about. Like, for example, nonlinear densities or mass distributions. So what we really rely on, at least we think, is a good intuition, or you can call it a prior knowledge, about how we can adjust our action in order to affect the trajectory to achieve the goal. Right? So for example, it's very easy for us to understand that if we swing harder, the rope will reach higher. Right? If we extend our arm further, the rope will also reach to a further location. Right? So in this work, we actually call this intuition residual policy. So our hypothesis is that the knowledge about the change is much easier to learn and also more transferable to different ropes or systems than the specific actions or strategies we learned. So to implement this idea, based on this kind of observation, we implement this idea called iterative residual policy. So at its core is the system actually learned delta dynamics. And what they do is that it will take in observed trajectory and a delta action as input, and it will try to predict the updated trajectory after apply that delta action. And here the action, the robot action is actually represented by their target joint angle and the maximum speed. And then by sampling different delta action and then predict their corresponding trajectories after apply that delta action, then the system can select the best action that will get the system closer to the goal. And then it can iteratively refine this action until it reached the goal conditions. So note that the delta dynamics model, we actually only trained in simulation. And then, as you can imagine, for this task, it actually has a huge sim-to-real gap, right? So here is actually just an example of highlighting the difference. When we are using the exact same rope parameters in simulation and real world, the trajectory is actually very different. But our hope is that the learned delta dynamics, especially its general direction, is good enough or generalizable to real-world objects with different physical properties, even if the exact model is not 100% accurate. So here is a system in action. So at the beginning, the system will take an initial action that is actually the same for all different ropes. And then the distance to the goal is actually measured with the shortest distance along the whole trajectory. And then the policy will sample different actions and predict their delta trajectory correspondingly, and then select the one that actually has the smallest distance to the goal. And then this process will repeat until the system reaches to the goal or reach the maximum number of iterations. So that is for one rope. And in our evaluation, we try to evaluate the system's generalization capability to different ropes with different physical parameters. Again, in all the following experiments, we're going to show you the results of using the same model trained in simulation. And a lot of the ropes that we test on is actually quite significantly out of distribution. So for example, this long cloth actually has much higher air resistance when you actually swing it in real world. And this bow whip actually has a nonlinear density that the mass distribution is actually nonlinear. And for both properties, actually we cannot directly simulate it in the simulation. In the simulator we have, actually we use a Mojoco simulator which does not have, like, for example, air resistance simulated. So here I'm going to show you the resulting trajectories after the policy converges on different goal conditions. So you can see that the policy actually chooses to use very different action in order to achieve the same goal, just to accommodate different rope parameters. And we also test our system with many different scenarios. So for example, one of them is we're trying to test how well the system can adapt to online changes. So what we do is that we're going to test, after the system converge on a given goal and the rope, we're going to tie a few knots on the rope, which basically change the length and also the density of the rope. And we'll observe how the system is able to quickly adapt with respect to those changes. And we also test on the policy on different robot embodiments, which will basically change the length of the last robot link. So that basically changes the mapping between the robot's action and their effect. So the conclusion is that the policy is able to kind of adapt to different robot embodiments and able to converge to a good performance. So here is a quantitative result. Yeah, so actually on the right is a very strong baseline that is optimal action that is optimized in simulation and is optimized actually for each individual ropes. So we manually measure the rope parameter and then model it in simulator. But as you can see, it still kind of results in pretty high error. Like I think it's on average above 10 centimeter error, which really highlights the large sim to real gap for this task. While our algorithm is able to achieve relatively good performance across all the scenarios that we test on. So finally, in order to kind of test the generality of this kind of iterative residual policy framework, we try to test the same framework on a different task, right, which is the class placing task. So in this task, we try to swing a class and then want it to reach to a target configuration. And again, the target pose is defined by 9 different key points on the class. And again, the algorithm does not know the physical parameter of the class. So it still need to adapt online based on the visual observation. Okay, so here is the 2 typical strategies that the system learned that we observed. So at the first step, the system will use the same action regardless of the class and the goal conditions. And you can see that in the first case, the class actually lands too close compared to the goal configuration. And then in the second example, the class actually folded up due to the high density of the class. So based on this observation, the policy will actually adjust their action differently, right? So in the first example, the policy will increase the stroke in order to swing the class further in order to getting closer to the goal. And in the second case, the policy actually chooses to decrease the speed in order to prevent the class fold by itself. And this process will repeat until it converges or reaches the goal. So typically for this class placement task, it takes about 3 steps to converge. So as you can tell, this formulation of iterative residual policy is actually a very general formulation that is applicable for most of the repeatable tasks with complex object dynamics, right? So here I highlight repeatable because this system do require that it can be reset during the different trials in order for it to work. And I think the most important lessons we learned in this iterative residual policy framework is that instead of trying to directly learn the full dynamic model that's mapped directly from action to the trajectory, what we can do is instead learn this delta dynamics model that actually learns how the changes in action will result in changes in the trajectory. So this delta dynamics is actually much easier to learn and also potentially generalize a lot better into noisy real-world dynamics and also different object physical properties. So that is actually most of my talk, and I think here is a summary slide. If you want to have one sentence summary or takeaway from this talk, I hope you can remember that the importance and the benefits of incorporate dynamic action in deformable object manipulation tasks. And the reason is that by using dynamic manipulation, we can leverage the accelerations, the action, or in general, the dynamics in the system in order to kind of get more controls over the total degree of freedoms of the object, which is particularly the fundamental challenge for deformable object manipulation. And if you care about how to make this dynamic manipulation system work, here are some lessons that we learned from our projects. For example, we can use action primitives in order to reduce the complexity of learning action sequences, or we can use iterative residual policy in order to handle the complex object dynamics, and also potentially better handle sim-to-real gaps. And that's the end of my talk, and happy to take questions.
Yeah, that's a very good talk. If you have any questions, I think, yeah, you can raise your hand here or maybe line up by the microphone, and we'll have to repeat it for the people on Zoom. Yeah, so first question.
Thanks for the great talk. I was wondering, how did you address the out-of-plane motions of the rope while you swing the rope up?
Yeah, okay. So the question is that how we handle the out-of-plane motion for the rope. That's a great question. I think we actually do not actually explicitly handle that. We test the rope swing action, and we observe that it's mostly in plane. And if we really want to achieve certain 3D goals in order to, we can rotate the base of the robot in order to achieve like other planar motion. Yeah.
I'm curious, where do you think is the most difficult part, and like what's the limiting part? What's the part that is limiting the performance? Is it more understanding the state of the system, coming up with a policy, or something else?
Yeah, so the question is that which part I think is the biggest limiting factor for the whole system performance. I would say that there's a lot of things that can be better. I think the hardware is kind of limiting. If it can reach higher speeds, then I think the Flyngbot, for example, will have better performance. But I do feel like the state estimation, or like the perception algorithm that's able to kind of estimate the state and also represent the goal configuration for different class. I think that is another thing that I feel really limiting our current system. So for example, in the last project, we actually simplified the state estimation by just tracking key points, right? We're tracking the tip of the rope or the corners of the cloth. But if you're handling like a shirt, pants, their configuration space is much bigger and maybe cannot be really simplified with a few key points, and they may have self-fold cushions. So I think if we really want to handle like in the wild cloth manipulation, all those other challenges we need to handle.
So for the Flyngbot, when generalizing from the rectangular towels to the t-shirt, what were you treating as the corners? Was it sort of hand-coded, or was it automatic?
Yes, so the question is that for Flingbots, when we generalize from rectangular cloths to t-shirt with general garments, how we're treating compute the corners. Actually, the answer is that we do not explicitly detecting corners for Flingbots. Actually, the system learns where to grasp, and actually most of the time they don't grasp corners because they didn't learn this optimal policy where the corners are not accessible. But because it doesn't really explicitly detecting corners or manipulating the corners, so it can easily generalize to different shapes.
Thank you for a great talk. I'm curious about the iterative residual policy.
Mm-hmm.
How hard do you think it would be to start advancing to 2 targets in the same stroke?
Okay, so let me repeat the question first. The question is that for the iterative residual policy, how hard it will be to extend it to reach 2 goals with 1 stroke? That's a very hard question. I think, yeah, I actually never really think about it. I think this is probably pretty hard and maybe requires some reformulations of the problem, but I will definitely think about it. It's a very interesting problem to think about, yeah.
I think for that one, you could probably dynamically replan. That's possible.
Yeah, I guess the one of the challenge I think about now is like how the system even know whether that 2 goal is reachable with 1 stroke. I think that's probably the first thing the system needs to identify. And actually, I kind of don't know how to solve that problem. Yeah.
Well, actually, that brings me to my question, because this is basically trying to close the loop with the dynamic action, and the fact that a lot of these dynamic primitives
primarily sort of open loop and primarily also mostly one step. You can learn for a future demonstration from the past demonstration, but you cannot close the loop during execution. And so what do you think can be done to close the loop during execution? For example, let's say in sports, you see like a batter in baseball is to react to football.
Yeah, so the question is that can we do better? Like, so most of the dynamic action that I showed today is pretty open loop. And the question is that can we do better on like doing closed loop controls for those dynamic actions? I think definitely yes. I think that's definitely a very interesting direction. But I do feel that it requires a lot more requirements on the hardware. For example, the inference needs to be faster, and it probably also requires some other sensors like tactile sensing in order to get those fast feedbacks, or something that cannot be directly captured from the visual data alone. Yeah.
Thank you.
Mm-hmm.
Thank you very much.
Thank you.
So next up. Yep, your own laptop. Do you have that? You can put it.
We'll learn to that.
It's my pleasure to introduce our next speaker, Rika Antonova. Rika is a postdoc at Stanford working on interactive perception and robotics learning. She received the NSF CIA Computer Innovation Fellowship funding to conduct research on active learning of transferable priors, kernels, and latent representation for robotics. She completed her PhD work on a data efficient simulation to reality transfer at the Robotic Perception and Learning Lab at KTH, Stockholm, working at the group with Danica Kragic. And I myself can be happy to say we also collaborated, and it was a pleasure. And I'm very looking forward to this talk. Then go for it, Rika.
Thank you. So I have 25 minutes, right?
Can you join the Zoom and share?
Oh, what? Turn on Zoom.
Yeah, sorry.
Oh,
yeah. You can go to the website.
Oh, God.
No.
Oh, no.
It was to just go to this one here.
Mm-hmm. This one.
Yes, exactly. And then just share. Where did you put the mic?
Do we have power? Like
yes,
USB-C?
we have.
USB-C would be
USB-C power.
and I don't need to turn on the. Huh?
Here, you can charge it here.
Oh yeah.
This is for a different.
Oh, I see. Oh, it's okay. Hopefully my data. So I share screen, right?
Yes, exactly.
Just desktop. Yeah, I think it's.
You have enough power for the talk.
I think so. So I should be fine. I'll just have to figure out how to play in. Not in the window, but in. How do we play this in full screen? Okay. Great. I think we're good. So this will appear on here, right? Okay, I was not prepared for this.
You can.
Oh, I can minimize it.
Just.
Perfect. Yes, thank you. Where is the mouse though? Let's see the mouse. Wow, so sad. Oh, maybe it's because I yes.
Yeah, I think
Correct.
just put it out of the way.
That's it, and then I will tell them that.
It's the hybrid, you know, it's a bit more challenging.
Great. Okay, I think we're good. All right.
You can't stand in this region because that's for
I
the
have to
hybrid
stand
people.
here.
Yeah.
All right, for the hybrid people. All right, I will stand here and I won't walk too far. So previously was wonderful talk, and Shuran started mentioning that one of the difficulties is how do we represent deformables? How do we do state estimation for deformables? And this in part is what I'm going to address there, and then I'm going to talk about the scalable simulations and the real sim in that context. Oh wow.
Sorry for interrupting.
Okay, so I have additional equipment here. Oh, all right. So I'll try not to shout. So yes, so we're going to first look at the challenges with representing deformable objects. Then I'm going to talk about our approach to this, which is a distributional representation for deformables. Then I'm going to talk about what is real to sim for deformables and can we do it with these new things that are called differentiable simulators and what are the challenges there. And because we have some challenges there, we can also step back and go and see a little bit what still is there to be done with non-differentiable black box simulators, but at scale. So this has been brought up many times during this workshop that we have potentially an infinite number of degrees of freedom as compared to what we have with rigid objects. That is very hard to obtain full supervision for deformables, and you know that some equipment exists for producing this, but it's very labor-intensive. Equipment is very expensive. So we need to be able to develop self-supervised and unsupervised methods that can handle this. Moreover, as we probably all know, the occlusions and the high deformability, they make the states of the deformables look very, very different depending on not only the perspective as you would have in the rigid object, but also kind of the time step and how the object deforms. And then usually when people face these difficulties, what they would say is, okay, well, how about we embed our high dimensional challenging state into low dimensions, and great, we can, do model learning or policy learning, but in this low dimension. And what I'm going to be observing here is that the challenging dynamics, they remain in the low dimensional space as well. So tracking what is happening to the object, even if you were to embed it in the low dimensional space, would be challenging. So you can have low dimensional spaces which are hard to represent, but here's one example which is easy to represent just in the picture, which is you extract a bunch of key points. And if you use supervised or unsupervised key point methods, at a certain point in time, if you have a lot of deformation, you will have challenges and you will not be able to, let's say, track the key points across time, and there will be issues with noise as well. So we need to cope with ambiguous representations for deformables, even if we are able to extract a low dimensional state with them, and we need to be able to cope with noise. So our approach here is to use unsupervised methods that can help us reduce the dimensionality first, but then put distributional state representation onto the resulting low dimensional state, which is represented here by key points. So after we extract the key points from, let's say here an RGB image of a deformable moving, we interpret this as a sample from the probability distribution, and this probability distribution encodes the actual state of the object. Why would we want this? So one is this distributional view allows us to have permutation and variant representation. So we no longer have to really keep track of the correspondences of these key points. And for many of the applications, this would be favorable. So dropping this need to track the key points through time. And then we can also show that we would be more resilient to occlusions and noise with this paradigm. So now just to scope this term, real to sim, what does this mean? So suppose we have this example of just a robot flinging up a small piece of cloth in the air, and you can see that depending on the properties of the cloth, it would land on a table in a different way. So the real to sim problem is to infer the physical simulation parameters so that the simulated objects, they behave similar to the real objects. So of course we can change something about the friction and scale, but also here in this work we would look at changing bending stiffness and elastic stiffness, and ultimately you can change any parameters that you have available for you in your simulator. And I would notice here that with even a small change to some of these parameters, you drastically change the outcome of the shape of the end state of the object. So that's why it's a challenging problem.
All right. So just to prepare us as to what sort of hardware examples we would have with this, something like rope winding, flinging cloth in the air, maybe not as dynamic as what we saw in the previous case, but still, the cloth deforms under gravity, so you can't really full control its motion. Then some household tasks, like, for example, wiping. And here again, you can have a cloth. Here is a pretty stiff cloth that doesn't deform, but you can have much more deformable cloth as well. And here's an example with a 3D deformable, which is kind of like a tire or a hoop object. And you can have various things like, for example, assembling a belt and pulley system is an inspiration for a task like this. So we have a simulator. In this case, this is just a bullet simulator that is stylized to resemble our physical setup. So, similar colors and similar colors for background and for the object, as well as in reality. And we're going to be changing the bending stiffness, elastic stiffness, friction, and scale parameters. Again, the method is general. You can be changing any properties of the simulation. But here I've shown that already with these parameters, you can see very drastic changes in how the deformable behaves. So we're going to take a look at how we could handle that. So overall, I'm going to be talking about the method that we named ReSim ArcHS, and I'll explain overall the overview of this and the distributional representation for deformables. That is a key part here. So at first, we sample from what I would call a prior on the simulation parameters. It could be some uninformed distribution over, like what are your initial physical properties of the simulator. Then we extract the key points. There are several methods in the literature that can do it. There are some supervised, some unsupervised, but here we're not particularly demanding to what this method should do. It should just sample the key points on the object, doesn't matter where. And then we pass this through an ArcHS net layer, and I will talk in detail what this means. So here we take the key points that are unordered, and they can appear on various parts of the object, and we interpret this as noisy samples from a partially observed state distribution. And so what we do with this is we embed this into an infinite dimensional space that I will explain. And this is in order to get, as I mentioned before, permutation invariance and robustness to noise, but also a convenient distance metric. So we will be able to kind of mathematically compare the different states, how close they are to each other, and various nice properties such as the continuity of this metric and this representation. So ultimately, we're going to be relying on what is called the kernel mean embedding. And this is something that would help us to map the, find the embedding map into this infinite dimensional space. And we can represent the probability distributions in this way without the loss of information. Effectively without the loss of information. And what I mean here, and here is some literature for people who are interested in the mathematical aspect of it, is that with this mapping we can recover the expectations of all the functions in a given space, in a given reproducing kernel Hilbert space via a dot product. So if we have our mapping that we're looking for, and we have some function that we're interested in via a dot product, we are going to be able to recover the expectation of this function. So this is ultimately, could be useful for various reasons. So what we have here is a previously existing nice mathematical structure that we can work with. And so what we're going to do is this is, okay, now we, from math, from theory to practice, we're going to apply this to, okay, what happens if we actually have key points? These are a finite number of samples of our probability distribution that we don't observe of the deformable object. So first of all, we're going to convert this, abstract embedding into an empirical embedding with IAD samples. And so this just means that we're going to be treating our key points as just samples. And then with that, we could use various kernel methods in order to do the embedding. But if you're familiar with kernel methods, you would right away bring up the problem that they tend to be computationally demanding. And so anticipating this, because we want to scale right away, we're going to take an approximation with random Fourier features that will allow us to compute various functions that we need in a pretty fast manner. So what does this mean? This means that we can approximate the kernel distances, which would otherwise be computationally demanding to compute, with a dot product of two feature vectors. And these two feature vectors would contain pairs of cosines and sines with some parameters in them. And I would like to briefly explain this just from an intuition perspective. So what this effectively does is this introduces a choice for projecting onto different dimensions. So because we're mapping into an infinite dimensional space, we're not going to be able to say, put a coordinate system and just like cover all of them. There's an infinite number of them. But we randomly choose in which direction. So like this wiggly function here sort of represents the functional direction onto which we're projecting. And so you can think of it as building a coordinate system with a finite number, so basically like a finite subset of overall number of directions. Right, and here we would have some parameters like this W vector is kind of like where this direction is pointing, and we have an additional parameter which controls the stretch of this overall. And so this is how we are going to use the approximation in order to make it very computationally efficient to map these key points into effectively an infinite dimensional space, but then still have a finite dimensional representation for this that is computed quite quickly. All right, so this is our RKHSNet layer. And the interesting part of it, because in this day and age we do everything with deep neural networks, is that the reason why we call it a layer is because we can insert into any neural network whatever you like, and we can propagate through this layer the gradients. So whatever end-to-end system you're going to plug it in, it's going to propagate the gradients and going to be able to adjust these sigmas and w's, so like these directions and stretches that I've talked about before, effectively making it more, making this coordinate system choice more adapted to the data that the system is actually training on. All right, so we're done with building this layer. Now we're going to put it into this overall system and continue building it. So after we have this layer, we're processing our key points. We're mapping it into infinite dimensional space, but with this approximation. And then the output of this basically presents for us like this new transformed state of the deformable. And you can add to it the overall state of the other system. Like, for example, if you're tracking your robot, where your robot is. And then we're going to train something that has been introduced before in RSS 2019, a method that's called base sim, which is going to take the input simulated trajectories. So by trajectories, I mean this data that we have just encoded, maybe padded with where the robot is, right? So a representation of deformable and then the robot. And what it's going to learn is going to learn the mapping from the input simulated trajectories to the output of the Gaussian mixture of simulation parameters that have generated these trajectories. Because we're just doing this in simulation, right? That both this input and output is available to us. And then, so the training is just going to be done with data of likelihood. And this is just like a regular training of a mixture density network, just with these special inputs and outputs. And then after this, we're going to infer the posterior for our simulation parameters by passing through this network the data for the real trajectory of what happens when the real robot manipulates this deformable. And then what would happen is we would, over time, so let's say we have one trajectory, but we could have multiple trajectories, we would be able to get from this mixture density network the mixture distribution of what our simulation parameters should look like, but the distribution of them, not a single point estimate for the parameters. And that is supposed for us to produce all the multitude of simulated trajectories that most resemble the motion of what happens in this real demonstrated trajectory. So that's our overall system. And what I would like to show now is, okay, what is this useful for? So here is an example of the key points extracted with an unsupervised key point method. And these plots show the distance to the ground truth state. So here the ground truth we're comparing the state of the deformable by kind of like the region of the space that it occupies. And here, this ground truth, we're calling it ground truth because this is not available to any of the methods. We're not training with it. We're just like post factum looking at where the deformable object is and creating the mask curve and comparing the masks. All right, so this is our evaluation metric. And on the plot here, we're comparing BASIN, so this approach of inferring the posterior for the distribution of the simulation parameters with the original inputs. So these are just the raw key points compared and various other features that could be extracted from that. And comparing it to this base sim RKHS and base SUM RKHS, two variants which are using our representation of this embedding into an infinite dimensional space with approximation. And you can see here a pretty large difference. So we can get to the ground truth much quicker, and we're able to do this not only for this unsupervised method, but also for the supervised extraction method. So here are the key points that are obtained with supervised approach, also a little bit noisy in this case. And likewise, we can get a fairly good improvement in performance here compared to base sim with other representations. Also compared to methods which I call bulk methods, which instead of iteratively estimating the posterior, they're just getting a bunch of data, training some simple model, for example, like an MLP, or training a Gaussian, fitting a Gaussian process with a Gaussian regression, Gaussian process regression, and then outputting, the estimate for the posterior for the simulation parameters. So we can do this with a few objects in the scenarios that I shown before for this fling task, where we're tracking the state of the cloth with the key points. But again, these key points don't have to be systematically placed on any part of the deformable object. Then these are examples with the wiping task. And likewise here, this blue and black line, you can see that we're getting some performance improvement here as well. Then this is this task with the hoop. And here I want to highlight that you can see that the key point method has in part failed to track the motion of the deformable, and there's like some pretty visible noise here in the case of the unsupervised method, and we're still able to benefit from it compared to not using our representation. All right, so with this, we have a method that can do inference for the real-to-sim problem for inferring the physical parameters for deformables. And we can do it from either a single real trajectory, or we can also adapt to the changing dynamics if we, for example, use this method iteratively and we feed new data with a slightly changing situation. And this is all ready to use as adaptive domain randomization for now sim to real task if we wanted to close the loop and go real to sim and then sim to real. All right. And so transitioning to, okay, what else can we do for the real to sim? Is this the only thing? These days on our minds is the fact that, okay, these black box simulators where we don't have any gradients going through the simulator itself, okay, they're interesting, but they need some data generation part for us to be able to do something with them. So what can we do? We can use differentiable simulation to kind of speed up this process. And this is something that is going to be presented at this workshop as well. And people are very excited about this direction right now. But we want to point out that while this gives us some computationally efficiency and sometimes does give us a better precision, it also has some problems. So for example, these are some of the differentiable simulation landscapes that you can get if you kind of naively code up the simple task here. So you need an expert knowledge in order to create differentiable simulators that actually have nice smooth gradients and landscapes. And so these differentiable simulation frameworks, they require a knowledge of frequently like a custom programming language or a framework, coding up custom physics equations, some non-trivial C++ Python integration and compiling, and also custom rendering tools. So this is kind of like very much work in progress in the community. So we want to also be able to actually have simulators that are scalable and that are easy to use for us, roboticists, but also that we can bring in other people, like, for example, from computer vision, from machine learning, maybe from computer graphics and topology, and be able to kind of work with them all together using the benchmarking or simulation tools that are relevant to our tasks. And so this is one of the things that we've done earlier last year with a group at KTH, where we have a set of environments which are open source. They implement OpenAI Gym interface, and they're fast, real-time, built on PyBullet, but we have stylized them and kind of like customized them, pre-customized them, let's say, so that people are able to run them even if they're not roboticists or if they're just interested in a set of tasks and want to try something scalable, but they don't want to code out the physical simulation from scratch. And we've given some examples of how to load a very large number of mesh modifications into these environments. So for example, different garments and different data sets. For example, this 22,000 garment data set that's procedurally generated by another group. All right, we have procedural generation of meshes and some interesting tasks on here that are just for exploring what one could possibly do with, let's say, interesting tasks for exploring what one can train with reinforcement learning algorithms and how far they are from currently being able to solve these tasks. So this is an example, even after extensive hyperparameter search of what a TD3 algorithm could do. And you can see it's not really achieving kind of like the goals here. And we also built in some experimental tasks here for us roboticists that would do dual arm manipulation and something like food packing tasks. So that's what we can do with non-differentiable simulators. And our next step right now is looking at mobile manipulation. So again, bringing in the deformables here. This is a visualization of AI habitat, which there are frameworks that are emerging right now that are good for mobile manipulation and navigation and so on. And they're highly visual, as you can see here. But in this system, they didn't yet have support for deformables. So this is what we're adding. And we want to do now the next step. After the real to sim, we want to do the sim to real with the robots that we have in our lab. All right, so to summarize, I've talked about first the distributional approach to encode the state of the deformables. And next, we would want to apply this to more general problems with partially observed settings, not necessarily focusing only on deformables. Then I talked about real to sim and that we can do this with differentiable simulators. And that there's some, to-dos in the community, even though there's interest. And also, I talked about our work on large-scale training for interacting with people from other communities, but also bringing this to a more mobile manipulation setting, kind of whole room scenario as opposed to tabletop scenario. And these are the pointers to the work that I mentioned, and I would love questions from you.
Yeah, so if you have any question, maybe you can line up by the microphone and you might have to again repeat on.
Oh, okay. I will say something.
Yeah. Push.
Yeah, so this is cool. One thing about the end, really, like when you're talking about mobile manipulation as the next step, would you want to have a fully differentiable simulator, like beyond? So one thing I guess I'm trying to understand is you have to have a differentiable simulator for like this contact modeling, right, for deformable manipulation. So how do you integrate that into like an existing simulator? And wouldn't you want like maybe multiple different types of modeling for differentials?
Right. So the question was, how would you integrate multiple different types of simulators together, and maybe one of them can be deformable and one of them can be even not deformable. Not deformable, differentiable, and one can be non-differentiable. Usually the community that is interested in differentiable simulators, right, they see a lot of promise in it. So ultimately, I mean, you could in principle build, there are even right now, like the beginnings of the differentiable rendering, right, where you can, and actually, in part, that's what we're doing with point clouds, but people can do it with RGB as well. The problem is, of course, then scale. Can you really scale this? Can you really propagate enough radius through this whole thing? And I'm not sure about that. I'm a proponent of either a combination or also not leaving behind the black box simulators because they are fast. And gradients, they can be expensive, so it's not like they come for free. So I would say that for the cases where we really need precision, and for deformables, sometimes it is the case, right? Like you miss by only a little bit and, the band snaps and you don't really put it on your poles. For that, we might want a very precise model, and maybe we think very hard about that model. But for the whole room scenario, maybe you do want to keep your non-differentiable simulator that you're able to scale and stylize and everything. So in terms of on the interface, some piece that can use gradients and the other components don't use gradients, that's fine. But I think as a community, it would be nice to kind of not have the differentiable versus not argument, but more like bringing them together. I think that would be beneficial.
Thanks. Thanks for the great talk. I was wondering, when I look at graphics literature, there are some fantastic methods about like doing very disciplined measures, fantastic visualizations, and then some motion models with blending and stuff. And then we have had some speakers today doing similar things with point clouds. And so both of their goals were to have the end result be similar. And your goal is to have end sets so that they similar. So do you think you will have a distinct advantage in sample efficiency, or yours will be easier to train, harder to train, something like that?
Yes, thank you very much for this question. People don't normally notice. We tried using, for example, differentiable renderer. You would have to invest a lot of time in training that. So with, let's say, half a minute of work, I can import a texture of the object that I'm dealing with, right? And then spend a lot of time figuring out what the dynamics of this is. So in a sense, what we're saying is that in many cases, it is possible, like if maybe you don't have a whole room scenario, maybe even have a tabletop scenario, it is frequently possible to bring the photorealistic part, even if you have to kind of load something by hand. You might not need to learn it from scratch. But after you have this, as a roboticist, you still have very little, because if your dynamics is different, right, you still cannot manipulate the subject. So that's why we focus on the physical parameters. And we say that it would be great. That's why we're like all up for collaborating with people in computer graphics, computer vision, all that, right? It would be great if there is some other component that would relieve us from the need to like load this, textures and so on. But as roboticists, we feel like, okay, but then we would still need to supply what is the right dynamics for this. And that's what we're focusing on.
So one more question, sorry. Can you please give some information about what was the exact role of the RKHS and the dot product and then expectation stuff? What was the exact equation with the physical board for that?
Okay. So let's try to see if I can answer this quickly. Oh, yes. So I think the question was, so this embedding into RKHS, what is the physical intuition for it? All right. And I would say here that this is a very, very general mathematical method, right? So there is no direct mapping that I know of for like something that is related to physics of it, right? But our intuition here is in terms of the properties of what this gives. So if I go back and I say, oh, where was this? And I say, what do we want out of this? Why do we even bring this up? And there are these four things: permutation invariance, robustness to noise, convenient distance metric, and continuity, that this framework gives us automatically. And that's what we want. So it's not like we're saying that, oh, this is good for modeling some deformation model or some context or something like this, right? We're saying that it is a very general method that would take the representation that is noisy. So for example, we decided to extract key points. Oh, we could use something else, right? But that thing is, in its positional way, it's not robust to noise. If you permute the key points, then you kind of lose the interpretation of what this means. And what we're doing here is that we're bringing in this additional mathematical piece to say, okay, now with this piece, we don't need to worry about, what happens if we permute or what happens if there is noise. So that's the motivation part.
What is the convenient distance metric for? What is the convenient distance metric for your case when you are targeting that the sim and the real chip behave similarly? So what is that distance metric look like?
That's not necessarily for sim and the real. That's even just for the states themselves, right? So if the rope deforms, right? If I see the rope as sort of like its surface as a probability distribution, right? Something that is far away in the sense it has a very different shape. I should have like a natural distance metric that would let me tell that would let me say how different these two states are. And so that's what we get here, at least with the mathematical properties of it. But yeah, I don't think that you can have like a direct mapping to like 3D coordinates or something that is just more physical.
Thanks so much.
Thank you very much.
Thanks.
This brings us to the next part of the workshop, which is the spotlight session number 3.
Yeah, so whenever your spotlight talk is up, please come over here.
You're in person.
Yeah, so we're going to do it as the other two. Martina's going to play the video, and then we're going to have around 1 minute for questions. Yeah, you can watch it here.
She's going to play the video.
Michael, can I start it, or I think you have the introducer?
Okay, there's no voice on this. Okay, Martina, can you mute this video? She's gonna speak over it.
Sure. Okay, I'm playing it. Is that okay?
Yeah, just to you.
Can I just?
Yeah, if you want.
Wait, do you want to speak over the?
Yeah.
Oh, okay.
I'll just hold it for now.
Like the video is going to be.
I can restart it. Okay, now if you can start.
Okay.
You can. If you don't want to.
Can I start the
Yeah.
video from the beginning?
Yeah, Martina, please restart, and then you go.
Yeah, go for it.
Okay. We present our work, Verdo, a visual, tactile, implicit representation of deformable objects. And think about yourself cleaning rooms and cooking. Tool use are common in our day-to-day lives, and many of them deforms. So the research goal of our project is to derive a deformable object modeling that has visual tactile representation that predicts geometry in contact, and it's also compatible with common robotic sensors. At a high level, Verdo decomposes deformed shape representation into a deformation field and a nominal shape representation. Here, the nominal shape is a geometry of an object takes in the absence of external forces. This is the architecture of our model. In the left panel, we visualize the inputs of our network, which are reaction force, point cloud, and contact locations. In the right panel, you can see a shape reconstructions using our implicit representations. In the middle panel, we visualize our network, and it has two subsections. One is about representing nominal shapes using object model, and the other is about representing deformation field using deformation module D. So these are the reconstructions using a single pre-trained Verdo, and I want to highlight that Verdo can represent multiple objects and their deformations. Also, given the same contact location, Verdo can produce a unique deformation field from the tactile signatures. And also, Verdo can be generalized to unseen contact formations that are within the distribution of training data set. This is an important functionality in robotics, given a wide variety of interactions. Also, however, it's not trivial to get a contact patch explicitly. So instead of getting the contact patch, we can use a partial point cloud to perform a geometric estimations under occlusion. Here, the reconstructions at time step 0 is when the vision is missing. So I want to highlight that even when we are using the tactile only, the geometric estimation is fairly close to the ground truth. Also, our method can learn dense correspondence without explicit supervision. So for this figure, we first painted the nominal shape and tracked the painted points by applying a variety of deformations. And this property is useful for tracking a pose and relative deflection of a point during robotics manipulations. Finally, we visualize the latent space using view map projections. And in the left panel, we visualize the object code, and it exhibit
a separate and even separations. However, if you visualize the first codes, it's naturally distributed according to their bending directions and it's generalized across different objects. And finally, if you visualize the concatenated vectors, you can see that it's clustered by their deformation properties like stiffness that are not directly observed or given as input. Thank you so much.
Any questions? Then I have actually a question about the applicability of this method. You seem to focus on these like specular elastic type objects. Now we have heard a lot about linear deformable objects, ropes, or clothing. How is that extendable? Or?
Yeah, that's a great question. So, for example, if you are manipulating chains or ropes, we found that it can be elastic under gravity. So in this case, we can apply our methods to the rope manipulations.
Thank you very much. And we're gonna continue with the next spotlight talk. I think Hoshan Shi.
Yeah, right.
He's here. Okay.
I'm on Zoom. Yeah.
All right, perfect. Then you can play the video.
Hi everyone, my name is Haochen Shi. I'm a first-year master student at Stanford University. Today, I'm very excited to share our recent work on deformable object manipulation, which mainly focus on manipulation of elasto-plastic objects, such as plastic or Play-Doh. Our task is to let the robot use a parallel two-finger gripper to deform an elasto-plastic object, such as a Play-Doh, into a target shape, such as the letter X on the top right corner. It's a very challenging task to manipulate the elasto-plastic object into a target shape for the following reasons. Firstly, the real-world input from RGBD cameras is very noisy. Secondly, Play-Doh has high degrees of freedom and therefore very complex dynamics. Thirdly, the action space of this manipulation task is very large. Therefore, we propose Robocraft to tackle these challenges. The result of shaping X by Robocraft is shown at the bottom right corner. Robocraft includes 3 modules: perception, dynamics, and control. We will work through them one by one. Graph neural network needs clean and sparse data to learn a particle-based simulator, but the raw RGBD images from vision sensors are very noisy and dense. So how to tackle this problem? In the perception module, we reconstruct a watertight mesh around the raw point cloud and sample a sparse point cloud inside the mesh as the input to our graph neural network. After preprocessing the data in the perception module, we use the graph neural network to learn the dynamics and predict how the particles will move when applying an action. We demonstrate in our work that 10 minutes of real-world interaction data is sufficient for the graph neural network to learn the complicated dynamics very well. The last module is model predictive control, with the trained graph neural network as a dynamics model. We use a random sampling and gradient-based trajectory optimization method to find the robot trajectory that leads to the most similar shape to our target. Next, we will show our results in the simulation. In the simulation, Robocraft successfully shapes most of the letters in the alphabet. Some of them, such as C and E, are in fact very challenging, but Robocraft is able to figure out a good trajectory to complete the task. Next, we will show the experiment results in the real world. Robocraft successfully shapes the letter X in the real world. It accurately predicts how the Play-Doh will deform and leverages the gradient information to plan the best trajectory, which is vertical pinch combined with horizontal pinch. Here's a more challenging task: manipulating the letter A in the real world. If you were asked to shape an A, how would you accomplish the task? Although the shape of A doesn't seem very complicated, it's actually hard for me to quickly come up with the exact steps to do it. RoboCraft instead figures out a creative solution that differs from what I have in mind, but nicely completes the task. Following the question of how to shape an A in the last slide, here's a comparison between RoboCraft and untrained human subjects in both the simulation environment and the real world. You can see that RoboCraft is comparable to and sometimes better than human subjects in the tested tasks. Thanks everyone for the attention.
Thank you. Are there any questions? Yeah, please, just come here. It's easier with this microphone, so you can hear you.
Hey, great talk. I was wondering if you thought about deforming the object on a horizontal plane, like along the plane on which the thing is sitting.
So if I, sorry, can you hear me?
Yeah, I can hear you.
Okay. So the question is like manipulating the Play-Doh into a target shape in a long horizon. Is that the question?
Like you're, if I can see my hands, I guess you're doing this. What about doing this?
So sorry, can you raise your hand higher? Yeah.
So you're doing this. What about doing this?
Oh, yeah, that's a great question. So, okay, yeah, thanks for the question. It's a very great question. So, in this work, we are mainly focused on like grippings with the grippers vertical to the plane. So it's 2D grips, and in the complete version of the paper, we also explore 3D grips, like allowing the gripper to rotate on the plane. So it has some angles to the. It's not vertical to the plane. It also has some angles, and our RoboCraft is also able to deal with those situations. Those are for sure more complicated and more challenging tasks. So yeah, we mainly focus on grips like this, vertical to the plane.
One more question.
Yeah, so how accurate is your graph neural network in just predicting the dynamics? Like, did you do any experiments to see whether it predicts the deformation as the amount of deformation that actually happens in the real world?
Okay, so the question is about the amount of so the question is about how the graph neural networks work in the predicting those deformations.
Yeah.
Okay. Yeah. So, I guess empirically, I think our graph neural network is able to predict the dynamics in a long horizon very well, and also since in the real world we don't have the precise physical parameters of the Play-Doh, and it's also hard to predict those parameters very accurately. And our graph neural network has better performance than simulator based on material pooling method on the real world experiments. Yeah.
Thank you very much.
Thank you.
Continue on with the next spotlight talk by Gautam Salanto. Come here and we can play the video. Sure.
Hi, my name is Gautam Salhotra, and in this video, we present our method Deformable Manipulation from Demonstrations, or DMFT, to solve robotic manipulation tasks on deformable objects. Many everyday tasks use deformable manipulation, such as folding clothes or cooking. The problem is hard due to the difficulty of obtaining object states and predicting their dynamics, especially since environment interaction can change these properties. Furthermore, their complex dynamics and their high-dimensional configuration can increase the task difficulty. Analytical techniques succeed in certain conditions but fail to generalize with such tasks. we propose a new method, deformable manipulation from demonstrations, or DMFD, for an agent to use experts' data while learning to solve deformable manipulation tasks. It is designed to work with state and image-based observations with both 1D and 2D deformables and in both simulation and the real world. Now let us look at the DMFD training pipeline. So here we see that the agent obtains observations from the environment during experience collection or the replay buffer during training. For the state-based environments, the observations are encoded by an encoder network. Then the state encoding is passed to the actor and the critic, denoted by the blue and black arrows. Note that the observation for the actor and critic is the same as the state observation. Our method can additionally use image-based observations denoted by red. Here we see that the image observations are cropped and encoded by a CNN. The image encoding is then passed to the actor and the critic, denoted by the red arrows. However, for image-based environments, the critic is privileged because it also receives a state encoding while the actor does not. This state encoding can be seen here in the solid black arrow. Specifically, our method uses expert demonstrations in 3 ways. 1, we pre-populate the expert buffer with pre-populate the replay buffer with expert trajectories before training. We leverage an advantage-weighted formulation for the loss function, encouraging the agent to match with the expert actions in the replay buffer, but note that we add an exploration term that we balance with this loss. And finally, we employ a reference state initialization probabilistically, where we reset the agent to a state along an expert trajectory. Then we compare the state trajectories of the expert and of the agent to create some sort of imitation reward. Our method has 4 main contributions. First, to encourage wide exploration, we add an exploration term to the advantage-weighted loss. To deploy our method in the real-world settings, we actually extend this framework to the image domain using CNNs and data augmentation. Second, we introduce probabilistic reference state initialization that I just mentioned before. We do this during experience collection, where instead of always resetting the agents to states seen by the expert, as is done in RSI, we invoke this concept probabilistically to promote exploration and learning in states that are difficult to reach. Third, we create 2 new simulation environments for cloth folding with 1 robot arm. We deploy DMFD on a real robot and observe that we have a minimal sim to real gap, indicating that it can actually work in real world settings as well. And finally, DMFD outperforms LFT and non-LFT baselines on both the state and the image-based environments, and for both 1D and 2D deformables. Next, we discuss the results of the image-based environments. So for the straightened rope task, we see that DMFD beats the best baseline with image-based observations. In this rollout, our method solves the task with a clean motion, whereas the best baseline still contains a loop. In the cloth fold image task, an agent must fold a flattened cloth along an edge. We see our method beating the best baseline by folding the cloth with almost complete coverage over the 2 halves. Our new environments that we create are the cloth fold diagonal task that requires the agent to fold a square cloth along a diagonal with only 1 end effector. In the pinned corner version, we successfully fold the cloth almost completely over itself, whereas the best baseline kind of struggles with the task. In the unpinned corner version, we have similar success, and we can see that while the best baseline is able to actually finish the motion, is actually able to fold the cloth, it's not actually able to finish the motion. Here we present a real-world example or a real-world experiment on the cloth fold diagonal task with the unpinned version. But this is a variation with large rotation of the cloth. Our method is also robust to variation in the real world. So we can see these in these rollouts over here. And over the course of all the rollouts we recorded, we have a sim to real gap of approximately 6% or so. In conclusion, our method works on the state and image observations and is able to outperform LFT and non-LFT baselines. It is primarily because of the ways in which we use the expert data and balance it with exploration. Additionally, we introduce 2 challenging cloth fold environments and deploy our system on a real robot. Thank you.
Will we ask questions? Yeah, please.
How many demonstrations do you use for this task?
So the question is, how many demonstrations are used for this task? For the original paper over here, we had about 8,000 demonstrations. we managed to find ways to reduce it down by almost 2 orders of magnitude. So we're down to about 100 demonstrations. And we're trying to see for follow-up works how to reduce that further.
Yeah, I have a follow-up. So I'm wondering about if you've analyzed like the distribution of demonstration data, like if you've analyzed how many demonstrations are picking that corner or the edges but not corner. Like, have you done that?
The way we created demonstrations was we actually reset to a bunch of variations, and then we have a sort of algorithmic expert that would solve the task. That being said, we did not check how many of those expert demonstrations were for individual corners and how many were not. But this would be a great thing to verify, is to see the distribution of where the experts choose to pick into this.
Yeah, one more question.
You also used some reinforcement in the baselines. How did the reward look like for these experiments?
Yeah, actually, there are a lot of plots in that. It's in the poster, so it's going to happen in 10 minutes. You'll see the poster. In a lot of the baselines, we saw anything that did not use demonstrations was understandably performing not as well as some methods that were using demonstrations. In fact, in many of the rollouts I showed over here, the best baseline was always mostly something that used some sort of demonstration. And so the exact graphs I can show it to you in the poster, and it's also in the PDF that's in the paper.
Did you use a dense reward or only a sparse reward?
Oh, I see. Yes, it's dense reward. It's a dense reward for every step.
Dense rewards, you found that none of them were able to complete the task.
They were able to complete the task, but many a times there's a performance metric to what degree you complete the task. So for example, to what degree you're able to fold the cloth, let's say along a diagonal or along an edge. And in that sense, they were not able to perform as well as our method or some of the other baselines as well in the same, for the exact same task. So they do sort of complete the task, but it's the completion is not binary. There is a performance metric for this. Yeah.
Thank you very much.
Thank you.
Brings us to our next spotlight talk. Alex from CMU. I see, perfect. Daniel, you can play the video, Martina.
Hello, my name is Alex Lagrassa, and the title of my talk is Planning with Model Preconditions for Water Manipulation. Although deformable objects are difficult to model, model-based planning is still a useful tool for many tasks involving deformable objects. For example, pouring, shaping dough, rope manipulation, and cloth smoothing. In this example, the robot is watering the houseplant and it can't spill water on the floor. For a movement in free space using a controller that's slow enough to avoid sloshing, a simple rigid body model is accurate enough to model the effects. However, if the robot is pouring the water over the leaves, a more complex model such as a simulator is necessary to model the interactions between the water and the leaves. The task can be completed without modeling those interactions by using a special purpose model, such as a simple learned model or analytical model for pouring near the base. Our problem statement is then to learn model preconditions for various different models and also use that information to plan and use models where they are accurate. To do this, we use model preconditions, which are regions of state action space where a model is predicted to be accurate. For example, transition A is not accurately modeled by any of these models. B can be accurately modeled with a simulator, and C can be modeled using a simulator or a learned model. In this work, we learn a model using data, then learn the corresponding model precondition, and then finally plan using those model preconditions to only use transitions that are predicted to be accurate. The tool we use is a model deviation estimator, or MDE. An MDE predicts the deviation, which is defined as the distance between the predicted next state of the model and the actual next state. The model precondition is then defined as state action pairs where the probability that the deviation is greater than a maximum deviation, Dmax, is less than some small probability delta. This is the data collection pipeline we use in this work. The system is in an initial state, has some initialized models, and a goal distribution. The robot computes plans, execute those plans, and then collects two data sets, alternating left and right. The first data set is to train a dynamics model. Once the models are updated, then new plans are computed, executed, and then used to update the model deviation estimators. And the final result is a planner that can compute plans that are more reliable at test time. This is the process for learning MDs. The implementation that we use for the MD is a Gaussian process, where the observations are inputs of state action pairs, and the outputs are the deviation. This is the domain that we evaluate our method on. The state is the pose of the box on the left and the volume of both containers. The actions are to move the left box to a desired XZ pose and to rotate about the XZ plane. The tasks are box at location, which is to move the control box to a given location, and water in box, which is to pour a given volume of water into the target container. No more than 1% of the initial volume of water can be spilled. It occurs in box at location when the box hits the target box and then water spills. Model error occurs in water in box in the transport by moving too quickly and the water coming out, but also by not pouring the desired amount. Here we show the success rate in finding plans using model preconditions and without using model preconditions. On the left, you can see that the success rate in finding plans does go down using our method, and that's because it's more constrained. However, we do find that the success rate when executing those plans is much higher when using model preconditions than when not using them. In conclusion, we've shown an improvement in plan performance by using these learned model preconditions, and that deviation estimators can be used on learned models. Our next steps are to scale to larger dimensional state spaces, which are important for representing many deformable objects, and to assess the ability for this approach to improve data efficiency over existing methods, especially over predicting error in state space. We also anticipate many challenges in applying this to the real world, as data is much more expensive and the state is difficult to observe. If you're interested in discussing this further, please visit my poster or contact me. My email is on the bottom right. Thank you. Hello, my name is Alex LaGrosse.
Yeah, do we have questions?
I have a quick question. I'm curious about the choice of the Gaussian process for modeling. Did you consider any alternatives, or did you right away think this was the right measure?
Can you just repeat it?
Yes.
Yeah, which microphone?
This one, the big one.
Thank you. I've actually used many different implementations for them. I tried using nearest neighbors. I used the neural net. I tried representing the uncertainty in the neural net. GPs ended up being the easiest choice. They're data efficient. The ability to, sorry, I forgot to repeat the question. The question was, why did we choose a Gaussian process as the implementation, and if we considered other models as well? And the answer was data efficiency, having a well-defined and easy to work with representation of uncertainty. And that made it easier to select both what mean we want and balance on the probability of the error being below a certain threshold. And does that answer your question?
Yeah.
Okay, thank you.
Should I come up to the mic?
Yeah.
Okay. Yeah, so the question is, it seems that because there's such a huge variety of geometries and leaves and houseplants, it would be almost impossible, even in like the ideal setting, to water 100% of them without spilling any water. What do you think the upper bound percentage would be in the ideal case that like you could hit for this kind of problem? Because I've not even thought about this problem before, and so it's kind of an interesting space of things to think about with leaf geometries and such.
Do I need to repeat this one?
Yeah, just put the limits on.
I don't know, I mean, is it repeated on the mic? Okay. The question was if what sort of success rate would be acceptable for a watering task, and how to address the difficulty of modeling the wide variety of leaves. Is that an accurate representation? I think the desired success rate is very user dependent. question. So that would depend on what the requirement is. So for example, if a little water is okay in a house, that would be specified by the user. I think that getting a high probability is not out of question because there's ways of watering that doesn't require it spilling on the leaves, for example. And that's one thing that I hope to address in both reasoning about model error and in incorporating that into planning. Does that answer your question?
Thanks.
So, yeah, thank you very much. This brings us to our last spotlight talk from Rika. Oh, it's online, okay. So we have 2 people to answer questions, and let's play the video.
We present DiffCloud, real-to-sim from point clouds with differentiable simulation and rendering of deformable objects. First, we will describe DiffCloud inputs. Our hardware setup consists of a Antonova robot and 2 RealSense cameras, one mounted on the side and one overhead. Next, we manipulate deformable objects and record point clouds from both views. Using knowledge of the geometry, kinematics, and meshes of the Antonova robot, we also mask out the robot from point cloud frames such that only the deformable object is captured. The merged point clouds serve as input to DiffCloud. The goal is to estimate unknown physical parameters of the object, such as stiffness and mass. We use a mesh-based deformable simulator. In simulation, we execute the same trajectory on the deformable object which was performed on the real robot, resulting in a deformed state. From this state, we differentiably sample a point cloud from the surface of the mesh. Next, we take the loss incurred between the simulated and real point clouds. Since the simulator and the point cloud sampling procedure are both fully differentiable, we can propagate the gradients to the estimated simulated parameters and perform updates. We repeat these 2 steps until point cloud alignment is achieved, indicating that we have found simulated physical parameters that fit the observed real point clouds. We evaluate DiffCloud on 2 real scenarios, starting with lifting a cloth off a table. We show the real point clouds for a stiff, lightweight paper towel and a heavy, collapsible polka dot patterned cloth. On the left is the target input point cloud sequence, and on the right is the result of visualizing the simulated cloth with the parameters found by DiffCloud as point clouds. We find that the inferred parameters produce point cloud alignment between real and sim, noting that DiffCloud correctly learns the shape retention and self-collapse behaviors of the paper towel and polka cloths. Next, we move on to fold. Similarly, we show the trajectories for 2 cloths of very different properties. We note that the fold scenario exhibits a high degree of self-occlusion and partial observability. Nearly half the cloth is not apparent in the point cloud due to the resting half of the cloth being indistinguishable from the table surface. Still, DiffCloud finds parameters that fit the observed trajectories and learns the shape retention versus self-collapse properties. We also evaluate DiffCloud on 2 simulated scenarios using synthetic data as input, band stretch, and vest hang. In these experiments, we will visualize the initial guess for parameters that DiffCloud starts from in black, and compare this against the final optimized parameters in blue. 2 target sequences for band stretch are shown in green, where varying the band properties affects distance traveled upward along the pole. DiffCloud successfully finds these parameters, shown in the blue column. On the right, we see that DiffCloud starts from an initial guess for parameters shown in black, which diverges from the target behavior in green, but eventually converges to optimized parameters in blue, resulting in alignment with the target. For vest hang, we show a highly deformable and shape-retaining vest, with the properties affecting the resting pose of the vest on the pole. DiffCloud learns to infer parameters that describe these behaviors. Thank you so much for listening, and for more information, please feel free to check out our website or stop by our poster session later today.
Any question? Yeah, please ask.
Yeah, so the question is, do you need to learn the parameters of the simulation for each object separately, or can you learn a generalized model that can represent maybe like multiple shapes of deformable objects?
So that's interesting. In this work, right? The question was, can you learn a generalized model that would kind of infer the properties of multiple objects as opposed to a single object? So in this case, we tried for a single object, and that was specifically to infer the parameters of infer the parameters so that you match the motion of a given object. It's an interesting question as to in what cases would you want such a thing, right? Because you wouldn't be then manipulating a given object, right? You would be like manipulating an abstract group of objects or something like this. So you can certainly do it very simply by just feeding a lot of data from multiple trajectories of different objects. You would you would find something. The problem, of course, is what happens if you have objects for which some group of parameters would be optimal for one of them, and then another group of parameters would be optimal for the other one. So for that, right, I would refer you to what I was saying before about treating these things as probability distributions, both on the inputs and the outputs. And so then you could certainly do this. However, we did not do it in this particular work. And I think with differentiable simulators, a lot of the focus is, as I was mentioning before, on can it be precise and can it offer more precision than what we can have with the black box. So like a lot of the motivation is really for, can I match the behavior of this particular object, not just a general clause. And that's why the focus is on that.
Right, thank you.
So is the differential simulator, is it explicitly learning parameters about the object, like its level of tension and weight or something? Or is it explicitly learning to render based on those parameters?
It's explicitly learning the parameters, so you would have differentiability with respect to some parameters, and those are the parameters that you would be adjusting, right? And what do you mean by implicit? Oh, sorry, Andrea. So the question was, whether the learning process is learning explicitly to infer the parameters of the simulator, or is it learning something implicit? And so I'm asking, what is your idea for this?
Yeah, like if you had like a piece of rope, like the weight of it will affect how it gets simulated. Like, is the simulator learning sort of interpretable properties of it?
Yes. Yes, it is learning interpretable properties in the physics that you have coded for, okay, this rope is moving and the physics parameters for its motion for the model of that. Yeah.
Thanks.
One more question?
Did you face the issue that multiple sets of parameters can fit a particular motion?
That's interesting. Let's see if Priya is around. Maybe she
repeat it for me.
Yeah, I'll repeat it. So, so the question was, did we face the issue? Oh, can we have her on screen? But
she speaks up.
Oh, she speaks up. We can hear her. Yeah. Did we face the issue of what happens if you can have multiple parameters that would be a good description for the motion of the, to match the properties of the object?
Yeah, that's a great question. So we did face this issue, especially like since we're considering the parameters of stiffness and mass, there are like some scenarios where high stiffness could overcompensate for low mass and vice versa. But I think in this work, we're mainly concerned with not so much like finding the exact stiffness and mass parameters that correspond to like the real quantities on the physical object, but just learning simulated models that could fit the real behavior by finding really like any valid combination of the stiffness and mass that would yield point cloud alignment. But it's definitely an interesting question. And in follow-up work, it'd be interesting to consider maybe different sets of physical parameters like friction, mass, and things that don't necessarily have or yield like similar deformation results on the objects themselves.
Yeah, thank you. And a follow-up question, does like the same set of parameters generalize to like many different motions of the cloth?
So in general, we did find that one thing that we didn't do in this work, but we would definitely want to evaluate in follow-up work is like whether, for example, like the found trajectories from lift would then yield comparable behavior on the fold task. And we did see some general patterns like the stiffness and mass parameters found from lift and fold yield similar results across tasks, but may not be like exact parameter matches. But definitely like fitting parameters based on one trajectory and then evaluating across tasks is something we'd like to do going forward.
Thank you very much. That concludes the spotlight session. So that means we now have the coffee break and the poster session outside the room, and we're going to reconvene here at 16 sharp. 4 o'clock, sorry, 4 p.m. Yeah, see you then. Yes, yes, yes. Yeah, I think. Are we using your laptops? Yeah, I can just keep up here. So you can play the slides material for the stream.
Okay. I didn't get anything.
How are you all? Nice to meet you. Thanks for happy to help. Yeah, no worries. Whoa. How did you update this? Nice. You're very fast. I'll have to make fewer jokes about not looking like the picture. Then. Yeah, that's okay.
What else? What has quit?
Yeah. We just tested. We can share. So it's HDMI.
Yeah, I have a
adapter. Yeah. You can keep playing the videos, Martina.
I just noticed that I had a mistake.
So if you click share screen, you need to mute. Martina, can you stop sharing for a second?
Got it. Share screen. You know that
This is feedback audio.
Okay, Martina, can you hear us?
Yes.
Okay, can you see if the mic cover is out?
Do you hear any feedback from that?
Yeah, I can hear you. I can hear you. I hear myself.
So how do we fix it?
And also
has it been happening all day?
The sound of the computer.
Sure. Michael, I think there's some. He's saying that there's some issue with feedback from the projector. I don't know if it's like something.
Yeah, let me check.
Maybe it's a setting.
We're muted here. Yeah. We have to restart this guy. So now the feedback is off, right? But that was over this. Because you don't have any speak output, right? If you.
Yeah, it's muted right now.
Okay, okay. Okay, if we plug this in again, and then we test. Is there feedback again? I don't think so.
How is it?
Is the feedback?
Speak up.
Yeah, is the feedback there or not?
Okay.
Okay. So that seemed to work. Then, Martina, are you there?
Yes.
Okay, then yeah, Martina, you can introduce the next part.
Okay, cool. Thank you. Okay, so it is my pleasure to introduce our next speakers. They are Alan Kuntz, that is here in place of Tucker Hermans, and Isabella Huang. And they are from the University of Utah and University of California. In particular, Alan is an assistant professor in the School of Computing and Robotics Center at the University of Utah, where he leads the Artificial Intelligence and Robotics in Medicine Lab. Prior to joining as faculty in Utah, he was a postdoctoral scholar in Vanderbilt Institute for Surgery and Engineering and the Department of Mechanical Engineering at Vanderbilt University. And he completed his PhD in computer science at the University of North Carolina at Chapel Hill. While Isabella is a PhD candidate whose research focuses on modeling and control with soft materials in robotics, she is advised by Rosina Baishi at the University of California, Berkeley, where she develops soft tactile sensors for use in physical human-robot interaction. She is also a collaborator with the NVIDIA Seattle Robotics Lab, working on simulating and predicting the physics of grass planning for deformable objects. And prior to graduate studies, Isabella completed her undergraduate degree at the University of Toronto in 2017. So thanks again for being here, and the floor is yours.
Thanks, Martina. Good afternoon, everyone. I'm really happy to be here along with Alan to present our work today. And before I begin, I just want to acknowledge all our collaborators without whom this would not be possible. Okay, so in this talk, we want to cover the following topics in deformable grasping and manipulation. First, we want to talk about why we even need to use simulation when studying interactions with deformables. Then I'll show our work in DefGrasp Sim, which is a tool for simulating deformable grasps. Along with that, some comparison of simulated to real-world results. I'll then highlight some key shortcomings of FEM-based simulation, in particular speed and differentiability, and show how we're currently using deep neural networks to act as an alternative to FEM. Then we'll talk about work in deformable shape matching using DeformerNet. And so you can see these topics will be split into two groups. I'll be discussing the application of grasping, and then Alan will be covering DeformerNet for manipulation. Okay, so when we think of grasping 3D deformable objects, we as humans can have very different strategies based on the object and the task itself. For some examples, let's say we're picking up delicate fruits from a bush. In this case, we want to avoid grasping it such that it imparts too much deformation because this would bruise the fruit permanently and it wouldn't sell. And when we're grasping deformable containers, it's possible that you might crush its contents. For example, I would avoid grasping along the face of this Cheez-It box. But if the box were rigid and doesn't deform to my grasp, I could just grasp it any way I want. Another example is robotic surgery that includes manipulating soft tissues. We want to grasp the tissue in a way that will allow us to maneuver it in the way we want, for example, to stretch it or to perform processes like suturing. And lastly, sometimes the grasp just doesn't even matter. In fact, it's way easier to pick up the soft teddy bear than to pick up a rigid version of it, because a soft bear can deform to the gripper and actually improve contact. So it became clear to us when thinking about this topic that choosing best grasps for 3D deformable objects is object dependent and task dependent. And since these grasp goals are so diverse, we wanted a way to sort of evaluate grasp on a whole range of objects and therefore launch a full-scale simulation study. So this full-scale study is, we believe, best performed in simulation for many reasons. As we've heard a lot today, deformable objects have infinite degrees of freedom and are described by continuous field quantities such as deformation and stress fields. These quantities, more importantly, are basically impossible to measure in the real world and in real time. But this can be done in simulation. So simulation leads to safe experiments that are repeatable, resettable, and easily accessible, especially during a pandemic. So we present DefGrasp Sim, which enables automatic and systematic evaluation of grasp outcomes for grasps on general 3D deformable objects. Our contribution here is twofold. First, we release a new data set of 3D deformable objects, which is one of the largest in existence at 34 objects. Of course, this is tiny compared to the millions of rigid object models that are out there, but it's a good start, and we hope the community will also add to it. Secondly, we then use the NVIDIA Isaac Gym simulator that simulates deformable interactions using 3D FEM, the finite element method. And using this background, we create a code base that allows users to run grasp experiments on any object of their choice. Let's look at that in a bit of detail next. And this is what using DefGrasp Sim looks like in practice. First, you can choose any object, either some from our existing data set or a custom model of your own. Then you can choose to run any of these grasp experiments on that object and record the outcome of that grasp. For example, some of these outcomes include the final stress field of that object after grasping, or the final deformation field. For example, maybe the total deformation that the shape undergoes during reorientation under gravity, or simply whether it was picked up or not. And so these different metrics can be chosen based on the object and whatever task you're interested in. Now, I want to mention that users can also design custom grasp measures that they want to look at that might not be included from our code base, because at each time step, a full state tensor is actually made available to the user. This full state tensor includes full nodal positions and velocities, element stress tensors, as well as contact points and contact forces. And to our knowledge, this is the most complete per time step state tensor that there is out there for 3D deformable objects. So we're happy to see that this ability to design custom grasp measures is starting to be used in the community already. For example, in this recent work by Lei et al. And his team in predicting grasp success. Now, the next natural question to ask is, well, do these simulated experiments have good correspondence with the real world? To answer the question, we performed a few pilots into real studies where the material parameters we feed into our GraspSim simulator are only roughly estimated based on typical material values. So that's to say there's no fine tuning. Okay, so let's see some examples of estimating the stresses imparted on a piece of tofu during grasping. We see that there are qualitative similarities in shape when doing in the real world on the left versus in def GraspSim on the right. As I mentioned before, you're able to actually extract the stress field of the object at every timestamp. And according to existing literature, we see that permanent breakage can happen at around 3,000 pascals. We then see some similarities between the stress fields predicted in def GraspSim compared to what shows in real world. So for example, grasp A didn't impart any breakage, but in simulation, we predict that grasp B would, especially around the edges of the gripper. And indeed, that's what happens. And the third example of another grasp on this tofu is along its long axis, and these regions of high stress are shown in red. So we see that breakage indeed occurs along these areas, and even though we don't have the full, let's say, state tensor of this real piece of Trader Joe's tofu, we can see that the qualitative results are similar. We also have some experiments testing deformation of picking up a rubber tube, for example. And in our paper, we do have some additional experiments on stability as well as volume changes of bottles, if you would like to check that out. All right, so this tool is pretty promising and I believe useful, but there is one major shortcoming, and that is that it's slow because it does use a computationally intensive finite element method. So in fact, one of those grasp tests can take as long as 5 minutes, especially if the object mesh is dense. For example, when you have very complicated geometries with features that you want to preserve. And so we were looking around for solutions, and we found an existing DeepMind paper that tried to solve this very same problem in 2020 by representing a physics simulator, an FEM-driven physics simulator, as a deep neural network. So I'm going to just give an overview of that work. I think it can be relevant to some of us. So this work, basically the key insight is that meshes are natural representations for structured objects, including 3D deformable objects, and therefore we should also represent objects as meshes for deep learning. In the past, objects have often been represented as point clouds, and popular machine learning methods that work on point clouds such as PointNet and PointNet++ have been very successful, but there is no inherent connectivity between points, unlike in FEM. So on the other hand, as opposed to point clouds, meshes are collections of connected vertices and edges that don't change over time, that clearly define the shape and structure of an object. And these meshes are the go-to representation for computing dynamics using numerical techniques. For example, in our def GraspSim work, all deformable objects are indeed represented as meshes and not point clouds. Now, MeshGraphNet aims to solve the problem that we were facing, which is, that scientific simulations like FEM are expensive, so can we use mesh-based graph structures in machine learning to do predictions instead? And they found that the answer was yes. So they were able to train a one-time step prediction, where at each step, the physical system is represented as a graph. It's then encoded, processed, decoded, and then these output features can be used to directly calculate the next state of the system. And this is just rolled out over the course of a trajectory. So I will show an example of the power of this network in predicting the deformation and stress on a 3D plate when it comes in contact with an obstacle. So on the left is the ground truth generated by FEM, and on the right is prediction that DeepMind did using MeshGraphNets. So we wanted to actually modify this architecture for our application in 3D deformable grasping using a gripper. This would involve the use of grippers that are realistic to what we see in the real world rather than arbitrary obstacles. And the hope is to eventually use this as a grasp planning module. Okay, so I'm going to show some example results for how we've tailored this architecture for 3D deformable grasping, where the ground truth comes from our simulations in DefGraspSim. Specifically, when we're grasping 3D deformable objects, the most important quantities are stress and deformation fields. So that's what we are focusing on predicting. So we can get these quantities in ISAAC-GIM as that full state tensor that I mentioned, but we want to see if we can get similar results using machine learning instead. Now, there are two main benefits of using this neural network. For one, it's much faster. A full rollout or a whole trajectory of squeezing the object until until enough force is applied for safe pickup takes around 1 second using mesh graph nets and 1 GPU. This takes maybe around 2 minutes using ISAAC-GIM. So now, instead of doing grasp planning offline, where we would evaluate a bunch of candidate grasps first and then choose the best one, there's now potential to do this in an online manner. Secondly, neural networks are differentiable. Thus, we want to use it to actually optimize an initial grasp pose to produce the best grasp outcome, whether that be minimizing stress or maximizing deformation, whatever that might be for you. This sort of differentiable optimization is not something we can do in ISAAC-GIM. Okay, so some examples of using mesh graph nets for prediction are shown. This is an example applied to a grasping scenario where those two solid rectangular prisms are the two parallel jaw grippers. So in this visualization, we plot the nodes of the object's mesh, which in this case is a simple rectangular prism, just like the tofu. And on the left is the ground truth response of this object generated by DefGraspSim. You can see that as the gripper squeezes during the trajectory, the deformation increases, and so does the stress, where the nodes on the object are colored according to the stresses at that point. And on the right is the prediction that we generated, and you can see it's very similar. We also extend the application of mesh graph nets to near rigid objects, for which we say that deformation is negligible. And this is motivated by real-life grasping scenarios, because when you're grasping near rigid objects, we can't just command the gripper to close until some fixed distance. Because if they are quite rigid, that could actually damage the object and the grippers, right, if the object is stiff enough. In reality, force commands are more practical. That is, you can tell, or you would like to tell a robot to squeeze an object until a certain ideal total force is achieved, at which point then you can feel free to start picking up the object. So we changed also the network architecture to allow for kind of the external action to be the total gripper force instead of, let's say, change in gripper position. And as you can see, the resulting predictions for stress imparted on the object are very similar from the ground truth compared to after training. We also take advantage of the differentiability of this neural network. And here's one preliminary example, but we can start to use it to optimize or refine an initial grasp pose to a better one according to some metric. So in this particular example, we're trying to refine the grasp pose so that it maximizes the resulting stress of the object. So through this optimization process, the initial gripper pose is in blue, and it eventually becomes shifted up to a pose in orange that you can see ends up being localized around the edges of the prism, where because curvature discontinuities are higher there, this typically would actually lead to higher stresses. So in practice, though, I think we rarely want to maximize stress on an object unless you're really trying to break tofu for some reason. Yeah, you probably would want to do the opposite, but this is a great example of what we hope to be able to do with the differentiability of the network. Okay, so that was for my part for grasping. I would love if you have any questions later on. You can feel free to contact me if you want to also get started with DefGraspSim. But now Alan will take over for manipulation.
Okay, awesome. You may recognize me from the acknowledgements slide earlier, which was going to be the extent of my involvement in this talk before last night. So Tucker couldn't make it. He had a flight that was canceled, but luckily I'm a collaborator on the project he was going to talk about. And much more importantly, my flight was not canceled. So here we are together. All right. A bit about me. I'm an assistant professor at the University of Utah in the Robotics Center, but more notably, before I was a computer scientist, I was a paramedic on an ambulance in a very busy 911 system. So this is my second career, and that kind of shapes my applications in these kinds of things. And so I'm extremely excited to talk to you today because one of the things that I'd like you to take from this is an application space for a lot of your methods and your techniques that's very important and that I am very passionate about. So we're in the middle of a pretty big crisis that you may not be aware of, and that is that there are not enough medical providers, and it's getting worse, much worse. And this is true of providers at all levels of healthcare. So from EMTs and paramedics in the pre-hospital setting to nurses, physicians, specialists, and surgeons. And the pandemic has made this much worse as well. So I'm going to talk about surgeons for a second. And specifically, if we look at cardiothoracic surgery, a pretty important branch of surgery, many would argue, the demand for these surgeons is going up. And that's because we're an aging and growing population, right? So many of us, there's more of us than there used to be. We're aging and we're becoming in need of these kind of specialized medical interventions, right? And because of specifics about the distribution of this aging population, the need for surgeons is actually growing at a rate greater than the population is. Here's the problem, though. The number of surgeons is not. The number of surgeons is in fact declining, and it's projected that by the year 2035-ish, the caseload per surgeon will more than double what it is today. This is an issue, right? Something that we need to address. So there are a lot of ways that this needs to be addressed. We need to create a healthier population. We need to recruit more surgeons. We need to make their lives easier, but I don't care about any of that because I'm a computer scientist, right? And so, and a roboticist, I want to automate pieces of surgery, right? How hard could that possibly be? So I'm about to show you a video of surgery, robot-assisted surgery. If that bothers you, feel free to turn away and I'll tell you when it's over, okay? So here we have a video of a surgeon teleoperating a Da Vinci surgical robot to remove a lobe of a lung. And I want you to look at this video and think about the challenges that this specific application introduces to automation. So there's a bunch of them, right? One, we can look at the perception challenges, which are kind of unique to this space. Everything's kind of the same color, right? It's this gross gray pinkish color. Everything kind of looks pretty similar compared to at least when we think about manipulation in like industrial settings. And so that makes feature matching hard, increases the computer vision challenges. Everything's shiny, right? And so we have this specular effect that makes things difficult. Structured light doesn't work as well, for instance, right? We don't have a lot of data, right? Our data in medical robotics is frequently pathological in nature. That's a really funny joke. If you were a medical robotics audience, you'd be laughing a lot right now. We have pathological data, right? We don't have a lot of it. You can't collect it actively, right? Good luck signing somebody up to let you go poke around in their body just to train some model, right? These are the challenges. And so the ones that I specifically want to talk about today are the fact that we don't have a lot of data, or we can't get a lot of real world data, and everything's deformable, right? As you saw, almost all of this was deformable. If that focus surprises you, you're in the wrong place, or I'm in the wrong place, I guess. But either way, so let's talk about deformable object manipulation in the medical context. So before we can manipulate deformable objects, we have to represent them, right? And as we've heard over and over today, this is very difficult, right? These are infinite degrees of freedom things to describe in a true way. We have these high dimensional representations. We need to choose from among these. I told you that the vision challenge is very difficult. I'm going to pretend that other people have solved that, which is what I like to do. And we're going to get our geometry in the form of point clouds. Now, the good news is that a lot of the smart people working on perception in medical robotics are producing sensors that give us point clouds. And so this is kind of a natural way to start to think about sensors in medicine. Okay, So we're going to focus on point clouds in this work. So this is a paper that Tucker and I's student Bao is presenting later this week on Thursday, I think. And so just to plug to that, go talk to him in his poster session. It's going to be awesome. Okay, so we want to manipulate deformable objects in medicine. We want to do it in such a way that we're leveraging kind of the sensing modality that we're getting. And so let's think about it in this way. This is the kind of sub-problem we're going to solve here. So the first thing is we're going to take our current shape of some deformable object in the form of a partial view point cloud. We're going to take some goal in the form of a point cloud. We're going to figure out where on this object to grasp it with some robot-assisted surgery device. And then we're going to, in our work, take a shape servoing approach to kind of incrementally move our current state in a point cloud representation of the deformable object to that goal point cloud. So how do we go about selecting this manipulation point? We've heard about some principled ways to think about this, and our future work is taking a much more complex approach to this, but we wanted to focus on the manipulation. And so in this work, the manipulation point selection is kind of a heuristic-based approach where we say, well, if you can match some key points between your starting codes and your goal, the intuition is the things that move more should be closer to where you grab them. It's a starting point. It seems like a reasonable place to start. That's where we went. So that's how we select our manipulation point. Now, how do we represent then the state of these deformable objects that we're getting from the point cloud in a way that we can then computationally reason over in this shape servoing way, right? And so that's the next piece of this. And so what we do is we embed this point cloud in some lower dimensional latent space here using a sequence of point conv layers in a neural network, right? And so this gives us a lower dimensional representation that simultaneously, because of the training process, encodes features that are relevant to both the shape, structure, and manipulation of these objects, but is low dimensional enough that we can reason about it. So using that, we kind of embed this in a shape servoing control loop at a high level. So we take our point cloud from a sensor, we run it through this model that we call the former net, and that gives us an incremental action for our robot to take, moves us a little bit closer in this latent space toward our goal shape that we want, and we repeat this process. And so here's what the full model looks like. We have our feature extraction that we just talked about a little bit, that we get our current state from, as well as our goal state. So we embed these into the same latent space and we look at the difference. And then we have another model or another piece of the same model that takes that difference and has learned how to manipulate the gripper of the object in order to move the robot such that the deformable object moves a little bit closer to where we're trying to go from a deformable object perspective. So how do we overcome this fact that we don't actually have the ability to get a lot of data from people, right, when we're deforming people, which is really the point. So we're leveraging large-scale simulation to take steps toward that. And so this is what it looks like right now. We've got a simulated surgical robot over there on the right. This is an older version of that robot that you saw from the video. And we are placing in front of it in Isaac Gym a diverse set of shapes with different geometries, sizes, and stiffness properties, and letting it, in the way you all do, wiggle it around, right, for a while in simulation. And then from this, we get our training data that we train our method with. And so I encourage you to go talk to Bao to get the actual specifics on the results, but it works really well. So here we have objects that were not seen in the training being manipulated to goal shapes that were not seen during the training, obviously on a bunch of different geometries. So this is it working well in simulation, but how does it work well in the real world? And so it turns out that at least the ways that we've tested it, it works really well in the real world without us having to have done any kind of fine tuning or other changing of the method to get it to work in the real world. So here we have a robot that's not in the scene manipulating a laparoscopic tool that is in the scene that is grabbing this piece of foam. And here it is using our method manipulating the object, which is this goal point cloud that you see in red here. So in addition to that work, and this is now beyond the work that we're presenting at this conference into kind of some of the next steps that we've begun to take, we're also looking at bimanual manipulation for these as well. So the question you should be asking me is, how in the world are we going to get a goal point cloud in a real setting from like a surgeon that's trying to use this to help them, right? That's an excellent question. I'm glad I brought it up. So that's the key here, right? There's a lot of advantages to having this reasoning about the current state and the goal state kind of in this same modality that we're leveraging right now, but it does present this challenge, right? And so one of the things that we're taking steps toward is, well, if on a task-specific basis, you can come up with a low burden way for a non-expert human user to specify some parameter that can then be easily translated into a goal point cloud. You can create that small task-specific piece and then leverage our method on the back end that's not task-specific to accomplish a lot of things. And so that's where we're going with this, at least in the kind of near term, right? And so the first thing that we've seen to make this work is let's have a human define a plane. Now, there are other ways to get a robot to move a deformable thing to the other side of a plane, but the point here is that this is just one instantiation of this kind of interface translation layer, right? And so here we have a plane, and we have kind of a method that transforms the current point cloud into some point cloud that looks like what the object would look like on the other side of the plane in some way, and it's capable of using our method that reasons about the sequence of point clouds in a goal point cloud in order to get there. And this works both in simulation and on the real robot. And the medical application here is something called retraction, where we're thinking about moving a piece of tissue aside so that a human surgeon can then do the complicated pieces to whatever's underneath it, or visualize what's underneath it, things like this. Right? This is a common task in robotic surgery. So this isn't the only thing we're thinking about. We're also thinking about the task of anastomosis, which is connecting two tubes together, and how would a human specify what this connection should look like. Here we've we're taking the approach where a human could specify a space curve that they want the two tubes to kind of look like when they're joined. And here we kind of swell that curve into a point cloud. That curve could be gathered from a 3D mouse or from the actual robotic device that they're using in surgery to kind of trace this curve in space where there are not tubes, and then have the method kind of join the tubes there, right? We're also looking at wrapping tissue around other objects, for instance, like instant placement and things like this. And so here, all of these are the same method underlying it, right? This point cloud reasoning shape servoing. This is just 3 instantiations of like heuristic ways that we've used more human, low burden ways to kind of specify goal representations that we then translate into this point cloud goal, right? Anyway, please work on medicine. It's all deformable. It's all super important. Come talk to me, talk to Tucker if you're interested. If you want a medical slant on things, let me know. So that I think is it for us, right? Awesome.
Thank you, Isabella and Darren. And thanks a lot also.
Please line up by the microphone or ask online.
Okay, great. So first of all, fantastic talk. I honestly have a lot of questions, so I don't want to take up too much of my have to discuss them later.
There's more time.
Okay, but
later, I mean, not now.
So first for the grasping stuff. So 2 questions for that. There's been a growing amount of interest in using climate and soft grippers. In the work that you've presented right now, are you assuming a rigid morphology, or are you assuming a very specific morphology that doesn't get any rigid morphology? Are you assuming a parallel jaw grip? Yeah.
So the question for GraspSim is, can this basically support compliant grippers? And also, am I assuming that the grippers are rigid and also of a specific geometry? Currently, Isaac Gym does not support soft body to soft body interactions, but there has been existing work using Isaac Gym where the grippers do have a compliant pad, but the objects are rigid. But you can't really have it both ways right now. That may change soon. And the parallel jaw gripper that I'm using is, it's kind of stripped of all defining features. It's loosely based on the panda hand, but it doesn't look exactly like that. And the reason for that is to, just like represent a general parallel jaw gripper. And this can definitely be tailored to other hands as well. You can upload different like URDF files to describe whatever hands you may want. So that might even include like multi-fingered hands if you'd like.
The other question was, so first of all, thank you for moving away from SGM. I really don't like SGM, and I don't like it either.
I didn't say I don't like it.
Okay, but so in the learning, in sort of this, using going down feet from that path, one of the concerns I always have with those kind of methods is what happens to things that are not in the source data set. Did you find that to be very much a problem in the kind of objects you're working with? And if so, or if not, just want to hear a little bit about that.
Okay, so the question is generally about generalization of deep neural networks and whether like my results would apply to maybe objects that I didn't see during training. Yeah, definitely. I think with a broad enough class of training objects, you should expect some generalization to those that do have similar features. I haven't tested the bounds of exactly how different objects can be, yet still generalized. But I think that is a challenging question and an open question in many ways. Right now, we're sticking to maybe like more simple geometric objects first, just to scope it out. We do see generalization from prisms to other shapes of prisms, but what about curved edges or shells, in fact? So I think as long as you have enough objects of each of these categories of geometries, then the hope is that you will see some generalization. Yeah.
Wait, I think we have one question online, so I want to make sure that we're able to get to the online question.
Yeah, so the question online is, does the Isaac Gym simulation actually simulates the rigid gripper grasping, or does it use fixed points, anchor points?
Do I have to repeat that or no? Okay. It does not use fixed points to get there. It actually does simulate the dynamics of the rigid gripper. So you would have to define like the inertial properties of every link in the URDF, for example. And it can also do built-in, for example, position control, velocity control, torque control. So in that sense, it is a robotic simulator because you can do control of the actuator.
Thank you. Let's do one more question because we are a bit running out.
Sorry, let's take one more question just because we have to get to the next speaker.
So, but Alan and Isabella are around.
Yeah, we'll be around.
Question for the professor. I was wondering, previous work on medical robotics basically looked at different flavors of CPE, coherent point trims, with different regularizations, basically non-rigid registrations. And your work does not look at that. So I was wondering, like, what advantages you have? You're probably much faster, but how accurate you are versus that and stuff like that.
Yeah, so I think that that's tackling a related but a little bit different, distinct problem, right? And so in the registration front, we're really looking at, well, I have some existing model of the anatomy. I want to deform it such that it's like what I'm looking at, and then that allows me to reason about the knowledge I had in the medical imaging, for instance, to then make decisions based on what I see. So we're just moving things, right? The things that are under the surface that we would then access, that we need to have that registration from the imaging for, we're not there yet. But once we start doing so, hugely important, absolutely.
Thank you so much.
Yep.
Well, thanks again.
Yeah, I will.
All right. Turn on my computer. I'll try to keep this short. Okay. So, right. So let me get that going.
You can introduce her. Yeah, we set it up.
Hello, everyone. So it's my great pleasure to introduce our next speaker, Carolyn Matl. So Carolyn is a research scientist at Toyota Research Institute, where she worked on robotic manipulation with the mobile manipulation team. She received her doctoral degree from the University of California, Berkeley, where she was advised by Rosanna Baichi and was supported by the NSF Graduate Research Fellowship. Her research focused on developing and leveraging interactive perception for the robotic manipulation of complex material such as liquid, grains, and dough. Outside of research, she enjoyed cooking for her friends and family. And I can personally attest that it's very good.
Yes.
All right, go ahead.
Thanks, Daniel. So yes, as you said, I'm Carolyn Matl. Thank you so much for having me here today. This is an amazing crowd, like feeling a little stage frighty. It's first time talking to a live audience in a while. So I am a research scientist with the mobile manipulation team at Toyota Research Institute. And prior to joining TRI, I was a PhD student under the advisorship of the wonderful Rosanna Baichi, who's here right now. And there, for my dissertation, I focused on, as Daniel said, the manipulation of complex materials like liquids, grains, and doughs. So today I'll be presenting the latter half of my thesis, how we designed a soft tactile hand and used it to manipulate deformable elasto-plastic materials like dough. So this presentation draws from two works that were published last year in 2021. The first at ICRA, which we were honored with the Best Manipulation Paper Award, and its follow-up paper, which was published at IROS. Both were remote presentations again, so it's really lovely to have this opportunity to revisit this work with this audience in person. Okay, so before we begin, let's first talk about what even is a deformable elastoplastic object. So in our work, and in fact, many works that simulate these types of objects, we categorize doughs as 3D elastoplastic objects, or in other words, objects made of materials that exhibit both elastic and plastic properties. So a simple illustration of this characteristic should be very familiar to those of you who cook or bake. When you press into dough, some of the dough springs back, but there's also some permanent deformation that can result from this forceful interaction. So modeling this type of material sounds a bit complex. And even so, we're already technically simplifying it by considering it as elastoplastic, which is rate independent of the applied loading force, instead of viscoelastic, which is rate dependent. Luckily, in the context in which we have our robot interact with our dough, time is less of a crucial variable, so we can settle for this simpler material representation. Okay, so given the characteristics of soft deformable material like dough, which has these regions of elasticity and plasticity, we wanted to come up with a way to interact with this type of material delicately. So to enable both the perception of the geometry and stiffness of the material without creating any unwanted permanent deformation. So this would be perceiving within this elastic region, but we additionally wanted to enable intentional deformations of the material through interactions with sufficient load force. So this would be acting within the plastic region. And ideally, we'd like to also optimize how we interact with and manipulate these materials, and we want to explore these ideas within the context of shape zeroing. Okay, so this talk will address these challenge criteria in two parts. So in the first, we'll discuss how we designed a variable stiffness soft tactile hand that was used for both sensing and imposing load forces on deformable objects. And in the second half, we'll examine how we can use this new technology to efficiently shape servo pieces of dough with model-based reinforcement learning. Okay, so the first set of criteria ultimately led us to design this really simple hand made of soft compliant material, which we called stretch. And so the robot could vary the stiffness via a simple actuation mechanism by stretching the membrane. So the soft tactile end effector that we designed can be categorized as a very simple soft optical tactile sensor. So meaning that the tactile interface is made of soft compliant material, and when the membrane surface makes contact with the environment or an object, its deformations are imaged by an optical sensor like a depth sensor. So I imagine that many of you here probably have worked with these types of sensors in your own work or may recognize some of these examples, so I'll just briefly go over them. So on the left, the gel site sensor and all its iterations like the gel slim from MIT or the digit finger from Meta, these are all quite popular due to their high resolution contact images. In comparison, the four pictured on the right have arguably higher compliance, which opens up a lot of applications where soft contact makes interactions safer or more robust. So for example, the TAC tip from the University of Bristol explored performing tumor detection, while the soft bubble from Toyota Research was used to handle delicate objects like a wine glass. Isabella, who we just heard from, used her own soft optical tactile sensor to support human arms and even help wipe or bathe humans. So now in the middle is the first soft optical tactile sensor that I designed at Berkeley, along with my colleague Ben McEnroe. And this sensor was heavily inspired by the TAC tip from Bristol, except that instead of filling the fingertip with gel, we created this pressurized capsule full of air. So let me briefly explain why we did that. So because we were using pneumatics to maintain the shape of the fingertip, we could also leverage this actuation mechanism to stiffen the silicon membrane by increasing the pressure inside the capsule. So not only could this device act as a tactile sensor, but it could also act as an actuator and automatically adjust its stiffness to compensate for slipping. So for instance, to hold up this container that has dynamically changing mass. So in this prior work, we really were studying this sensing and actuation duality and found that variable stiffness tactile sensing had a lot of potential in expanding robotic manipulation capabilities, including the manipulation of deformable materials like dough, since we could leverage the fingertip in its soft regime to sense by interacting with the object within the elastic region. And we could also use the fingertip in its stiff regime to apply sufficient load forces to cause plastic deformations that we intended. But note that at the same time, there were a lot of challenges while working with this prior design. So for one, it was pneumatically actuated, so this made it difficult to controllably vary the stiffness of the membrane, and overall this was quite difficult and tricky to manufacture. So fast forward to year 2020, year of the lockdown, when we wanted to revisit this problem, but at the same time, access to major design and fabrication centers was basically revoked. So all of these challenges motivated the design of Stretch, or soft to resistive elastic tactile hand, which we were able to make with supplies I basically had already in my living room. So as you can see, it's composed of a flat elastic membrane that can be cast very easily by pouring EcoFlex silicone into a rectangular mold. And we attached this membrane to a parallel jaw gripper using Velcro. And so instead of varying stiffness via pneumatic actuation, here, as the gripper increases its gripper width, the membrane's internal strain increases, and this subsequently increases the stiffness of the membrane. And so you can imagine that this actuation mechanism makes variable stiffness much easier to control. So we use a depth sensor to image the deformations of the membrane when it's in contact with an object. And with the assumption that the object is convex, the robot can extract out the portion of the membrane that's in direct contact with the object. So you can see how it's really a bare bones, like very simple flat version of the optical tactile sensors that we saw earlier. Because Stretch was so compliant, we were able to use it at its low stiffness regime to reconstruct the geometry of very deformable objects like paper boxes or 2D wire shapes like this circle through touch. And because Stretch can vary can vary its mechanical response, we can estimate the stiffness of deformable objects as well via active palpation. So the graph on the right shows multiple indentation depth to load force curves that correspond to different stretch states of the membrane, where the higher curves correspond to the membrane being stretched more. And ultimately, we want to find the force at which the object finally deforms. Since if we imagine this object as having a single degree of freedom, we can divide this force by the amount of deflection to estimate a proxy for its stiffness in newtons over millimeters. And so we can use this force depth profile to actually save time and efficiently modulate the stiffness of the membrane so that the load force increases monotonically with each new contact condition. So instead of starting from the lowest indentation depth every time the membrane stretched, we can jump up this ladder, as you saw here, to the next indentation depth that would result in the closest increased load force. And this allowed the robot to efficiently approximate a stiffness value for the object. So the robot measured the stiffness of 4 balloons filled with different materials, as you see here. And even though these are technically, again, proxy values for stiffness, since we're using this simple 1 degree of freedom model, you can see that the values increase with each object as we would expect. And the estimated values are sufficient for differentiating between materials within this range. So just keep this in mind because we'll be reusing this proxy for stiffness in our dough rolling work, where this estimate actually enables more efficient rolling. So for this first iteration of the sensor, we chose to use the robot to roll blocks of Play-Doh into balls of dough as a way of demonstrating the range of capabilities this simple sensor could offer. So first, stretch was used to measure the membrane stiffness needed to deform this block of dough. And once the robot measured how much the membrane needed to be stretched, it was commanded to roll the block of dough in circles, tracking the position of the dough in parallel to ensure that the robot was able to maintain contact with the dough while still being stiff enough to exert force on the block of dough. So this goes on for quite a bit, but once the robot thinks that the ball is round enough, it'll stop rolling the dough. And so stretch, and then in a second, you'll see that stretch is used at its lowest stiffness to measure the geometry of the ball. So here it's estimating its diameter. And then finally, stretch is used at its highest stiffness regime to press the dough ball into this sort of scone shape. Okay, so for the most part, you can see here that the robot was able to shape these blocks of dough into circular cookies. So we wanted to use this demonstration as a way to illustrate how we could use variable stiffness soft tactile hands to safely sense the geometry and stiffness of very deformable objects while also having the capability of imposing larger load forces to make intentional deformations, therefore enabling new robotic manipulation capabilities such as dough rolling, shaping, and flattening. So the next step is, how can we use this technology to more efficiently shape servo this type of material? Dough rolling the dough rolling that I showed earlier was based on a heuristic algorithm that sometimes took up to 20 minutes to execute. But we know humans can do this so quickly. So we must be able to do this more intelligently. Okay, so that's pretty much the goal for the second half of the talk. We'll talk about how we used model-based reinforcement learning to accelerate the task of rolling out dough into a breadstick of a specific length. So for this iteration of stretch, we made the entire end effector attachment out of elastic bands. And you can see here it's a slimmer version than the prior version. The depth camera was also fixed at an overhead position instead of being rigidly attached to the robot arm. And these design changes were mainly to compensate for kinematic limits required of the dough rolling task. Okay. So, however, notice that the task of dough rolling requires dynamic interactions of a deformable end effector with a deformable object. So this is highly complex and high-dimensional dynamics that are difficult to model and, as we heard earlier, even to simulate. So instead of explicitly representing the dough-to-hand interactions, we used model-based reinforcement learning to learn a transition function for these interactions. So meaning we learn from data the relationship of given an action applied to the dough and its current state, what will the dough state be after that action is applied? And so that model is represented by F here. Now, within this framework, we use model predictive control to select the best action to take at this time step given the current state of the dough. So this is done by optimizing the cumulative expected reward over a certain number of time steps into the future. So we're looking ahead, where at each time step reward is calculated simply as, well, in this case, how close are we to the desired goal, dough formation. And what the reinforcement learning framework adds to model predictive control here is that it allows us to iteratively update or improve the transition model F to better reflect the dynamics of the dough and hand interactions. So this means that if we start off with the wrong model or a poorly initialized model, then the algorithm still has time to self-correct. So I know I did just mention that these interactions are extremely complex. So this brings up the question, and a question that we think in this community a lot about is like, how do we deal with such high dimensional data? In our case, because our goal was fairly simple, we were able to simplify the problem with some engineering to make it a lot more tractable. So to simplify the state space of the dough, we took the dough formation's bounding box and used those dimensions to track the dough's shape progression over time. As for what actions to apply to the dough, well, the two things we decided to vary were the stiffness of the hand's elastic membrane, which we could vary by stretching or closing the gripper, as well as the depth at which the robot pressed the dough. These two parameters were chosen because they directly affect the load force imposed by the elastic hand. And the rest of the robotic action was fixed in that each roll consisted of a back and forth motion at the highest point of the dough formation. So given all these simplifications and action constraints, we were actually able to train a dynamics model of these interactions with only about 1 hour of robot time, where the robot randomly interacted with the ball of dough under these action constraints. Okay. So as we can see here, comparing the reinforcement learning methods with a random and heuristic policy, all of which were under the same state and action simplifications and constraints, the robot was able to roll the dough out into this 6-inch log with significantly fewer rolls. And also the robot was able to efficiently roll the dough into different length breadsticks up to basically a foot. However, what happens if the dough that is being manipulated now is not the same dough as the one that was used for training? Maybe it could be a drier dough, which could cause it to be less malleable or stiffer. It could also be more well rested. So this means it's much easier to plastically deform. And this is a really real problem because if any of you are familiar with working with dough, the feeling of the dough can change quite quickly. But because this is a model-based reinforcement learning framework, it allows the robot to iteratively improve the dynamics model, given new observations as the robot in real time interacts with the dough. So let me replay that. Oops. Okay. So here we were able to show that it's able to self-correct and efficiently roll out a stiffer dough much faster than compared to when using a fixed model using just MPC. But you might ask, well, in our prior work, we showed how we could use stretch to approximate a proxy for the stiffness of these objects. Wouldn't it be great to use these estimates to calibrate the model more quickly so that we can more efficiently roll out the dough? And yes, you would be absolutely correct in that it does help. So here we're showing our robot measuring the stiffness of these 3 different doughs that are hydrated at different hydration levels. And we were able to demonstrate through our experiments that these stiffness measurements do indeed help the robot regress to a better dynamics model for the dough interactions. And this leads to significantly more efficient rollouts. So if the robot sensed that the dough was soft, it would use a different rolling technique than if it sensed that the dough was hard. And the actions chosen by the robot actually made a lot of intuitive sense. So for instance, for a hard dough, the robot chose to apply actions that corresponded to higher force output, versus when it sensed that it was a softer dough, the robot chose to first apply low force to the ball until it formed into a short log, and then it started increasing the membrane stiffness to finish rolling the ball out into a longer log. So as a brief recap, through these two works, we explored how we could use a very simple variable stiffness soft tactile sensor to sense the contact geometry of very soft deformable objects, as well as to measure a proxy for stiffness for deformable objects, and finally to use that information to efficiently shape servo dough. I'd like to say, though, that there are several avenues of future work to explore here, since we really viewed this work as a stepping stone into new directions for soft robotic manipulation and sensors. So, future work includes, for one, while our simple state and action space of the dough allowed us to simplify the dimensions of our problem, a higher dimensional space would certainly allow us to explore more interesting shape servoing problems, as well as to allow us to create a tighter sensory action loop. Furthermore, there's been a lot of great recent work on modeling deformable contact and deformable objects, some of which was presented today. So I would love to see how those models can be incorporated to in a robotic system to deal with materials like dough. Finally, because this work was done during COVID times, Play-Doh made the experiments a lot more manageable to do in a household setting, but the dream would be to shape real dough, which is way more elastic, way more malleable, sticky, and tricky to deal with, but at least at the end, you could actually eat what you make. So I just wanted to take this opportunity to thank my collaborators, Rujna, Isabella, and Josephine, as well as the ICRA workshop organizers for inviting me. This was a really great opportunity. If you have any questions, don't hesitate to reach out to me at my new email. I also just wanted to give a little plug that at TRI, we work on related problems for deformable object manipulation, and we are working on things like dough rolling or food prep. So we are hiring at TRI, so don't hesitate to reach out if you're interested in a role there. Great. Yeah. Take questions.
Yeah, thank you very much for the great talk. I think we can take maybe 2 questions from the audience, and then we'll move on to the panel discussion, which concludes the workshop. But if anyone has any question for Carolyn, please, please line up or ask online. I think we have one. Yeah.
Great talk.
Thanks.
I'm curious about the stiffness of the object.
Yeah.
So you showed some numbers for like the soft dough or hard dough. Is that relative, or is that some number you can actually trust as like the softness or hardness of the object?
Yeah, so again, I mentioned it's a proxy for stiffness because we use a one-dimensional model, but it is a actual number that you can measure, if that's what you were asking, because it's based on basically the state of the soft hand, so how far it's stretched and how far it's pressed into the dough. And based on our model of the sensor hand, we can estimate the load force that it's imposing onto that object. And so taking that load force and the amount of deformation you actually sense at that contact condition, you can just basically divide the force by the deformation to get this one-dimensional estimate of stiffness. Yeah.
And the accuracy seems to be in like hundreds of newtons per.
Yeah, it was within 1% of the operating region of basically the load force that we could measure. So it was fairly repeatable. So that gave us confidence that we could even though this might not be the most accurate representation of stiffness, it was enough, it was sufficient information there to help us accomplish like more efficient dough rolling, for instance. Thanks.
All right, let me just check online. So we don't seem to have any more questions. So thank you again.
Thanks.
And with that, we come to the last item of the workshop, which is the panel discussion. And for that, I invite all the previous speaker ladies in the panel to come up here, and we have a nice discussion about the formal objects. Who would have thought? Yeah. So let's see if this works. So basically, you guys sit around this table, remove the garbage.
Well, I think we should just have everyone.
We also have Andrea over Zoom in a true hybrid fashion.
Yeah. A little social distancing here.
And now we play musical chairs.
This. So I think if we arrange like this, it might be better. And I hope this mic is able to pick most of you up. Let me see if I can. Oh, I lost it. Can you help me with that? Hold it. Thank you. So how is the sound quality, Martina? Can you hear me?
Yeah, it's good.
Okay, so this distance seemed to work.
Okay.
Yeah, we therefore open the panel discussion. To make it a bit more structured, I think it's good to, we have 2 prepared questions, and then we have a short statement from each of you, and then we have some back and forth towards that. And I think, Martina, you can start with the first question, and then we go first with the hybrid. So Andrea first, then we go to Carolyn, Rika, and so forth. We reached. We are back, and then we go to the next. Yeah, let's see how this works.
Okay, thank you. And thanks you all for being here. So the first question we wanted to talk about is, what do you think that are the main challenges and bottlenecks for achieving good performance in the manipulation of deformable objects? So maybe, Andrea, if you can start talking about this.
Yes, thank you. So thank you also for letting me speak first. So yeah, it's a very I would say broad question, because the field itself is broad, so it's hard to I think this comes out regularly at these meetings. There is so many different things we consider as deformable objects and different approaches. So well, I usually don't self-cite, but we did write a paper a few years ago. I think it came out in 21, which was a follow-up of a similar workshop, and it was on RAM, and we mentioned, in fact, the challenges and methodologies which should be addressed by newcomers in the field. And I think well, of course, that paper came out on IEEE RAM, and I recommend it. But my personal opinion, is I think perception is crucial, and of course modeling, which comes along. So I think nowadays it's really very difficult to have this perception modeling running online at interaction time, so that the robot can operate immediately on the object. But again, it's very, very, I mean, there are other things as well. For example, the grippers and the hardware we have are not good for certain tasks. It really depends on the tasks. But we should have better touch sensing. So now there's a lot of buzz, and I think it's very nice with the gel site type of tactile sensing, which are cheap and seem to be very performing. Maybe that's also a good tool for manipulating soft objects. Yeah, that's my 2 cents.
Okay, that's great. Thank you. So maybe we can keep moving to the speakers that are in person. So Michael, maybe you can moderate now.
Let's go. Right, we start with Carolyn and then we go this order.
Okay, yeah. So I think the question touched on like what are some bottlenecks in this area, and I would say that I think there's a microphone there. Oh, should I just pass it around? Oh.
Yeah, try passing that around.
Okay.
But the audio is fine.
Okay.
One for the room.
So
okay.
So in terms of bottlenecks, I would say that the more complex of an object, like when we start looking at doughs, for instance, or granular materials, right? How do we find a good representation that kind of succinctly summarizes what we need to know about that material or object that allows us to accomplish whatever the goal task we want to do? How do we deal with like such high dimensional representations and dynamics, right? I think figuring out how to represent those succinctly and efficiently is kind of where I see the bottleneck right now. And I think a lot of people touched on this today.
I think one of the challenges we have is figuring out if we do want to learn from simulation and how much is really the central gap manageable in this sense. So it seems that the rigid, in the world of the rigid bodies, people know very well, their biggest enemies, the contexts through which they cannot differentiate, that create, chaotic behavior and so on. And it would seem at first glance that we have it easier in the deformables world, right? Because maybe the context is softer. But it is still unclear whether we benefit enough because our models would have to be necessarily harder. So I think that's kind of one of the big challenges to understand in the kind of time of the big data and being able to collect a large data. Should we go more in the learning from real data, collecting large data sets, building large models from real data, or should we push on a lot more on making the simulators usable and learning from that and so on? So I think that's kind of one of the challenges that we had. Very like robust simulators that have very small, like a manageable sensorial gap that maybe we could make even faster progress.
Yeah, I think in deformable object manipulation, there are so many challenges. It's like really hard to pick one. But I think one thing that really bothers me a lot, what I think a lot about, is what is supposed to be the right state representation. I think it's independent from the method that we take. Like if we want to define a task in deformable object manipulation, you need to define the goal state. So how we actually even define the goal state? And I think right now, what we mostly see is that we cannot choose different representation based on different object we manipulate, based on different tasks we are trying to do. And is there a way that we can unify it? Is there a representation that can be like unified, applied for any objects or tasks? Yeah.
I definitely agree with that last point a lot. I think that particularly in my application spaces, what does it mean to succeed? What is a reward? Where do we get these values when we're talking about complex tasks that people spend decades learning to perform, and the right way to perform is one of the things that I think about a lot. And then also more complex modeling or inferring kind of environmental reaction or interactions outside of just the deformable object you're manipulating. So ways in which it's adhering or adhesion to, the ways in which it adheres. There we go. Thanks. My PhD is not in English. So, modeling these, overcoming these, accounting for these in safe ways is one of the things that I
So I agree also. I think what Carolyn and Shuran are pointing out is the complexity of state in this environment. I think it relates to this issue of reset that I think we all struggle with, because we want to try experiments and getting back to the same initial state is very difficult. So that it's hard to compare performance in many of these contexts. The one thing that I just walked past the compliant motion manipulation workshop, and I think compliance is really important here, because when I think about how I manipulate many of these soft objects, I'm using some sort of compliance. I'm not really, for example, with dough or granular material, I'm not actually ever really knowing the state of all the different objects or the components, but I'm scooping my hands in such a way that they force the objects to comply with my hand surfaces. So understanding that in some way, it may be really important, because we may not need to know the precise state of the system, but we can impose constraints such that the state has to conform to what we're looking for.
Yeah, I'm really happy you all brought up the idea of representation, because these objects are so complex. We tend to err on the side of the more quantities that are captured, the better. But that gets me thinking a lot about speed and the usability of these simulators that we all basically work with. And so, for example, like, we can't really use online deformable prediction right now. Simulators that are accurate are slow, and at the same time, if you want to train these surrogate models, we need a lot of data, but to collect a lot of data, you also need speed. But it's kind of a circular problem, because if those, let's say, for example, FEM solvers were really fast to begin with, then we wouldn't need to collect that much data. So it's kind of a problem of anticipating, what should be solved first? Do we wait for a compute to catch up, or do we pour an effort into data and training to kind of solve the speed issue?
Right, thank you very much. Now we have the chance to add something. Now you have heard other panelists speak. Maybe you want to add something to your original answer. If not, we move on to the second question. Additional insights? No takers?
May I ask a follow-up question?
Yes.
Okay,
please.
so we all know that deformable object is so hard. But is there some like good aspect of it? Is any aspect of deformable object actually easy, or we actually solve like anything that we can think about?
It's funny you say that, because I was just thinking, one thing that really we get for free is grasping. Grasping is really easy. I mean, it's if you put a stuffed animal in front of a robot, grasping that is completely trivial, right? So you can impress visitors that way too. Just put a stuffed animal on, the robot will pick it up and they'll go, wow! But it's so easy because of natural compliance. So grasping is one. I don't know, others? Benefits?
Scalable.
I just want to counter that with Isabella did show that grasping tofu is hard though. So there definitely are categories where grasping is a lot easier. Like at Toyota Research, right now our challenge on my team, on the mobile manipulation team, our challenge task is to grab things off the shelf and shop for, help a shopper out, go to a grocery store and grab random things off the shelf. And some of the easiest things to grab are bags, because you just go in and crush them.
Yeah, it's true. Bananas.
I see. Oh.
Who should answer?
Yeah.
As you know, I'm your quintessential academic, so I will take that approach, but I have the following observations. Number one, this is completely at the beginning. You really are just testing the waters how to deal with the compliant objects. However, academically, if you go, and my colleague Ken is here, go to the mechanical engineering department.
Sorry, can you just join the panel?
Oh, sure. You can find our colleagues in mechanical engineering department who wrote whole books on continuous mechanics and deformation and elasticity and all that falls into that. Now, it seems to me that one of the things have to be done here is to have students to learn maybe the whole book of continuous mechanics, but certainly the principles that the mechanical engineers and mechanicists have developed over the 200 years. This is really not new for them. So that's number one. So then, given that we go through that exercise, what is obvious to me, and Caroline showed that very nicely, we need better observables, measurements. I mean, she developed together with other students, Isabella in particular, this tactile sensor, but there are many variations of that. And the question is, what is an ideal observing system that we can measure easily, quite quickly, repeatably, the measurements of the stiffness. Now, finally, I would say that to put all this together as again, the mechanical engineers have the finite elements system as their Bible. I mean, so there are software packages and all that. So the question from application, and Professor Tucker made a very strong point on that, is speed. How do we can compute this whole thing fast? Because I don't want to be under a robotic surgery for 1 hour when the machine computes how to do the surgery. So those are my comments. Thank you.
Yeah, thank you very much. Is there some comment to the comments? Or we move to the next question?
May I say something?
Absolutely.
Okay. No, I just have a comment, a bit provocative about this unique representation. I think someone mentioned it. So I'm a bit, sometimes I'm a bit skeptical about this because I feel like maybe what we are doing, most works are application driven, and it's such a broad field to my, in my opinion, that it's probably, I mean, I understand that some methods should be transferred, but targeting a unique representation to me seems like a utopia. It's like if you replace the non-rigid in your workshop title with rigid, robotic manipulation has so many different perspectives. Just look at the parallel sessions we have at ICRA or IROS conference, because you can have in-hand manipulation, you can address pick and place, you can address compliant manipulation, so many different things. And for each of these, we are still struggling to find the benchmarks and challenges. Or I mean, by challenge, I mean like the DARPA challenges. Amazon came up with one format, but it was very specific for the pick and place. So yeah, unique representation maybe should be mechanical, but even the mechanical, if you deal with strings or fabric or it's very variegate. So I'm just not too convinced about this, but that's my opinion.
Thank you very much. I think we can move on to the next question. Martina, if you like.
Yeah, thank you. So thanks also, Andrea, for this last comment. That's true for sure. And the next question is, what is the state of current simulators for deformable objects, and what features do you think are currently lacking? So maybe we can start again from you, Andrea, if you don't mind.
No, I don't mind, but unfortunately I don't have a neat answer for this because I haven't worked with simulators so much as you saw. So now we work a bit with SOFA, which we just started with. So it's a mechanical simulator, but I don't feel aware enough, knowledgeable enough to reply on this. I would say we basically generally we work offline with the images we acquire from objects because we do a lot of vision-based work. So we don't really trust the simulators for what we have to do, which is maybe a mistake. So that's all.
Okay, thank you. So maybe we can switch to the in-person speakers. So Michael.
So it's been a little bit since I've worked with a simulator. The last simulator I worked with was Isaac Sim, which Rika and Isabella presented work on. And so obviously it's gotten a lot better since I've worked on it. But I would say one thing that I would love to see with simulators, like an advanced deformable object simulator, is being able to simulate more complex material properties, like, for instance, stickiness. Like, I don't know anything out there that has that capability yet, or time-varying properties, right? Like, I'm just thinking of dough again here. Like, if you let it sit, it's going to become more malleable. Like, how do we simulate that, right? And yeah, even representations in simulation, like if we cut a piece of dough in half, how do we know that's like the same piece, but now separate entities, right? Like, I think those are all interesting questions to ask.
So I work more with the simulators on the speed side, so training from large-scale simulation, and for that I was pleasantly impressed with PyBullet actually, from which we built one of our frameworks that I talked about today. It handled underneath it has two different deformation, like generic deformation models, one of which is FEM, and you can make it reasonably fast. So not maybe as fast as you can do real-time MVC with it, but definitely as fast as you can collect thousands and thousands and maybe millions of like data points for your learning algorithms. So on that side, I think we're good, and especially with Isaac Jim incorporating and hopefully releasing into the wild more of the deformable properties and deformable models as well. Now, the issue is that I think there is a difference between that mode, where we're interested in reinforcement learning, like large-scale learning from simulation, and the mode which is more close to what we need in robotics, where I'm dealing with a particular object. I want to simulate this particular object. And for that, probably simulators are pretty slow unless you go to the high precision ones, unless you give up on the precision. And so this is something that I think was mentioned also before when we were talking last year in different workshops, that what we don't currently have with simulators is it's not like we don't have fast simulators. We have fast simulators, but they're not precise. We also have precise simulators. But what we don't have is a very flexible way to go from one to the other without really digging into the internals of the simulator, which takes up a lot of time. So I think if we spent a little bit of time kind of as a community to figuring out how to make the user interface such that you can say, here is the knob, I really want precision, and here is exactly how slow I expect this to be. But within the same simulator, I can turn that knob down and I will get speed. And this is something that would be nice. Currently, we have this, but we have it in all different kinds of simulators, so you have to switch between them to get these different modes.
Yeah, I think that's a really good idea. I want that too. And I think it can be used in different stages of training, right? For example, in the beginning, we can use the fast one and get more diverse training data. And then in the later one, we can actually use more precise one to do same-to-real adaptation. Yeah, I think if I want to say something else, I think I really don't expect that the physics simulator is able to simulate everything that I want, but I do hope that we can do a better job to describe the limitations of simulator in a way to the end user or to researchers. I feel oftentimes we kind of discover the limitation of the simulator while we are doing a research project or in the middle of doing a research project. And I kind of feel like this idea of like from computer vision or like just in general, like creating a data sheet for a data set, like describing the limitations of your simulator, like kind of in a clear way or easy to understand way, I think that would be really helpful.
So I'm sure I know the least about the existing simulators of anybody up here, but I can tell you what I want to see in my applications that I don't see in the ones that I've used at least, and those are complex materials, so multi-material, non-homogeneous things. Changing topologies, right? The ability to cut and to adhere and affix things to other things and still have it work. Piercing, suturing, things like this. So those may exist out there, but I haven't seen a ton. So tell me if you have that. Tell me. I'd love to see it. But
yeah, so I think that it's great to see so much interest in simulation right now. I think that Mujoko, DeepMind's purchase of Mujoko is a very interesting moment because they're putting a lot of effort now into more realism. And again, the danger with simulators is that they appear very realistic. And it's very easy to fool the eye, and so we can convince ourselves, hey, this seems to work, but then it doesn't transfer. So I think that one of the factors is somehow capturing the uncertainty that's inherent in the motion. Maybe the non-determinism, because simulators are generally deterministic, and so we don't see that variation at all. But it would be nice if it could show you a range of outputs outcomes that might happen. Let's say if you provide an impact to a cable, where's a range of places that it could fall or land. So capturing that, I think, would be really interesting. The speed, as Rujna said, I think is very critical. We do have lots of access now with the cloud to very fast computing clusters that can speed this up. I think, as Caroline said, the issue of time-varying material properties is really interesting because in surgery, for example, you absolutely have that. So as soon as there's a manipulation, you immediately get edema and changes in blood flow, and so that changes the material properties. So surgeons somehow find a way, humans do, to on the fly adapt to changes of the property of their materials. So it seems like there's something where there's some fundamental approach that's not so dependent on the material properties that we seem to use, and then we adapt it on the fly based on observation to what's happening. And you're absolutely right also about tactile, because if you think about people who are blind, their ability to manipulate is actually quite good. So that's something we're completely missing. And gel site hopefully will be a way, but gel site is interesting because it's not particularly tuned to deformable. It's very different, rigid. So that's another area that we'll have to struggle with. And the last thing I want to mention is this idea of competitions or benchmarks. That if we had some good benchmarks that we could all try and work toward and then compare against, would be very valuable. And I saw that the group from Carmen Torres and WPI are proposing this competition next year, which I think is a really great idea.
Yeah, in terms of simulation, each one that exists has their downsides, mostly that they're not super accurate. But I think we are in a very unique position right now. Simulators in the robotics community are really just starting to ramp up, and that's mostly due to the ability to accelerate using GPUs. But these simulators have existed for a long time. For example, in mechanical engineering, right? Phenomena such as adhesion, heterogeneous materials, time-varying materials, they can be simulated, but they're painfully slow. On the other hand, the graphics community has also worked independently on their version of simulators that might not be physically accurate, but are fast and look correct. And as I mentioned in my talk, there's just so many different metrics that we might be interested in when grasping deformables, and they're object dependent. So for example, the tofu, right? We could not simulate breakage in tofu or permanent deformation in tofu with our linear elastic model. And to my knowledge, neither do any of the existing robotic simulators. But if we could kind of have a plugin or a way to kind of switch up the model such that breakage is modeled, but maybe you trade off accuracy in other scenarios, that could be great. A good example that I can also think of that has actually been done in practice is the problem of interpenetration within many of these simulators where your mesh kind of crosses contact and you can't separate them after the next time step, and that's not physically realistic. But Chungmin, who is Professor Goldberg's student, like for example, she has repurposed a backend that uses IPC, incremental potential contact, to then build up a robotic simulator that solves that issue of removing interpenetration, but perhaps add a bit of a trade-off for accuracy in some other ways. So I don't really envision like this totally generalizable, beautifully fast simulator in robotics that works for any situation, but I do hope that we can kind of pick and choose which physical quantities we care more about and kind of have our simulator be flexible to that based on different objects and different tasks within one environment. I can foresee a future where that might be realized, and I think that would be useful to all of us.
I agree. Well, I will say one thing. What to me this all suggests, we need very strong interdisciplinary groups attacking these problems, and you have been doing it, and I have been partially doing it. But I think that from educational point of view and from university point of view, the walls between departments need to be removed. And so that it's very hard to think about in one PhD, like Isabella is, to deal with and know every outcome from material scientist, from the mechanical engineer, from the user, and even chemist, because a lot of these materials are due to different chemistry, to really include all of that. But if she, and I am as guilty as anybody else, if I would have generated an environment of all these people, then possibly she would have had an easier and much more generalized system as she has now. I mean, I'm very proud of what she has accomplished, but nevertheless, it really points to this thing that we in academia still are promoting individual accomplishments in individual fields, and these problems require much more breaking the walls.
Thank you very much, everyone. We do one last kind of round. I mean, first, if there is any comment to the comments. Let's do one final round, 20 to 30 seconds. Each speaker, what do you want to emphasize the focus on for the future? Like, where should we go? What should we put in grant proposals? Where should the community move? Let's start with Andrea again.
In terms of I think the applications should be oriented by society, and we should not forget that this is our purpose. Other than publishing as much as we can, we should also solve useful problems.
Sociology.
And that's one thing. So currently I would think medical maybe, or I saw a lot of things about fabric and clothes folding, and I think I ran out of time.
Thank you. 30 seconds. That was the most important part. So these parts are the ones that come out.
What is the 30 seconds?
Yeah, because then if you only have 30 seconds to answer, only the most important things make it through.
All right, I'll start. My 30 seconds. Okay.
Go.
So for deformable objects, I think being able to perceive important properties, material properties, or dynamics of deformable objects is important. And I'm blanking now, so I'm just going to pass on the
right? I think we have an opportunity to benefit from high speed up that we get, GPUs, big compute resources. And I don't think that we as a community know as of now what it is that we want to invest it in. Is it like a big FEM simulator that would do a very precise thing? Is it some particular phenomenon that we want to model? So basically figure out how to make use of the larger compute resources that we might be able to have and get that, yeah. Okay, I want to say something different. Okay, so I also multi-model or multi-sensory learning. I would say that we have a lot of sensors out there now, and also we're kind of converging on the method as well, like all deep nets, right? So I think, yeah, it is a good time to actually consider like merging all different type of sensors. Yeah.
I guess I would say that we should start from the ground up, keeping kind of the human in the loop in mind at every step. So what are the data requirements? What's the burden on collecting that data? How do these things generalize to new tasks and new users and new environments and things like this, so that we keep that.
So I think this real to sim question is something that would be very interesting to make progress in. I think if we could, even if we had these great simulators that we're wishing for, we need to instantiate them for our materials. So if we could find ways to do that quickly and adapt them to new materials, that would be very valuable. And I think that benchmarks is also going to be just so important for advancing this area.
This is not something I have personal experience with, but something I've seen come up from others' works. That's the idea of differentiable simulators for deformable objects. I think that's a really exciting field because it's useful. You can actually optimize over inputs and do some useful control. And yeah, I just think that's an exciting thing to investigate as a community.
I have nothing to add.
And with that, we reach the end of this workshop. Thank you everyone for participating. A special thanks to our speakers, our panelists, as well as everyone that contributed to the workshop, and as well as for the spotlight session. And I hope we see all of you next year, and let's do more deformable objects.
And I think we need a big round for the organizers who did a fantastic job.